Okay, so then good morning, everybody, and welcome to session number 6 on the last day of this exciting conference. Keynote given by Maurizio Peruzzini from CNR Econ, Sesto Fiorentino, and he will talk about synthesis, reactivity, and catalytic applications of exfoliated black phosphorus. So please,
okay.
Maurizio, could you...
So good morning. I ask Valentina to start my presentation, please. Good morning, everybody. Good morning, Mr. Chairman. Thanks, Stefan, for your previous kind introduction, and thanks to everybody for assisting this morning session. We will talk exclusively about phosphorus chemistry, that is the chemistry of exfoliated black phosphorus, indeed, which is an extraordinary 2D material, as it has been already mentioned by Miriam in her brilliant lecture before. So we can move to the first slide, please. That's a very old-fashioned presentation, let's say, in which the speakers say somebody to move to the next slide or to the previous one. I'm sorry, but we will try to do our best with this kind of presentation. Well, the first slide that I would like to introduce you is the one that makes a sort of panorama or scenario of phosphorus chemistry. You see that the chemistry of phosphorus, it is not only in my opinion, a fascinating element in the periodic table, came out from the alchemy time in 1669, when an alchemist in Hamburg was capable of obtaining white phosphorus by distilling putrefied human urine. After 200 years, it was recognized that white phosphorus was not the only way by which this kind of element could be present in nature. And indeed, the phosphorus, like carbon, by the way, is one of the elements which present the larger family of allotropic forms. In particular, if you play with the temperature and the pressure, you can move from one allotrope of phosphorus to the other allotropes. And indeed, if you heat elemental phosphorus, white phosphorus, to over than 280 degrees, you get a polymeric form of white phosphorus, which is named red phosphorus, which is red colored, and which is completely different from the white one. In particular, red phosphorus is not toxic, it's not harmful, and is absolutely stable in the air, which is extremely important as well. Later on, about 100 years ago, playing with pressure and working at a very high pressure of about 12,000 bar, it was possible to transform white phosphorus into black phosphorus, which is a three-dimensional modification of the elements, which recall, let's say, graphite in its main form. And of course, red phosphorus can be transformed into black phosphorus, and all this one can be transformed into each other by increasing or lowering the temperature at working at appropriate pressure. And you see in this slide there are different modifications of white phosphorus. Among them, violet phosphorus has been recently upgraded to the form of a real allotropic forms of the element, which is in between the red and the one and the black. But what is important to this lecture is that in 2014, about 100 years later, the discovery of black phosphorus, it became evident that the three-dimensional structure of black phosphorus could be easily exfoliated. And so the single layer of elemental black phosphorus can be ideally obtained by Scotch tape exfoliation methods. As a result, an extraordinary 2D material was produced, which was nicknamed phosphorin. And you see on the top, colored in blue, a sketch of this element. The next slide, please. Okay, so in principle, black phosphorus is related to graphite, and graphene is related to phosphorin. And in principle, you can do this via an, let's say, conceptual experiment in which you exfoliate graphite, obtain a sheet of graphene, and you add hydrogen. You make an hydrogenation reaction of this 2D material, and ideally you had the hydrogen atop at the bottom of each carbon atoms of the system. The next, please. Doing this, you transform the sp2 hybridized network of carbon atoms into an sp3 hybridized network of carbon atoms. Of course, the addition of hydrogen atom on the surface of graphene, on the surface of graphite, and then forms this single sheet of carbon atom, transform a system which becomes no more stable in the flat form, and obtain stabilization by removing the tension and then transforming into a form of corrugated Honeycomb network, which is, let's say, compatible with the carbon sp3 hybridized system. In this case, the next, please. You can get a compound in which all single CH group of graphene have been replaced by single phosphorus atom, which are hybridized sp3, which are therefore packed in their form, and which highlight the isolobal connection existing between single phosphorus atom and methinic group, which is one of the must of the, let's say, isodiagonal relationship existing between phosphorus and carbon atom. And this is a result of the, let's say, hypothesis that brought Professor Roald to get the Nobel Prize in 1981. May I have the next one, please? Okay, and you see what happens in 2014. This is a report of the last years of phosphorus chemistry, as it has been reported in papers, came out from a perusal of literature data, and you see that moving from until, let's say, 2014, the chemistry of black phosphorus was completely neglected. So the number of papers that was devoted to black phosphorus were extremely few. You see that also the other allotropic forms of phosphorus was not particularly studied. But in 2014, there was a rapid increase of attention for these new, let's say, allotropic forms of the element, and this came out from the result that phosphorine was indeed produced. And then the possibility to exfoliate black phosphorus and to form a single flake of phosphorine was a sort of a boost for this kind of chemistry. And you see that in few years, the number of publications dealing with the words black phosphorus or phosphorines in the title becomes extremely abundant in the literature, and are still continuing to become extremely abundant, because in particular they capture the attention for the many reasons that Miriam has brilliantly exposed in his presentation, for the many reasons that attract the attention of physics, for the spectacular, let's say, photonics and optics properties and electronic properties of these new materials. May I have the next slide, please? Okay, this slide reports the synthesis of black phosphorus. You see here that the synthesis that has been obtained in our laboratory comes from a modification of the reported method. You see here that we start from red phosphorus, which is not a toxic allotropic form of the element, and we make the reaction in a quartz ampoule in a closed system, controlling rigorously the temperature and working in the presence of tin and tin tetraiodide at the appropriate temperature. By doing this, please, the next, you get the formation of beautiful crystals, crystalline forms of black phosphorus. The next one, please, which can be characterized by several methods. This is a microscopic electronic photograph of this material, and you see the lamellar presentation of the material at the micrometric definition. May I have the next one, please? Okay, this is some of the properties of black phosphorus and phosphorin. You see here in particular that black phosphorus as an sp3 hybridized element. The surface of black phosphorus is absolutely puckered. And what is particularly appealing and what is particularly important is that this kind of allotropic modification of phosphorus exhibit a sort of band gap, which is about 0.3, 0.4 for the bulk modification, and increase once the compound has been exfoliated. In particular, if you are capable of exfoliating black phosphorus till to the monolayers, you move to a band gap of about 2 electron volts. And in this way, you get interesting electronic properties to be tuned out by controlling the band gap of the element. By the way, phosphorus is not carbon, and the reactivity of phosphorus is already a problem, is always a problem, and in particular, the chemical reactivity of black phosphorus, in particular the exfoliated black phosphorus, becomes very high. And this high chemical reactivity does not help working with this element for electronics and optic application in particular. The next, please. You see here a nice, let's say, figure which show you the different kind of 2D materials as was represented a few years ago. This is, however, a very nice slide that I keep because it seems to me extremely appealing. And you see here that there are many elements which cover in the 2D forms different band gap, moving from graphene to the boron nitride, which I think will be one of the target of one of the next presentation as well. May have also the next slide. Okay, one of the most important properties of black phosphorus is the fact that the compound shows an anisotropic properties depending of the axis by which they are considered. In particular, the electrical conductivity is highest towards the so-called armchair direction, whereas, may have the next one, the thermal conductivity becomes particularly relevant in the armchair, in the zigzag direction, that is the perpendicular direction to the previous one. And you see that this is a very peculiar property of this kind of 2D materials, which is extremely appealing for, let's say, application in optics and electronics as well. The next one, please. Okay, this is a slide that presents the many applications of black phosphorus and exfoliated black phosphorus. I would like just to stress in the last times also the importance of biomedical application that is coming out in this kind of chemistry and physics. The next, please. Okay, this is the way by which the compound is prepared. The Scotch tape application, which is the normal one, and the one which was used to reproduce the method by which graphene was prepared. And you see on the right side of the slide the liquid phase exfoliation system, which is the one that we use generally in my laboratory to produce good quality of exfoliated flakes of different thickness. And on the bottom there is a paper, the first paper that we published in this chemistry, that put evidence to the fact that a small amount of water is not innocent in the synthesis, in the preparation of exfoliated black phosphorus by liquid phase method. The next one, please. Okay, these are the functionalization of exfoliated black phosphorus. In the literature, let's say, while the aspect of physics are particularly studied, the chemistry of black phosphorus remains largely unexplored, and in particular remains largely unexplored the way by which black phosphorus has been functionalized. Here is a perusal of some of the literature data. The first one is one of the first papers dealing with this aspect, came from Andreas Hirsch in Germany, and was published in Angewandte, and they represent the reaction, the stabilization of black phosphorus by electron transfer reagents or van der Waals interaction, which complicated extended molecules, like, for example, this diamide. The other one is the tetracyano TCN2 molecule. At the bottom of the slide, you see another paper, which was largely claimed in 2016, later on has been a little bit reconsidered, and report the first example of supposed covalent functionalization of phosphorine, of exfoliated black phosphorus, and comes from the reaction of titanium isopropoxide, tetrakis isopropoxide, with sulfonate group. As a result, a surface of a real sulfonate is decorating the black phosphorus area. But however, the characterization was very weak, and in recent years this compound has been reconsidered. The next, please. Okay, this is another example which is more robust. It came from the group of Tobin Marks in Chicago, and there was the decoration of the surface of black phosphorus exfoliated with aryl diazonium salts, and at the bottom a variation of this method which produced aryl iodonium salt, which were more robust and particularly more stable towards oxidation reaction. But you see that, may I have the next, please? You see that until this time, the real method of decoration of white phosphorus, that means the chemical functionalization black phosphorus, were extremely low. There are also examples of reported carbene and nitrine decoration, but so the methods are still need some improvement and some improvement. And this explains why in recent times, with one PhD thesis carried out in my group, we decided to investigate in detail the chemistry of exfoliated black phosphorus with organometallic precursors. In particular, we selected our attention to the compound that you see here, that is a dimer of palladium containing an eta3 allyl ligand, a bridge of chlorine ligands which connect to palladium allyl system. This compound is very known in the literature for undergoing very easily, let's say, bridging breakage by reacting with a simple sigma donor ligands, for example, phosphine, like the one which is reported here. This is a compound in which triphenylphosphine is reacting with a dimer, forming mononuclear compounds in which the ligand is still eta3 coordinated to palladium. On the other side, you see an example of eta1 coordination, which comes from the detachment of the eta3 coordination, and the organic ligand remains eta1 coordinated via the carbon atom to the palladium group. By the way, we studied by DFT methods the different coordination abilities of different organometallic fragments, including this one, and we see that there was the possibility to stabilize, in principle, to get stable compounds either in eta1 or eta3 model. There is a small difference in energy between the two fundamental structures that are here reported. And then, once we prepare this organometallic compound, may I have the next one, please? We take advantage, this is a report about the theoretical analysis. What is important to say here is that the single phosphorus atoms of phosphorine still contain a lone pair which is oriented atop from the surface of elemental phosphorus atoms. But what is important is that the spherical requirements are such that the lone pair is not oriented orthogonal to the surface, but is bent and is projected towards about 30 degrees inside, let's say, the cavity formed by the adjacent phosphorus atoms. In other words, may I have the next one? In other words, we are very careful when we consider the bonding capacity. We should be very careful when consider the bonding capacities of transition metal ligand systems towards phosphorus atoms. And you see here different possibility. Sometimes the steric repulsion between the interacting systems and the phosphorus and lone pairs are so high that the compound is no more stable. You see here some example. I don't enter in detail. I would like to stress the fact that this theoretical calculation comes from the group of theoreticians working in my institute in Florence, Gabriele Manca, Andrea Ienco, and the senior of the group was Carlo Mealli. May I have the next, please? Okay, this is our results with this chemistry. We reacted the dimer of palladium with two exfoliated black phosphorus in dichloromethane at room temperature in a suspension, agitated suspension, stirred suspension, and we get a compound in which there was a palladium phosphorus ratio between 1 to 32. It does mean that the surface of black phosphorus, exfoliated black phosphorus, was decorated by palladium centers. We expected indeed the formation of an organometallic grafted materials, which could have been one of the two structures that are presented here, which are a little bit different in energy, and we were very keen to characterize this compound. Okay, let's move to the next slide. You see here that we started the characterization, the usual characterization of, let's say, 2D materials, then in the solid state characterization. In particular, we started the characterization with powder X-ray diffraction analysis in Raman spectroscopy and XPS methods. And we were a little bit, let's say, worried at the beginning because the results of these investigations did not show the presence of any chlorine in the molecule in particular. And I was really at the beginning disappointed, but then became extremely intriguing. Also because the system was absolutely reproducible with different but controllable amount of palladium. We have no presence of palladium nanoparticles and palladium phosphide species, which are absolutely known, and the solid state characterization method were absolutely clear on that. And the structure, the crystalline, the lattice structure of black phosphorus is presented in the material, is preserved in the material. Also, the system was absolutely homogeneous in the distribution of palladium, and it contains just a single palladium species, independent from the amount, from the loading on palladium on the surface, which was ranging between 3 and 6% at maximum. May I have the next, please? Okay, you see here some other results. So the point of importance was the fact that chlorine was not observed in our analysis, and so we had some ideas that even the organic fragment could not have been present. In particular, we then, for excluding the presence, for completely excluding the presence of the organometallic fragments, we prepared the carbon-13 labeled compound, and then we repeated the experiment with the carbon-13 labeled. We ran the carbon-13 solid state NMR spectroscopy of the system, and we observed indeed no significant signal of carbon-13 in the spectrum. It does mean that the conclusion was that no organic ligand in the material was present, no organic ligand in the material was present, and that we decided to investigate further on the system by using sophisticated electron microscopy technologies like the HAADF STEM and solid state method like ESAF study. As a result, we obtained indication that there was a clear coordination of palladium atoms, not as a single atom, but in the form of palladium-palladium units. It does mean that the system has been decorated with a dipallada palladium-palladium units, in our opinion. Now the paper has been just accepted just a few days ago in the Journal of the American Chemical Society, but it was a very hard work to get all the proper methods to convince the reviewers that we were on the proper direction and our hypothesis was good. May I have the next one, please? Okay, this is the results of the EXAF studies that were performed at the synchrotron, Soleil synchrotron. We have to thank indeed a great expert of these methods, that is Francesco Da Capito. And what is important to stress from this slide is that there is a sort of first coordination of single palladium in which we can see that there is let's say a privileged distance of 2.34 angstrom between phosphorus and palladium, which suggests a very strong interaction, let's say a sort of covalent interaction between phosphorus and palladium, which is absolutely a new observation in this kind of chemistry. The second observation is that there is a sort of second shell, which is present at about 2.8 angstrom, which is attributed to a palladium-palladium separation, and which is, let's say, longer than that obtained in metallic palladium, and which is, I think, one of the most important proof of evidence for the formation of the dipallada compound. Also, from this method, we could deduce also the coordination numbers associated to these bonds, and they were extremely close to the number of 3 and 1. It does mean that the palladium atom is in a sort of 3-coordinate environment. May I have the next slide, please? And you see here some theoretical model, which suppose that the dipallada unit is inserted in between the phosphorine layers, 2 phosphorine layers, forming a sort of palladium-palladium unit, which is eta3 coordinated to the phosphorus atom of 2 different layers, eta2, eta1, and then is additionally supported by an intrametallic palladium-palladium bonds. Okay, also I should say that there exist many, let's say, sort of crystal state isomers, let's say, that change their energy in a very narrow range, in a sort of a swallow surface of energy, and that is responsible, if I have the next slide, just this was a sort of indirect demonstration that palladium is not exposed on the surface. You know that palladium systems in the oxidation state 0 are almost completely active, easily active in the hydrogenation reaction, of particular of unsaturated carbon-carbon bonds. We did a lot of experiment with carbon-carbon double bonds molecules and carbon-carbon triple bonds, and we obtained, in any case, in this case, absolutely no conversion to the hydrogenated compounds, thus indicating that the palladium atoms are probably buried inside the layers of phosphorine, and they're inaccessible to the organic fragments. By contrast, it was possible to get a hydrogen evolution reaction, and you see here some interesting results, which have been then published in our paper. And the system does work in the proper way, and in particular, the activity of the palladium complex is largely higher than that of the pristine 2D materials, that is, the materials without any metallic precursor. May I have the next one? Okay, this is the result. These are the results of the NMR spectroscopy. We did a lot of NMR tests, not only with the carbon-13 labeled organometallic precursor, which brought us to exclude the presence of any carbon compounds, but we also try to study the phosphorus NMR spectrum using the solid-state methods, which were which are used by our colleagues in CNR in Pisa and at the University of Pisa. Marco Geppi, Lucia Calucci, and Silvia Borzacchi did a lot of work in this sense, and you see here some of their results. In particular, when we worked with high loading of palladium, about 6%, the sample with the maximum loading of palladium, about 6%, we observed the signal of the black phosphor, of the exfoliated black phosphor, but together with him we observed a sort of bumps at the base of the system that were almost absent in the low loading compounds, that can be ascribed to the interaction of some phosphorus atoms of our functionalized phosphorine with palladium. Indeed, palladium has one NMR nuclei, which is NMR active, is the palladium 100, help me, palladium 105, which is 22% of natural abundance, and there's a quadrupolar nuclei. Is a quadrupolar nuclei with a momentum of 5 and 5.5. And this could be emphasized only by putting very high recycle delay, which emphasize the fast relaxing system. Indeed, the closer connection of the phosphorus atoms with the palladium quadrupolar nucleus should cause a very fast relaxation phenomena, and then this kind of let's say subtle changes in the spectrum could be observed only by recycling at a very high speed of the signal. And this was a very interesting result also, in my opinion, because it demonstrates that some of the phosphorus atoms are indeed interacting closely with palladium, and the ratio of the signal was in line with the supposed coverage of the surface and in line with the isotopic percentage of palladium 105. May I have the next one? Okay, this is the conclusions of the first part of my talk. I would like to ask Stefan how much time I still have.
Time is up, unfortunately, Maurizio.
So I just make.
If you come to conclusions, yes.
So the conclusion is that we have demonstrated that it is possible to functionalize black phosphorus exfoliated. Not only the reaction goes in the proper direction that we expected, but it doesn't mean that the actual result of the reaction is less interesting. And indeed, we were not capable of confirming the formation of organometallic precursor stabilized on the exfoliated system, but we obtained a very strong indication that the palladium decoration of the exfoliated black phosphorus has been obtained. A lot of characterization methods were used, and we applied also the system in the hydrogen evolution reaction. I would like just to skip the next slide and go to the one in which please, let's go, until I don't stop. There are so many slides. This is some other dealing with the catalysis as well. Let's go. Okay, let's go. Okay, and I would like just to stop to this slide because it's extremely important. Is the slide which was collected in Florence, a picture that was taken in Florence 2 years ago, if I'm right, if I remember. There is also Stefan just in a privileged position atop of the slide. And there are all the people that worked with me and Stefan in the project Phosphane that was funded in 2015 and ended in 2019. And I thank all of them for their important and extraordinary achievements in this collaboration. May I have the next one, please? Okay, so these are the other collaborations that we developed along the project Phosphane. All of them have been extremely important. Some of them have been absolutely extraordinarily important, because otherwise we will not be able to do what we have done in this year. The next one, please. Okay, just some publicity about the conference that should have been done in 2020. It's an invitation to everybody of you to CAMS. May I have the next, please? And you see that see you in Rimini 2020, the next one, but COVID has caused the shift of this conference in 2021 and then the reprogramming of the conference 2022. We are pretty sure that in 1 year more we will be all capable of doing this conference, which is a huge conference generally, in the presence. There is plenty of time for registering, and there is plenty of time to see what this conference is promising. There is a lot of material chemistry as well. May I have the next? Okay, just another view of the conference. This is the this is the 2022. And again, and last but not least, please the next one. Okay, this is my thanks to all of you for your kind attention. I'm sorry for having been a little bit longer, and thank you so much to the Andrea, to Antonio Politano and his colleagues for their kind invitation to be here in virtual L'Aquila. Thank you.
Yeah, thank you very much, Maurizio. There's time for one question. We have someone is raising.
I have a question. I have a question, if I can, Stefan.
Yes, please.
Yes.
Hi, Maurizio. Thank you for your last talk.
Ciao.
With you. So I'm wondering if you may comment on the stability of the phosphorin layer, especially when you reduce the thickness to the single layer, because I know that black phosphorus is somehow affected by oxidation, lateral oxidation, so on. And how can functionalization prevent from a degradation of the layer?
Yes, that's a good question indeed. And I would like just to stress indeed that the oxidation of exfoliated elemental phosphorus is let's say the bottleneck of all this chemistry, and I think is the bottleneck of the application of this beautiful compound in any physical device. And of course, let's say in principle it's very difficult to get the single monolayer exfoliation, and generally we work with flakes that have a thickness of few layers, depending from the way by which we prepare the compounds, and particularly the way by which we separate the single thickness aggregates. We have generally the possibility to get few layers black phosphorus, exfoliated black phosphorus, but I think that we are not in the position to have a single layer of phosphorus atoms by the liquid exfoliation methods.
Okay.
That could be obtained, of course, via different techniques, let's say vapor deposition or others. But with the liquid exfoliation, that we don't get really the single layer. We get a mixture of few layers phosphorin, which for our purpose and they are absolutely useful. Anyway, once it has been, let's say, chemically modified, either by, let's say, using nanoparticles or extended Pyric system or others, anyway, the stability of black phosphorus becomes higher. And so, in principle, it is possible to get interesting application either in catalysis and in, let's say, physical device. I don't know if this clarify your question.
Absolutely, yes. So you mean that functionalization is the good solution to prevent degradation of phosphorine, and this could be actually a good point for even for the monolayer too. Even if you said that monolayer is quite difficult to get.
A lot of papers that describes interesting way by which functionalization or even just, let's say, doping of the system with other ions, other metals, other compounds are capable of getting products which are much more stable than the pristine exfoliated black phosphorus.
Thank you.
Grazie, Alessandro.
Yeah. Thank you, Maurizio, for this very nice talk. And so we have to move on. And so the next talk is invited, given by Plinio Innocenzi from the University of Sassari. This will be a video talk, if I understand correctly. And the title of this talk is Boron Nitride from 0D to 2D Advanced Materials. So can we start?
Morning. It's a great pleasure for me to have the opportunity to talk in this conference. Let me give a special thanks to all the organizers, Professor Carlo Cantalini and Professor Politano. And the subject of my talk today is boron nitrate, from 0D to 2D advanced materials. In the last years, there was a booming research in the field of 2D materials, and especially what we have learned that 2D material is just a starting point to obtain a completely new family of advanced materials which are zero-dimensional. In particular, from graphene, we know that we can obtain graphene quantum dots and then all the larger family of carbon dots. Another example is hexagonal boron nitrate, from where we can obtain via bottom-up or top-down synthesis hexagonal boron nitrate dots. Boron nitrate, in particular, has attracted so much attention because of the peculiar properties, such as the wide band gap between all the 2D materials. Is the material which has showing the largest band gap, which is nearly 6 electron volt, and a lot of specific and peculiar properties, especially in optical active defects, which have attracted a lot of attention for developing photonic optoelectronic application. Other important properties is the high thermal conductivity, the low dielectric constant, and the excellent mechanical stability. So these make 2D materials a competitor, a direct competitor of graphene, so that is called the white graphene. At the same time, from 2D materials of boron nitrate, as just said, we can obtain 0D materials, so the boron nitrate dots. Boron nitrate dots can be synthesized using top-down or bottom-up route. An example is a hydrothermal route. It's a simple synthesis by reaction of boric acid and ammonia. Through this reaction, it's possible to obtain boron nitrate dots with extremely controlled dimension. However, one point that must be stressed is that when we talk about boron nitrate dots, generally they are never pure boron nitrate, never pure boron nitrate composition, but they are formed by they have oxygen or they have carbon. So in this case, we talk about bonds specifically because are boron oxynitrate dots. As you can see from this scheme, they are characterized by defects, particularly boroxyl rings which are open, and BOH groups, NH groups. At the border, we have these defects. And these defects play a very fundamental role to tailor the properties, the optical properties of the boron nitrate dots. The synthesis allows to obtain boron oxynitrate dots with an average dimension of 10 nanometers, shown by TM images and dynamic light scattering analysis. This particle is characterized by an amorphous structure, and only a small amount of crystalline domains is observed by X-ray deflection. One of the main properties of boron oxynitrate dots is that their properties are dependent on the presence of defects. In particular, defects control the optical properties such as the emission. If we observe the UV visible absorption spectra, they are characterized by two absorption shorter wavelengths due to the boron nitrate structure, and other two absorption at higher wavelengths around 320 and 415 nanometers, which are assigned to defects. In particular, these absorptions are correlated with the two specific emissions that we observe in the boron nitrate dots. One at 400, peaking at 400, another one peaking around 470 nanometers. One important property is that the intensity of this emission decreases with the temperature of thermal treatment during the synthesis. So, as prepared samples are more emitted, more efficient than samples treated at a higher temperature. This means that the thermal treatment is affecting the defects. If we observe the excitation emission intensity spectra map, clearly we observe the presence of two emissions which are correlated with excitation at 412 and 308 nanometers. So this is a two-color emission of from the boron nitride dots. The fluorescence maps show that emission centers do not shift with the thermal treatment while decrease in intensity and overlap. The change in intensity of the absorption and emission bands, which peak around 308 and 300 nanometers, are correlated and depends on the temperature of the thermal treatment. So when with the increase of the thermal treatment temperature, there is also a decrease in intensity of the absorption and emission bands. This is because there is a reduction of the effects due to the condensation of BOH species, for instance, which form B or B bonds, which are not emissive as the BOH species in the boroxide nitrate dot. The boron oxynitrate dots are water soluble, and this allows using in the synthesis, sol-gel synthesis of hybrid films. Hybrid films prepared via hydrolysis of methyl tetroxysilane and tetroxysilane. At the end, we have a film with controlled two colors emission. The boron oxynitride dots have shown two colors fluorescence with two excitation, which excite two different emission bands, and can be used for producing fluorescence films via sol-gel. Let's see another example of engineering the UV emission defects in boron nitride nanodots, which are prepared at this time from a top-down route, so starting from a bulk powder. A combination in ultrasonic and thermal treatment in phosphoric acid has been used to achieve edge etching and size reduction to the nanoscale. The dots have dimension with average dimension smaller than 10 nanometers. This scheme shows the main processes behind the top-down synthesis of boron nitride dots, starting from bulk boron nitride, hexagonal boron nitride, which is sonicated for 10 minutes at the beginning in phosphoric acid, then heated at 200 degrees for 1 hour, then more phosphoric acid is added and sonicated for 50 minutes, and then the final process of purification with centrifugation and dialysis to obtain the final products, which are dots with the average dimension smaller than 10 nanometers. The 3D fluorescence map shows a typical emission in the blue, which is generated by defects, typically hydroxyls, as we have seen in the previous example. But very interesting, there is a specific emission in the UV, which we observed only in the samples which have been prepared by heating and sonication in acid, while not observed in the boron nitride powders, which are only been subjected to either treatment or sonication. So this is a specific emission in the UV, which is very interesting. The FTIR spectra are characterized by a very peculiar properties, and if you observe the characteristic in plane boron nitride stretching vibration, which is peaking at 1372 wave number, this band appears resulting from a convolution of two overlapping bands, an almost temperature-independent mode, 1372, and a second band at around 1383. The latter one is monotonically decreasing with the temperature and disappears around 250 degrees. The spectral difference between the S-prepared boron nitrate dots and the 250 thermally treated dots shows the presence of a sharp mode with a maximum of 1385. This vibration is correlated to the UV emission at 320 nanometer, and this shows that the annealing promotes a decrease of both high-energy fluorescent and infrared absorption. This allows to make a direct correspondence between these distinct boron nitrate dots' physical properties. We have supposed that this UV emission, is correlated with the type of stone wall defect, which is a defect, crystallographic defect, that involves the change in the conductivity of two pi-bonded close atoms with a rotation by 90 degrees with respect to the midpoint of their bond. In the figure, you can see the results of quantum chemistry calculation, a computational UV absorption of pristine and defective cluster, and representation of the infrared spectra, including the cluster with stone wall defects, and the quantum mechanical calculation will simulate the infrared spectra, as we have seen, which are characterized by a sharp band of boron nitrate stretching, which overlaps to boron nitrate stretching normal band. So we are pretty sure that the UV emission is due to stone wall defects. Defects are also at the origin of luminescence in hexagonal boron nitrate nanosheets, so in 2D materials. In this sense, 0D and 2D materials are similar because in both cases, boron nitrate materials show a dependence of the optical properties from defects. So somehow it's possible tailoring the defects of these materials. In this case, we have synthesized boron nitrate 2D sheets via sonication assisted in liquid by exfoliation. Then we have submitted these samples to oxidation in air. Increasing the temperature, we observed a change in the absorption spectra with the rise of a band, and also a strong change in the infrared spectra. In particular, the infrared spectra show with the temperature there is a condensation of the structure via reaction of the boron oxynitride bonds and formation of boron oxygen boron bonds. So there is a densification of the structure, and this is associated with a change in the photoluminescence. It's very interesting to observe that in general bulk boron nitrate, hexagonal boron nitrate, is not fluorescent. Also, in general, the boron nitrate sheets, which are prepared in a proper way, are defect-free. But in this case, we have sonicated in water with a specific purpose to induce the formation of defects. And in fact, it's possible to observe a fluorescence which has the maximum intensity at 300 degrees of thermal treatment. At higher temperature, the defect disappears due to the condensation of the boron oxygen hydrogen bonds. The experimental results have shown that the luminescence in the visible range depends on the nature of the defects which originate during the synthesis. Theoretical calculation have also supported the results, and the UV absorption spectra of boron nitrate cluster model with structural defects, which are nitrogen and boron vacancies and oxygen impurities, have been computationally derived. Charged oxygen defects are the most promising candidates for the interpretation of the optical properties of the defective boron nitrate sheets, introducing intragap transition in absorption that effectively reproduce the experimental spectra. So again, it's possible to introduce and to design somehow to tailor the defects as a function of the optical of the design of the optical property. This is true for 0D and also for 2D boron nitride materials. Thank you so much for your attention. This is a greeting from our lab, which is in Porto Conte Ricerche. This is the view from our lab, and a special acknowledgement to all the people that worked with me in the field of boron nitride optical materials.
Okay, yeah, so thank you to Plinio, who has communicated that unfortunately he could not be present today, so there is no point in asking questions, and so we can right away move on to the next talk, which is also an invited talk and will be given by Enrico della Gaspera from RMIT Australia, and the title is Solution Processed Semiconductor Nanostructures for Optoelectronics. Please.
Good morning, everyone. First of all, I'd like to thank the organizers for inviting me today. My name is Enrico, and today I'm going to talk about my work on solution-processed semiconductor nanostructures for optoelectronics. So, a couple of words about my lab. My lab is set up at RMIT University in Melbourne. We do a lot of work on solution-based approaches to nanomaterials. So we work on colloidal nanocrystal synthesis, on the preparation of molecular precursors, and on the direct fabrication of nanostructure films. We play a lot with surface chemistry through ligand exchange, phase transfer, and ink formulations. And the overall aim of my group is to make thin film devices, such as transparent electrodes, solar cells, LEDs, and photocatalysts. So here are some details and links about my group for those of you who are interested. So when we talk about solution processing of nanostructures, there are mainly two ways to make nanostructures and nanomaterials from solution. So the first one is to start with colloidal nanocrystal building blocks. So you make nanocrystals in solution with colloidal techniques, and then you purify them, resuspend them into an ink. They look like something like this. And you can use this for thin film fabrication as particles dispersed in solution or as nanopowders. So it's a very powerful technique. However, it's reasonably complex because you need to be able to control size, shape, and composition of your nanocrystals. The other approach is the direct growth of thin films straight on the substrate. The simplest example is the sol gel technique. You start from precursors, and then you basically decompose them into your target material via, for example, thermal annealing. This is a much simpler approach. It has the possibility to prepare potentially endless materials compositions. However, it's difficult to precisely control the parameters and the functional properties of your coatings. So, pros and cons of both, but why do we care about solution processing? Well, if you compare solution processing with vacuum-based deposition of nanomaterials, and here there's a couple of pictures that exemplify what I'm trying to say. Liquid-based or solution processing, liquid-based depositions are simpler, faster, less expensive. They can be adapted to fast roll-to-roll production. So there's a lot of advantages, but this is true provided that the quality and the performance of what we're making are maintained. As a matter of fact, vacuum-based deposition provide materials with the highest quality and performance. So the key goal here is try to make these solution-based nanomaterials as performing as the vacuum-based counterparts. So let's start with some of my work on colloidal nanocrystals. So over the years, I developed different recipes to make doped nanocrystals through colloidal techniques, and one of my main focus was zinc oxide. So zinc oxide is well-known material and is one of the most promising materials that can replace some of the key components in optoelectronic devices, especially the transparent electrodes. So these transparent electrodes are usually made out of indium oxide, which is expensive and rare. So can we use something as cheap as zinc oxide, and also some liquid-based deposition with controlled doping? So as I mentioned, over the years I developed different recipes based on hot injection or straight heat up, and eventually something called slow growth for making pure zinc oxide nanocrystals and doped with both trivalent and tetravalent cations. So aluminum, gallium, and indium, but also germanium and silicon. So all of these dopants go substitutionally to zinc into the zinc oxide lattice, and this creates an excess of free electrons that can provide interesting optical and electrical properties. And if you look at the optical properties, you see here how these all these nanocrystals are transparent in the visible range. They have a sharp UV onset of absorption due to the zinc oxide band gap, and then they show some various absorption in the near infrared, but also in the mid infrared. And these are due to surface plasma resonances, which are basically oscillations of free electron, the same nature of what happens in gold and silver nanoparticles, with the difference that these are semiconductors. And these resonances are due to these dopants that we incorporated. With these different reactions, we can make grams of nanoparticles. We can control easily their size and relative dispersity. And also, we can see how these particles are highly crystalline and of very good quality. So now that we have these nanoparticles, what can we do with them? So the first application is transparent electrode and smart windows. So, for example, if we think about smart windows, or look at the transmittance of these coatings on glass, you can see how these have full UV blocking capability. So they prevent harmful UV radiation to enter the building if we use them as smart windows. There is full transparency in the visible range, meaning that you can easily see through the window. But also you have this tunable infrared absorption, which means that the heat cannot escape the building in wintertime or cannot enter the building in summertime. And this is something that's very useful for energy saving windows. On the other hand, we can look at their electrical properties, and this presence of these free electrons gives very improved conductivity, orders of magnitude more conductive than a doped zinc oxide. And when this initial study was published in 2013, this was the had the record of conductivity for a nanocrystal-based transparent electrode. The other thing that we can do is to look at plasmonic gas sensors. So traditionally, optical gas sensors based on plasmonic nanoparticles involve a metal oxide matrix, which is responsible for the interaction with the gas, and plasmonic nanoparticles, such as gold and silver, that can sense this variation through the variation of their plasmonic resonance. In this case, we have a material which is a semiconductor, zinc oxide, but also has a plasma resonance. So we have a single material that has both attributes, and the difference is that this plasma resonance lies in the near infrared and not in the visible anymore. So through a study that was conducted in collaboration with my former PhD supervisor, which is also part of this conference, Professor Alessandro Martucci, we demonstrated that this surface plasma resonance can indeed be used to detect both reducing and oxidizing gases optically through a single material, which is also responsible for the interaction with the gas. So besides zinc oxide, recently my group has moved towards other oxide nanocrystals. So one of them is tin oxide doped with fluorine. So fluorine doped tin oxide, or FDO, is another industry standard for transparent electrodes. And there are basically no recipes for making nanocrystals of tin oxide. So We developed a recipe to make very small nanocrystals, less than 5 nanometers. You can see them here, very small but still crystalline. And we can demonstrate the presence of this surface plasma resonance due to the fluorine doping. Same effect as we saw in zinc oxide, as you can see here. It's tunable and centered in the near infrared range. And also we demonstrated very strong blue luminescence due to defects within the bandgap. So this could potentially be used as transparent electrodes, but also for blue LEDs, for example. Another material that we recently started to investigate is a ternary oxide perovskite structure called barium stenate. So barium stenate as a material has the highest predicted electron mobility for a material with a bandgap above 3 electron volts, which means it's extremely important and promising as a transparent electron material. So we developed a recipe to make barium stenate pure and doped with lanthanum in various concentrations, and we also demonstrated that we can highly tune the ratio between the two, tin and barium, to the stoichiometry that we want very precisely. And again, these nanocrystals show a tunable IR absorption due to the presence of this lanthanum doping. Not just oxides, we did some work on sulfide nanocrystals. This is an example of zinc sulfide doped with indium. And here the key was to develop UV photodetectors. So zinc sulfide is a well-known wide bandgap semiconductor with a bandgap in the UV. And through the control of their size, through quantum confinement effect, and alloying with indium, we're able to precisely control the bandgap between the range of UVA and UVB. So basically, we develop photodetectors that are blind to UVA radiation, but are very sensitive to UVB and UVC, so the higher energy component most harmful. And you can see here there is no signal when the photodetector is exposed to low energy UV radiation, the red curve, and a reversible signal for higher energy UV. So this sums up some of the key results on the colloidal nanocrystal space. I want to spend the last few minutes talking about the direct growth of nanostructured thin films. So over the years, I developed this interest in trying to mimic the morphology and properties of sputters, so vacuum deposited coatings using solution-based methods. So with nanocrystals, your film will be still composed of tiny nanocrystals mixed together. How can we get some large grain growth, very dense films, similar to what you obtain with sputtering? So first I tried to explore a technique called chemical bath depositions, in which you grow a film directly on a substrate by dipping it into a growth solution and playing with the chemistry and the parameters of your solution in terms of temperature, presence of additives and ligands and so forth. And you can control the way that these crystals grow on the substrate. So in the first study, I developed a method to grow intrinsic zinc oxide, so undoped, that was used as a buffer layer in a type of solution process solar cells, which is represented here. And as you can see, the performance obtained for devices with a sputtered zinc oxide or a zinc oxide layer done by chemical bath deposition are identical. So this is a validation that we can mimic the performance and the properties of vacuum-based coatings using this chemical bath deposition. However, as usual, the holy grail was to make transparent electrodes. So we did another study in which we explore a different type of bath. We use a combinatorial approach to screen ligands and additives and temperatures and so forth. And at the end of the process, we were able to obtain highly transparent zinc oxide coatings that were also extremely conductive. The temperature of the deposition was only 80 degrees, so we could do it on plastic and flexible substrates. And we validated this by using this as transparent electrodes for yellow LEDs. As you can see here, the performance is identical between our zinc oxide and commercial ITO, indium tin oxide coatings. Finally, I want to show some recent results on a process called ultrasonic spray pyrolysis. This is a spray deposition similar to an airbrush spray, but is done through an ultrasonic nozzle that provides very fine droplets, and the spray mist is deposited straight onto a hot substrate. So the precursor can be fully decomposed into our target material. So we started working on a variety of materials, but I'm going to present some work on tin oxide. And as you can see, we can make high quality tin oxide coatings doped with various elements, including antimony and fluorine. These are fully transparent in the visible range. You can see it here. They have a strong IR absorption due to the surface plasma resonance I mentioned earlier. And they have extremely high conductivity. We're talking about a few ohm square. We can routinely make coatings with 10, 20 ohm square surface conductivity, which is what is needed for devices such as solar cells. More importantly, these coatings have a positive coefficient of conductivity, which means that their behavior is basically metallic. Okay, so I hope I've showed that we can use wet chemistry to make nanomaterials with extremely controlled properties and improved functionalities. I've shown some results on colloidal nanocrystals and doping, and also some direct growth of thin films on substrates. And last, I would like to thank my group and collaborators, the funding agencies through my university, the Australian government, and thank you all for your attention. I'll be happy to take any questions.
Yeah, Enrico, thank you very much for the very interesting talk. There's time for questions.
Yes, I have a question. May I?
Yeah, sure, go ahead.
Yes, thank you for this very nice talk. I was wondering about these zinc sulfide nanocrystals that you show. I could see from the TM images some defects, some twins. So I was wondering how is the crystal quality of this nanocrystal, and how the crystal quality affect the emission wavelength, and so the optical properties.
Okay, so thanks for the question. These nanocrystals are fairly small. They're only 2 to 3 nanometers. So they're highly defective, and the proof of that is they're strongly luminescent in the blue region, despite having a band gap around 4 electron volts. So all the luminescence comes not from band edge recombination, but just straight from defect. So long story short, they're highly defective. I can't comment much on twinning of these. We didn't do super high resolution TEM. So from what we could see, I could see every particle as a single crystal, but I can't exclude twinning defects in these. Regarding the crystal structure, there's an indication from Raman and XRD that they are cubic and not wurtzite, but the broadening of the peak is such that it's difficult to distinguish between the two. I don't know if that answers your question.
Yes, thank you very much.
Other questions?
Sure.
Yes, please. Go. No more. So then let me, just a curiosity, on one of your slides you had a mate who was painting his house. Do you see this as a possible application for the quantum dots, or was this just to visualize spray coating?
Let's call it a 50-50. Let's say I would like it to be, and there are people that are working on something that's called solar paint here in Australia. So they developed some organic nanoparticles based on bulk heterojunction solar cells, and they made them into a paint, and they actually painted the roof of their house with this as a demonstration that it could work. Industrial and commercial applications were many years away. So in a long term, yes, we're not there yet, not even close.
Okay, yeah, then thank you very much for this very interesting presentation. And we move on to, and we move on to the next talk, which is an invite given by Ivana Gobornik from CNR IOM in Trieste. And she will talk about direct insight into the electronic band structure and spin properties of novel topological materials. Okay.
Hello, everybody. I'm Ivana Gobornik. I'm a research scientist within the National Research Council of Italy, and I work at the Istituto Officina dei Materiali, which is located in Trieste, in this beautiful environment, and also in close vicinity to Elettra. In fact, IOM is operating a number of beam mines of Elettra, among which also the APE beam mine. For non-Italians, this kind of vehicle is called APE. And APE is operating as a facility within both NFFA Trieste and Elettra facilities. You can see the title of my talk. Evidently, I will be speaking about the electronic and spin properties of novel topological materials. So let me start. The outline of my talk is here. I will briefly address the topological properties of materials that are typically two-dimensional materials with strong spin-orbit interaction that results in spin momentum blocking. And these materials happen to host also the relativistic quasi-particles such as Dirac, Weil, Majorana, and so on fermions. In fact, Condon's matter became a useful playground now for high-energy physics. There are a number of materials of this kind that we studied in recent years. Of course, I will not be able to address all of them in this talk. I will pay particular attention to transition metal chalcogenides, namely in this case, nickel ditelluride and platinum-3 tellurium-4. And I will also try to illustrate how the facilities that are available within NFFA Trieste with a number of complementary techniques for the sample growth and sample characterization allow to pursue this work. The collaborators involved in this quite vast investigation are distributed worldwide. There are two CNR institutes involved, also University of L'Aquila with Antonio Politano, who is in fact one of the main collaborators in the work that I will be presenting, University of Princeton, University of Taiwan, Indian Institute of Technology, Chinese Academy of Science, University of St. Andrews. For the materials I will be presenting today, the main actors are within CNR IOM, University of L'Aquila, and Indian Institute of Technology. So let's briefly introduce topological materials. Probably you already know this. They are, as I said, initially two-dimensional materials with strong spin-orbit interaction that result in spin-polarized states. So let's take a classical case of two-dimensional material, such as surface state of a metal. Free electron state in a metal has a parabolic dispersion, and in fact, you may observe this free electron parabola that in the case of heavy metals such as gold may be subject to splitting due to spin-orbit interaction. This is Rashba splitting, and the two the two split parabolas are in fact spin polarized with opposite polarization. Now, in a topological insulators, very naively you may imagine that spin-orbit interaction is so strong that the parabolas are further apart, and what we have then in the center of parabola is this kind of Dirac cone dispersion with two ends of the cone with opposite spin polarization. The technique that allow us to map the electronic states of materials is the spin and angle result photoemission. All these quantities are conserved in one way or the other in the photoemission process. And here are the spin ARPES maps, or let's say just ARPES maps of called 111 surface states. This is not spin result, so evidently there are two parabolas, and if you do it in spin resolved mode, you can observe that one is red and one is blue, which tells us that they have opposite polarization. And similar case is also the topological Dirac cone in bismuth selenite that was in fact grown in our own laboratory in Trieste. This is the cone, and these are the spin resolved data showing the opposite polarization of the two ends of the cone. Okay, let's move to the next. Of course, the situation can be significantly more complicated. I presented quite naive picture. A number of other relativistic particles can appear other than Dirac, so there can be Weil or Majorana Fermions. There can be all new classification of materials such as Dirac semimetals, Weil semimetals of type 1 and type 2 and so on. Fortunately, in this talk, I will be sticking to Dirac quasi-particles, fortunately for you and for me. And so at this point, we will not be discussing this kind of things further. Just very briefly, our experimental setup. I said that I'm working at upper beamline, but in fact it's two beamlines. These are two complementary beamlines regarding the energy range that they cover, but also that the experimental techniques that they offer. So there are indeed a number of powerful spectroscopy techniques available on the two, but what is particularly important and concentrated in this zone is the fact that the two spectrometers where we do spectroscopy using the photons from Elettra are connected with a set of UHV chambers where we can introduce and prepare our samples. We can also grow our own samples. We can characterize them with offline techniques by, for instance, magnetoptical K-effect, Lidogé, or more importantly, scanning tunneling microscopy. And then the same sample, as you can see, can travel in any of these environments and be characterized then by any of the available spectroscopies. And this is in fact the core of our NFFA laboratory. For my pride, I say that also we developed and introduced what we call VESPA, so just to be in tune with Apple, there is also VESPA. VESPA is very efficient spin polarization analysis based on Willits scattering, so I will not have time to spend on that, but this is one of a very few setups worldwide which in fact is hosted at UP, and we are having users from all over the world, even in these COVID times, making experiments at our laboratory. Let's move to transition metal dechalcogenides. Those are layered materials with strong interlayer covalent bonding and weak van der Waals type interlayer coupling. As just the name says, they are formed by transition metals and chalcogenide atoms, and they can cover a wide range of ground states, starting from semi-metals, metals, semiconductors, and superconductors as well. And their properties are often conditioned also by the number of layers in the system, so also the third dimension matters. In many of them, spin-orbit interaction is strong and in fact plays quite important role. So I will not be discussing all what you are seeing here, but this is just to say that in many of those materials host spin-polarized electrons, which renders them then also candidate spintronic materials. Now, given to the fact that they are two-dimensional and materials and can be exfoliated similar to graphene, they were also proposed as the building blocks for the materials by design concept. But in order to implement them in real devices, the crucial step is understanding of their electronic and spin properties. And this is exactly what we are doing. Further on, I will be concentrating on group 10 chalcogenides. The motivation was that in this kind of systems, in particular in platinum palladium based, type 2 Dirac fermions were spotted. So what are the type 2 Dirac fermions? So in a simple, let's say simple Dirac cone, such as the one of graphene or topological insulator, the energy axis is the axis of the cone itself. For the type 2 fermions, for the type 2 Dirac cones, the cone is tilted, and therefore the Fermi energy cut in this kind of configuration may result of in two open electron and hole pockets, and this can result in peculiar phenomena such as magnetoresistive effect, in which the material conducts electricity only for a certain alignment of the electric and magnetic fields. Unfortunately, in both of the two materials that this kind of behavior was first observed, or type 2 Dirac cone was first observed, Dirac point was quite far from the Fermi energy, deep in the occupied states. So therefore, it was only of academic interest rather than of any kind of technological interest. Typically, in topological systems, the heavier is the better. So probably for that reason, a nickel counterpart was neglected, although also he belongs to group 10 materials. But in 2018, it was found that, in fact, in nickel ditelluride, this three-dimensional Dirac point is approaching the Fermi energy. So this was our motivation to do the band structure investigation. But there is one more extra motivation came again from the palladium and platinum counterpart. Namely, it was found that this particular interplay between trigonal crystal field splitting and spin orbit coupling, together with bonding and antibody splitting, results in a number of band crossings and inverted band gaps that, besides the bulk Dirac point, host also a number of topological surface states. In fact, they are in calculations very beautiful. So they ended up also in the title page of Nature Materials, but let's say also the experimental data are really beautiful for this kind of materials. There are a number of bands, most of them are the surface states, and I will be also mainly focusing in fact on those also for nickel ditelluride. So as I said earlier, nickel ditelluride is a layered material, similar to our other chalcogenides. This is the structure of the bulk in more detail. This is the surface structure, the bulk brilliant zone, and the surface brilliant zone. On the right, we have the measured energy dispersion along the gamma K and gamma M high symmetry directions of the brilliant zone. And all these arrows are pointing to some kind of surface states. In fact, some of those you can already see that you have some kind of Dirac-like crossing, so you can imagine that they are topological surface states. For the rest, you will have to trust me that they are. But as I said initially, we were in the search of bulk Dirac cone, which is expected along the gamma A direction, so the direction which is perpendicular to the surface. And in order to extract the KZ dispersion, we have to do photon energy dependent study. So these are the photon energy dependent scans. Once you do the photon energy dependent scans, typically the features which are not moving by photon energy are the surface states. So in fact, they are evidenced here. While the others that disperse are the bulk states, such as this one, which disperse downwards, but also the one that disperses upwards. And in fact, this state is the one that composes the three-dimensional Dirac cone, for which we find that indeed it is in the proximity of the Fermi energy, but with a Dirac point slightly above 20 milli-electron volt, which is still something that probably with some kind of doping could be brought to the Fermi energy. Regarding the spin polarization, yes, I told you earlier that we have topological surface state, but the smoking gun for the topological surface states is indeed the spin polarization. And as you can see here, these are the ARPES data and spin ARPES data on top. Even despite our very efficient spin detector, spin measurements are quite time consuming. So we have not mapped all surface states that we have in the material, but just some of them, like this one, that makes this kind of evident direct light crossing, and also the pockets that are close to the Fermi energy along gamma m direction. And there is evident spin polarization with typical inversion across gamma, which is the signature of the topological character of these states. Now, my colleagues and collaborators, which have more practical sense, realized that this spin polarized surface state can be exploited. In fact, they have realized that nickel ditelluride is very nicely behaving material in high frequency rectifiers, and they explained this success of the material exactly by these surface states, that spin polarized surface states that we observed. So I'm not quite fond of applications. I'm more on the backstage of that. So I will now leave nickel ditelluride and move quickly to platinum 3 tellurium 4, but not, this is just work in progress. So I don't want now to enter deeply into physics of the systems, but that just address more the capability of our NFFA facility. So platinum 3 tellurium 4 obviously is not dichalcogenide, but it's quite similar because it's composed of layers of platinum tellurium 2 and platinum 2 tellurium 2. Which results to be inequivalent on their surfaces, and the chemistry of the two is quite different, that we also realize in our platinum 4F spectra. We could also observe the steraces of the two different characters and characterize them electronically already by scanning tunneling spectroscopy. So there are evident differences, among which maybe the most prominent is this peak in the density of states on the platinum tellurium 2 termination. And further, we characterized those also by the ARPES and spin ARPES, and indeed found that they are quite different also regarding the electronic band structure. There are significantly many more bands in the case of platinum tellurium 2 termination rather than platinum 2 tellurium 2. But all these terminations host again spin polarized states, and some of them also in the close vicinity to the Fermi energy, which also renders this system a useful candidate system for potential spintronic applications, for instance. So with this, I conclude. I hope that I illustrated to some extent to you the electronic and spin properties of these two materials. That in one case host bulk Dirac point and spin polarized surface states, and due to that are candidate spintronic materials. And hopefully with this very last part of the talk, I showed you how a number of complementary tools that are available within the NFFA facility can be implemented on the road towards materials by design concept. With this, I would like to thank you for your attention. Thank you.
Yeah, Ivana, thank you very much for the presentation. There's time for questions. Okay. Well, let me ask one. So in the last part on the platinum telluride, the STM showed that there are different domains, so platinum 1, tellurium 2, and platinum 2, tellurium 2. But then you performed ARPES on either of these domains. So do you have a lateral resolution, or are you able to grow single domain films just of one of these two phases? Oh. Ivana, are you still there? Ivana?
I think she has some technical issues.
Yeah, it seems we lost her. Well, at this point, I would probably suggest that we go on, and maybe afterwards there will be a possibility to talk to her. Okay, so then let's move to the next talk, which is given by also an invited talk by Davide Campi from Università Milano Bicocca. And he will talk about high throughput discovery and characterization of novel 2D and 1D materials. Please, Davide.
So good morning, everyone. Can you all see my screen?
Yes.
Perfect. So good morning, everyone. And first of all, a big thank you to the organizers for inviting me to this fantastic conference. My name is Davide Campi. Actually, I've recently moved to the University of Milano Bicocca as a researcher. But most of this study on the high throughput discovery and characterization of new two-dimensional, one-dimensional material has been done during my years in the group of Professor Nicola Marzari at EPFL. So we have seen how 2D materials can be really promising in a variety of applications, ranging from electronics to optoelectronics to energy storage and so on. And we have seen some great examples of that earlier in this morning. But until quite recently, the majority of the studies in this field have been focused only on a handful of two-dimensional materials, while there are possibly hundreds of them out there. And for those materials that we want to uncover and characterize in this study. So to find them, we start already a few years ago, looking at two large experimental structure databases, ICSD and COD, that combined accounts for more or less 500,000 entries. So, of course, after screening them for unicity, excluding structures with partial or unspecified occupation, or that were clearly wrong, or again, that were only theoretical, we ended up with something like 100,000 structures that we studied, at first using a very general geometrical algorithm that essentially finds layered materials. And it does that first by grouping chemically connected atoms using a sort of empirical definition of what a chemical bond is. So just based on the distance of the interatomic distance of the atom, exploiting this work, the statistical analysis done by Alvarez in 2013 that tells you that two atoms tend to form a real chemical bond if their distance is below this sum of the van der Waals radii minus this tunable parameter, this that is usually around 1.3 angstrom. Once we build that group of chemically connected atoms, we compute all the vectors connecting one atom to its periodic replica in a larger supercell, to its connected periodic replica in a larger supercell, and then we compute the rank of this matrix of vectors, and that tells us the dimensionality of this chemically connected subgroup. And this algorithm is very robust because it actually allows you to identify the layer structures even if the layered are not in a conventional, not along a conventional direction, or if they are compenetrated, or if you have intercalated molecules or atoms and so on. So using this first geometrical selection from the 100,000 structures that I've mentioned before, we ended up with more or less 5,000 layered structures, on which we wanted to compute the energy that keeps these layers together, what we call their binding energy. And to do that, we resorted to first principle calculations. And actually, we compared the energy of the bulk structure, fully relaxed with a proper non-local van der Waals functional, like van der Waals F2 or RBD10, with the sum of the each isolated substructures, using an approach that was pioneered in 2012 by Bjorkman, and of course having in mind something, a sort of a computational equivalent of an exfoliation, a mechanical exfoliation process of 2D materials. So on the basis of these binding energies that we computed in this way, we have been able to identify 1,825 monolayers in this paper in 2010. And actually, we decided to divide these 1,800 materials in two groups. So first one that we call easily exfoliable, and the one in light blue here in this picture, are materials that have binding energies comparable or even lower than materials that have been already synthesized experimentally, so it should be fairly easy to synthesize them. Instead, we defined as potentially exfoliables this material here in green, materials that have a binding energy that is higher than the highest binding energy of our really exfoliated materials, even up to 4 times higher. But that still, if you look at this graph here, it seems to belong to a different group with respect instead to the high binding energies here in orange. So we think that probably with a little bit of effort, could be possible to exfoliate also these materials, even if they show a larger binding energy with respect to the ones that we are usually use in experiments. So of course, this was 2018. It's been a while since then, but we didn't sit on our hands for these years. We find quite a few 2D materials in these studies, but we wanted more, so we want to find more. And to do that, recently we essentially have applied the same philosophies and the same techniques, just with a few tweaks here and there in the screening procedure. But what we did is actually ingesting much more data. So most notably, we added a third database to the screening. Is huge, is this NPDS or Pauling file that you can see here in this table on the right. But we also took the most up-to-date versions of the ICSD and COD databases, since we noticed that many structures have been actually added during this year, since our first study. And we also consider slightly larger structures than before. By doing that, at the end, you can see the number for each individual database, but at the end, combining them all together and filtering them for unicity, we ended up with something like 9,300 layered materials. Of course, some of them were already included in the previous screening, but many, so more than 3,600 were new. We computed the binding energies for these materials, and at the end, we ended up extracting another 1,252 new unique materials, unique two-dimensional materials that were not included in our previous study. So bringing the total number of possible exfoliable 2D materials that can be exfoliated for experimentally known compounds to roughly 377. So this number here, the 1,252, is even more interesting if we consider two things. So the first of all, if we consider the distribution of the binding energies in these two studies. So in this new set of materials, we actually have a larger percentage of materials that fell in the easily exfoliable category. So they should be the best one to work with experimentally. And actually we found 968 of them in this new study, effectively doubling the number of easily exfoliable materials in the total database. And the second interesting thing is that many of these new structures cannot be derived from already known structures, like doing just a chemical substitution, like tellurium instead of selenium or something like that. But they represent entirely new structural prototypes. So actually we more than doubled the number of structural prototypes in our database for a total of 1,124. That is a huge number of structural prototypes. Not only we did that, so we expanded the database and we computed these binding energies, but we also ran an extensive theoretical characterization of all these structures. So both the 1,825 coming from the previous studies and these new ones. And so our characterization included the properties like band structures, computed at two different levels of theory. So one is PBE, another one is the GLLB functional that gets the band gap a little bit closer to experiment than PBE. There is this known problem of underestimation of band gaps in density function theory. We computed density of states and projected density of states. Actually, the position of these band edges with respect to the vacuum, computing the functions, but also the some useful properties like the effective masses at each point that can be relevant for transports, and also the phonons at the gamma point, that gives you an idea of, for example, the Raman activities and so on, and the dielectric and so on. Of course, for semiconductor or insulating materials. For a smaller set of materials, so the one with less than 12 atoms per unit cell, that are still almost 1,300, we also computed the magnetic properties. So we searched for the magnetic ground state during a lot of possible combination of initial states, and also using supercell that allows for antiferromagnetic or ferroelectric structures. And we also computed the full phonon dispersion instead of just the phonons at the gamma point, from which we can, for example, infer about the dynamical stability of these two-dimensional materials that actually turned out the majority of them, luckily, to be dynamically stable. So with that, we actually built not only a database of structures, but also an associated database of properties that can be very useful to screen these materials for various applications. And so we leverage this database of structures and properties to do exactly that. So to run more focused, application-oriented screenings aimed at particular properties. Here I will not go deeply into the details of this work, but we put them there just if you're interested. We screened for topological insulators, but also for photocatalytic active materials, for materials that exhibit high mobility, or again materials that can be useful as channels in short channel field effect transistor, or even two-dimensional superconductors. Again, I will just mention this briefly because it's still kind of work in progress. But following essentially the same philosophy, just targeting a different dimensionality of materials, we also screened for one-dimensional materials. So in this case, covalently bonded chains that are connected with the rest of the bulk materials only by van der Waals interaction. So from, again, the total number of structures, putting some limits on the number of atoms and species that we screened, we found 9,109 of these atomic chains, and we decided, we put an hard cutoff on the number of atoms, and we decided to compute the binding energies for these one-dimensional structures. Only 1,805 of them less than 40 atoms per unit cell. Here, of course, the binding energy is expressed as an energy over a length instead of an energy over a surface. But make the long story short, we ended up finding 815 unique one-dimensional wires that can be extracted from these experimentally known wired materials, if you want, and more than half of them, 486, have binding energies that are lower than this antimony 2 selenium-3. It's a material that has been obtained experimentally, not really in a single wire format, in a quasi one-dimensional form. So here in this field of these one-dimensional wired materials, the experimental data are much more scarce than the materials, so we cannot really be definitive about which binding energy is likely break to inexfoliable materials and which one don't. We can just make reasonable assumptions. And again, for all these databases of 1D structures, we computed useful properties like electronic structures, edges, and effective masses, and phonon dispersion, and so on. The actual phonon dispersion is much more relevant because just a small fraction of these materials turned out to be dynamically stable, because of course they are you have all sort of instabilities in 1D, like Peierls instabilities for the metallic compounds and so on. So now, before concluding, I just want to mention that all these calculations that I've shown have been performed using a very powerful informatic infrastructure that is called AIDA, again developed in the group of Professor Mazzari at the PFL. And this software actually allows you for a very easy automation of the calculation, but not only. It keeps track of everything you do, so of the inputs of the calculation, of the outputs of the coding that you are using, to ensure the full reproducibility of your calculation, and stores everything in a nice database that then you can query. Also, all the data that have been produced during this work are available, or will be soon available through this website, the Materials Cloud web interface, that I invite you to visit, because you can find a lot of not only this data, but a lot of interesting things. So to conclude, we expanded our original work on the database, adding more than 1,252 new monolayers, but actually more than doubling the number of structural prototypes and almost doubling the number of easily exfoliable materials. It should be the most interesting one from an experimental point of view. We carried out this extensive characterization of the entire 2D database from a theoretical point of view. We ran several numerous application-oriented mid-throughput screenings aimed at finding nice materials for specific application. And at the end, we ran in parallel the creation and characterization of a novel database of 1D wire structures. So to conclude, the acknowledgements for founding, of course, the NCCR Marvel and the Max Center of Excellence, and also the Marie Curie actions. For computing time, the PRAISE program and both the Swiss and Italian supercomputing centers, CSCS and Cineca, and also to the people mainly involved in this project, Nicola Monet, Marco Gibertini, Giovanni Pizzi, and of course Professor Mazzarri. And again, a big thank you to the organizers for inviting me, and of course to you for your attention.
Yeah, thank you very much, David. Questions? Well, let me ask one. So on one of your initial slides, you had visualization of the various materials, how easily they exfoliate, and so you discussed carbon, for example, was one of those, I think based on, or when you refer to the Nature Nanotechnology article. Would you show the...
Yeah, now I don't know why they...
So my question would be, it seems on that plot that actually carbon or graphene or graphite has some, is somehow sticking out of the crowd. So it's, I don't know, it seems that it's not by chance that graphene was the first material to be exfoliated. Can you comment on that?
So actually, so the graph that now I don't know why, but I cannot, seems that I cannot share the slides anymore.
No, I see them.
Okay.
I see the acknowledgement slide.
So
yes, this one. I think it was just there.
This one?
Yes, this one.
Okay, so this plot actually reports two things. So on the y-axis, we have the binding energies that at the end was the quantity that we decided to use to define if a material is exfoliable or not. On the x-axis, here we put it just to give it a little bit of more general pictures. What we report here on the y-axis is the difference in the interlayer distance between van der Waals, so a structure relaxed with a proper van der Waals corrected functional, van der Waals TF2, and instead a functional that has no longer range interaction, that is the revised PBE. So essentially, this one tells you that when you relax the structure with the revised PBE, the graphite layer just tend to expand a lot. So from this perspective, yes, you have this extreme behavior in graphite, that you have this huge expansion of the cell. But regarding the binding energies, instead, you see that graphene is not at the very bottom of the graph. So there are other materials that shows binding energies that are lower than graphene.
Okay, thank you. Are there further questions? That seems not to be the case. Well, then thank you very much, Davide, and thanks to all speakers of this first part of the morning session. So we will now have the coffee break, and we will resume at 11:30 with 4 more and very interesting talks to come. So then, see you in 20 minutes. Welcome back, everybody, for this second part of the morning session. And we have, before the lunch break, still 4 very interesting and exciting talks ahead of us. And we start with an invited talk by Giuseppe Nicotra from CNR IMM in Catania. And he will talk about atomic resolution transmission electron microscopy study of 2D ultra-wide bandgap semiconductor materials intercalated between silicon carbide and epitaxial graphene. So please, Giuseppe, the stage is yours.
Thank you. Good morning, everybody. Thanks a lot to the organizer for allowing me to present this talk today, and thanks the chairman for the presentation and everybody for attending. I am Giuseppe Nicotra. I am a researcher and electron microscopist at Institute for Microelectronic Microsystem of CNR in Catania. Today we'll present a study on bidimensional semiconductor intercalation between silicon carbide and epitaxial graphene. Here to outline the talk, we start with a brief introduction on Beyond Nanolab. Then I will introduce our recent study on graphitization of silicon carbide, and finally we'll speak about the intercalation study of semiconductor between SiC and graphene. Our lab is located in Catania, close by the international airport, in the premise of ST Microelectronics. Actually, our labs are inside microelectronics, and our offices are nearby, 5 minutes walking distance from ST. Here, the 3 main instruments of our electron microscopy facility. We have TEM 12010, equipped with a thermoionic filament for high resolution imaging, GIL 2010F with field effect gun for ultra high resolution imaging, equipped also with a GIF spectrometer for energy loss spectroscopy, and our latest RM 200 cold FEC is a cold FEC microscope with probe corrector for correcting spherical aberration, and fully equipped with both ADX and energy loss spectroscopy. This microscope are very high performance. It's one of the most performant microscope in Europe, and is able to work between 240 kiloelectron volt of oscillation voltage. At 200 kilovolts is able to have a resolution of 0.68 angstrom. 60 kilovolt is able to have 0.9 angstrom of spatial resolution. 60 kV is very strategic energy for analyzing bidimensional material, such as graphene. Thanks to the spherical aberration, this is what happened to the probe's electron probe. Without CS corrector, we have a larger probe size, 1.7 angstrom. When we switch the corrector on, our probe size gets squeezed and perfected. We can get a perfect round and aberration-free probe up to 0.6 angstrom, and are able to get these nice images that represent the direct atomic resolved images of crystalline graphene on the left and amorphous graphene on the right. Here I show a schematic diagram of how scanning TM works. Electron source is collimated by an aperture, and the electron beam crosses the lens and is converged over the the specimen. Thanks to the presence of scanning coil, the beam is scanning all over the specimen. And the transmitted electrons are collected by different STEM detectors. We have 3 different detectors: a high angle anodic field for Z contrast, a medium angle, and a bright field detectors. We can, with the system, we also keep it with the energy loss spectrometer and ADX spectrometer to get simultaneous acquisition of structural chemical information. I remind you that when we acquire the images with high angle dark field detector, we have Z contrast images which intensity is proportional to the square of the atomic number Z. Here show a typical image that we can obtain with our microscope. Here is reported an interface between strontium tatanite oxide and lanthanum peroxide. And thanks to this Z contrast, we can have also chemical information on the images due to the fact that the size of the atoms is directly, the intensity is directly proportional to the intensity and the square of the intensity. So we can easily localize the atoms, different atoms on the image. By the way, we can compare this image with the chemical information by using our spectrometers, and bidimensional chemical information can be obtained at atomic resolution. Our lab is also part of a big electron microscopy facility spread all over Europe, named STM3. Actually, it is an integrated infrastructure network of electron microscopy facilities, which provide also free access for academic and industrial research community in material science. And if you apply, we can share with us most powerful CAM techniques available at the nanoscale. Okay, let's go to our study. I will start with the characterization study of silicon carbide. There are several methods for mass production of graphene, such as CVD, liquid phase exfoliation, mechanical exfoliation. But all these techniques, the graphene is created, growth in a different substrate and SiC, and then is transferred on silicon carbide. But this entails several issues, such as damaging of the graphene, or with the different techniques, the graphene can be contaminated. In our study, we want to convince you that the controlled graphitization of silicon, hexagonal and silicon carbides is the best techniques. I show you our study of sublimation at very high temperature, ranging in 600 and between 600 and 900 centigrades on both silicon phase and carbon phase. Here report the first study obtained at silicon phase. Here in the image reports a step of silicon carbide. Actually, we are working with 4H silicon carbide step surface. And what we see here, if we zoom in at the interface, we can clearly measure the distance directly between the different layers on the terrace and on the steps. If we look at the distance that can be measured directly, very high precision, and we compare these results with the simulated one, we can see that in the case of the terrace correspond to the simulated one. The distance are actually the same. But if you move towards the steps, we can see that the distance between the first layer, called buffer layer, and the step is much wider. Actually, it's wider than the layer of the graphene layer. We interpreted this. We studied this effect and realized that in this case, there is in the steps, there is a delamination of the graphene, there is so a mechanical detachment. This is also entails also a change in the electronic structure. If we study at atomic resolution by the electronic structure by electron energy loss spectroscopy, thanks to its higher sensitiveness, what we can see here, we can clearly see the pi star sigma star peak, and the pi star corresponds to SP two hybridization. You can see here when the cis peak is very high, we have pure graphene. When we move on the first layer, we have pure graphene on the steps, and almost no sp2 hybridization is present on the terrace. So this means that no buffer layer is present on the step. Okay, if we move forward, we also studied the carbon phase. What we can see here, the situation is pretty different. There is a very large buffer layer, and we studied the concentration of the different chemical species inside. What we saw here, that there is a percentage, a residual percentage of silicon in between this buffer layer. When it drops to zero, we start to see pure graphene as confirmed by the Earth spectrum. And in this case, we realized that the sublimation is very slow, probably due to the presence of carbon, the first layer of carbon at the surface, and the desorption or the sublimation of the silicon is much slower. So for our study, the best way to get graphene on silicon carbide for our application is to use the silicon plate. So once we have got very good control of this method, we start to do our study of intercalation of wide bandgap semiconductors. Here I show cartoons from Al Balushi, who explain very well how the intercalation works through migration enhanced encapsulation growth. And here actually we can easily understand that intercalation is mediated by graphene, but through defects present in graphene. So when we have defects, the gallium droplet can go here, in the case of gallium nitride, and or also through the wrinkles, there is some aperture and the top, and the graphene, the gas can get in. Once the gas is below the graphene, a very uniform layer of semiconductor can be formed. If we remove the graphene and we perform the same deposition, we don't have uniform layer, but we will form huge islands that are not good for our application, for example, for realization of future vertical transition. So the presence of the graphene is very important. The graphene lattice acts as a pathway for the intercalation. So we started our study with nitride, and here we see a very nice intercalation results. Indium nitride is clearly showed here in this layer. The contrast images show clearly the presence of indium nitride. It's also graphene. Graphene is also visible, and the stacking of 4H6 is also visible. On the right, we can see the annular bright field images that is acquired by using a smaller detector, STEM detector. Actually, we will use a bright field detector with a beam stopper in the middle. So we collect the electrons scattered at a low angle in between the beam stopper here at the center and the inner side of the high annular detector. High angle annular detector, and this allows us to still get a direct economic resolution. But if we zoom in, we can also see light elements such as carbon. We can see the single carbon atoms. We can distinguish between silicon and carbides, silicon and carbon, as we see here. But most important is the fact that we can also see the nitrogen atoms that are not visible with other techniques. And thanks to this study, we discovered that in our process, we can get we can measure also the kind of stacking of the layer of indium nitride. Actually, here we can observe clearly the presence of a zinc-on-blank polymorphism of the layer. And this is the Hawley techniques. Right now, I'm able to see, observe this information in our materials. So give us a big capability on understanding the materials. Okay, we also performed a spectroscopy to study electronic structure, and what we can see here, the E spectrum of indium nitride is the blue one, doesn't contain any oxygen. This is a very good information. Just we can easily understand this by looking at the indium oxide spectra. Actually, there is no oxygen peak here. We can see also very nice fine structure of the nitrogen. We are continuing our work with the study of gallium nitride intercalation. Here we can see again the graphene. Here this contrast shows a slighter intensity increasing in the last two layers, but the chemical study confirmed that we have gallium and nitrogen in the bilayer and graphene on the top. Finally, I will show these last results on aluminum side intercalation. Here, the problem are related with the fact that aluminum has a higher energy ionization edge of 50/60, and the electron energy loss suffer of low probability to have a transition. So we have to increase the acquisition time for getting the spectrum. And we destroy the specimen. If you look inside this red box, you can see the graphene disappear due to the electron bombardment. In order to get rid of this problem, we are upgrading our facility with a new detector. Actually, we are removing our CCD detector with a new direct electron spectrometer. So without fiber optics, we can directly reveal the electrons, almost one by one. We increase the quantum efficiency, so the spatial resolution, the signal-to-noise ratio, the dynamic range. So we will be sensitive to traces of chemical compounds. This should be hollow in the next future. The upgrade is ongoing to improve our capability of study also of this material, but not only. I want to conclude by thanking all my colleagues that allowed it to get these nice results, and everybody for the attention.
Yep. Thank you very much, Giuseppe. Talk is open for questions. Are there any questions? Well, maybe I start. So, could you explain a bit more what is the motivation to grow these intercalated free nitride layers? I'm not an expert, but for example, is it possible to grow a monolayer of indium nitride by molecular beam epitaxy on some substrate, or is this the only way, this intercalation, the only way to get a monolayer of indium nitride?
Okay, this is, can you hear me? Yes, so.
Yeah, I hear you, yes.
Yeah, for sure, yes, could be possible with MB, but our idea is to make, to create a process compatible with industrial process for producing a future vertical transistors. So MBA is a technique that is very good for research, but not compatible for high throughput for industrial application. Here we use CVD techniques in order to use this one, and I have to say that yeah, the presence, as I told before, the presence of the graphene is a fundamental for this approach, and yeah, the idea is to create very shallow junction between silicon carbide and graphene, And the idea to use, for example, indium nitride, gallium nitride is also due to the fact that this material, especially when they are very high confinated, they have a very large band gap, and this will be useful for application in power devices. For example, right now there is an explosion of application in power device. ST Microelectronics is very interested in this for battery application, for example, where we need to control very high currents. So the devices that are thinking to realize are in that direction, controlling very high current, and at the same time reduce also power consumption. So if we have, for example, ballistic transport by using a bidimensional layer, we have very low energy loss. So, and this will be helpful in future application where we have to reduce at the minimum the current dissipation. So overall, this kind of approach helps in both sides. We can realize transistor able to transfer very high current, and thanks to the very high mobility, very low resistivity, we have also very high efficiency of the devices. This is the framework of the application that we are thinking.
Okay, thank you very much. Further questions? This is not the case, then thank you very much, and we move on to the next talk, which is also an invited talk given by Valentina Zanier from CNR Nano in Pisa, and the title of her talk is Growth and Characterization of Semiconductor Nanowires and Heterostructures. So please, Valentina, stage is yours.
Good morning, my name is Valentina Zannier. I am a researcher at Nanoscience Institute of CNR, and I work at NEST Laboratory of Scuola Normale Superiore in Pisa. Today I will speak about our research activity on the growth and characterization of semiconductor nanowires. Semiconductor nanowires are quasi-one-dimensional crystals which show many interesting properties, including the possibility to obtain defect-free axial heterostructure. In fact, when we combine materials with different lattice parameters in the bulk, due to the strain relaxation, we have the formation of defects such as dislocation at the interface. By contrast, combining the same material in the nanowire geometry, thanks to the nanometer size interface and to the strain relaxation along the sidewall, we don't have the formation of dislocation at the interface. Therefore, we can obtain heterostructures that are not obtainable in the bulk, and with many potential applications in electronics, optoelectronics, photonics. In Pisa, we grow the nanowires by means of chemical beam epitaxy. This is a schematic view of the growth chamber, and this is a picture of the system that is dedicated to the growth of 3-5 semiconductors. In this chamber, we grow the nanowire with the most common approach, that is the nanoparticle-assisted vapor-liquid-solid mechanism. In this approach, we have a metal nanoparticle, usually gold, that acts as a preferential absorption site for the molecules in gas phase that alloy with the particle. So when the liquid particle becomes supersaturated, we have the formation of the crystal at the interface, and so the one-dimensional crystal growth. This mechanism is really useful for the realization of nanowire of different material for the growth with a good control of size, shape, and crystal structure. However, there are also some drawbacks. For example, the different interaction among the gold particle and the growing material can affect the growth, giving some phenomena like interface grading and kinking. Now I want to show you an example of an axial heterostructure that we have studied, that is indium arsenide indium phosphide axial nanowire heterostructure. This system is really useful for the realization of axial heterostructure in the gold-assisted regime, thanks to the very low solubility of both materials into the gold particle. And so we can obtain, for example, indium arsenide nanowires with built-in indium phosphide tunneling barriers, really well defined and with very sharp interfaces between the two materials. However, the controlled growth of this INAS imp axial heterostructure in the gold-assisted mechanism is not straightforward. For example, phenomena like kinking or downward growth have been reported. Also, the growth rate is different of the two materials, and the nanoparticle composition during the growth of indium arsenide is different than during the growth of indium phosphide. So we have decided to study more in detail the growth mechanism. We started by growing indium arsenide nanowires on indium arsenide 111B substrate using gold colloids. Then we studied the chemical composition of the nanoparticle on the tips of this nanowire stem, and we found that these are indium gold alloy particles with an indium to gold ratio 0.5. Then on top of these indium arsenide nanowire stems, we have grown the indium phosphide axial segment using different phosphorus line pressure. And this is what we found. When we grow the indium phosphide segment using high phosphorus line pressure, we obtain the straight axial heterostructure. But if we use a lower indium line pressure, we obtain this kink geometry. We have analyzed the nanoparticles of these wires, and we found that in both cases, the amount of indium increases when we go from indium arsenide growth to indium phosphide growth. But the amount of indium into the particles of straight nanowires is relatively lower than the amount of indium into the nanoparticles of the kinked nanowires. So we decided to analyze better these nanoparticles and their evolution with the growth time. These are the TM images of the sample and the different growth times with the two opposite growth conditions. We found that when we grow the nanowires using a high phosphorus line pressure, the amount of indium is relatively low and the contact angle of the particle is constant for the whole growth time, which means also after a very long segment growth. On the other hand, when we grow the nanowires using low phosphorus line pressure, at the very beginning, still we have low amount of indium and the contact angle around 110. Then we see this widening of the base radius of the nanowire, because probably the system tries to keep the contact angle relatively low. But if we go further, the nanoparticle inflates because we have a higher amount of indium, the contact angle increases, and so the particle becomes stable. If it wets the sidewall of the nanowire, we have it triggers this kinking. Then we did some modeling and some calculation, and in particular we calculated the surface energy of the nanowires in different geometry, in different configuration, compared to the vertical and to the straight axial growth. Taking into account the parameter for our system, if we plot the minimum of the surface energies versus the contact angle, this is what we obtain. In particular, we see that there are two stable contact angles. So there is a contact angle window in which we have a stable vertical growth. If we go for a larger contact angle, we have this widening of the base radius. But if we go above a certain critical contact angle, the kink geometry with a wet sidewall becomes energetically favored. And so these results explain our experimental observation, and we can say that we found the condition to obtain the straight indium phosphide growth on top of indium arsenide nanowire. However, we have seen that even in the best conditions, so when we have straight growth, the amount of indium into the particle increases when we grow from indium arsenide to indium phosphide segment. And this is a problem when we want to grow thin alternating indium phosphide indium arsenide segment. For example, if we grow two thin indium phosphide barriers for the same time separated by a short indium arsenide segment, a quantum dot, we obtain asymmetric barriers. And if we grow together nanowires of different diameters with the two barriers, we see that the barrier asymmetry is opposite. This means that nanowires with very large diameter show always the first barrier thinner than the second one. And nanowires with smaller diameter show the first barrier thicker than the second one. This is even more clear here for the same sample. Here we plot the thickness versus diameter of the indium arsenide dot, that is constant, and of the two indium phosphide barrier. And as you can see, the two barriers show an opposite behavior, suggesting a different material transport dynamics. So the question is how the nanoparticle compositional variation between the two equilibrium composition depends on the diameter. Well, we have to consider that the indium absorption occurs at the nanoparticle surface, while the indium depletion from the particle occurs at the nanoparticle nanowire interface. So both absorption and desorption are proportional to the radius square. However, the amount of indium that has to be absorbed or released to reach the new composition is proportional to the nanoparticle volume. This means that larger particles take longer time to reach a new composition. So if we plot now the nanoparticle compositional variation between the two equilibrium compositions for INAS and for RIMP GRO for 2 nanowires with different diameter, we can understand that at the first indium phosphide barrier grow, small particles will reach earlier the new composition, and so for the same deposition time, the first barrier will be thicker. For the same reason, during the indium arsenide grow, larger particles lose less indium, and so at the second indium phosphide barrier grow, they will reach earlier decomposition, and the final barrier will be thicker. So now that we understood the grow dynamics, we were wondering, okay, but can we control the grow dynamics? So can we have symmetric barriers at the end? The answer is yes, if we can force the particle to have the same composition before growing both the indium phosphide barriers. So our idea was to keep the nanowires under arsenic flux after the first barrier and the second barrier growth. This grow interruption with arsenic flux basically remove the excess of indium from the particle, restoring the chemical composition. So if we implement this grow interruption, we obtain exactly symmetric barrier thickness and the same thickness versus diameter dependence. This means that we found a strategy to achieve an homogeneous grow dynamics for multiple barriers, and in fact we could realize heterostructure with well-defined and well-controlled segment thickness, like single and double quantum dots. Now I want to show you another example of an axial heterostructure that we have studied, that is indium arsenide, indium antimonide axial heterostructures. Indium antimonide is a very interesting material for optoelectronics, thermoelectric, and quantum computing. However, the epitaxial growth of indium antimonide layers of good quality is challenging because of the large lattice mismatch with all other 3,5 semiconductors. Also, the antimony has a very strong surfactant effect, therefore the control of morphology is difficult. In the past, we have obtained this, we have grown this indium arsenide, indium antimonide axial nanoheterostructure. We found the growth condition, the optimal growth condition to obtain these nanostructures, and we have studied their properties. We found that the indium antimonide segment show a cubic, so a zinc blende crystal structure, even when it is grown on top of Wurtzite indium arsenide nanowire stem. Then we analyzed the profile of these two segments, and we found that both materials show an hexagonal cross-section, but the two hexagons are rotated by 30 degrees. This means that the indium arsenide stem has 6 equivalent 112 sidewalls, while the indium antimonide segment has 6 equivalent 110 sidewalls. Recently, we have studied the effect of the growth temperature. So this is the growth process. We first have grown the indium arsenide nanowire stem at constant temperature, and then we have grown the indium antimonide segment at different temperature. This is what we found. At relatively high temperature, basically we have mainly axial growth, while at lower temperature we have mainly radial growth, giving these nanocubes, kind of three-dimensional crystal. At intermediate temperature, we have both axial and radial growth, and so we obtain these thick nanowires. If we keep the sample rotating during the whole growth time, we obtain these symmetric and homogeneous nanowires. But if we stop the sample rotation before growing the INSB part, and we align the indium arsenide nanowire stem with the help of the reed pattern in order to have the 112 sidewall of the indium arsenide stem perpendicular to the antimony injector, we obtain these asymmetric indium antimonide nanowires. This happens because in this configuration we have two indium antimonide sidewalls that are directly facing the antimony injector, while the other 4 sidewalls are screened from direct impingement. And so the growth rate on these 2 sidewalls is higher, and so we have an enhancement of the radial growth in this direction. So if we stop the sample rotation, we align the indium arsenide nanowire stem with the reed pattern, and we increase the antimony flux by adding an additional step in the grow recipe, we obtain this asymmetric growth enhancement, and we obtain these freestanding two-dimensional indium antimonide flags that are called nanoflags. We found that there are two families of flags, and they differ from the aperture angle, that is the angle between the INAS stem and the base sidewall of the flag. By analyzing these flags by TEM and by doing some modeling, we understood that the two different aperture angles are a consequence of a rotation around the growth axis of 180 degrees of these 6 facets that develop at the INAS-INSB interface. And so from top view, when we have this configuration, inside view we have this 145 aperture angle flag, while if we have this configuration in top view, that is the same of this but rotated by 180 degrees around the grow axis, inside view we obtain this 160 aperture angle flag. However, both these kind of flags show a very good crystal quality. This is the TEM analysis, and we found that the flags are defect-free zinc blend crystals, single crystals, with a stoichiometric composition and a completely relaxed lattice parameter as it is found from the GPA analysis. Finally, in order to grow bigger flags, we increased the grow time, the antimony grow time, but unfortunately we did not find we did not obtain a good sample. This is probably because the very thin untapered indium arsenide stem after a long grow time bend, and so the alignment is lost and we have this bad sample. We don't have a good flags. However, if we use, instead of untapered thin indium arsenide stem, we use different stems, like for example tapered indium phosphide nanowires, we can keep the nanoflags well aligned with respect to the injector for even a longer grow time. And so at the end we obtain bigger, well-oriented indium antimonide flags. And these flags are suitable for the realization of multi-contact devices. Indeed, we have realized this whole bar device and we measure the mobility and the carrier density. To conclude, I've shown you that the nanowire geometry gives the opportunity for realizing defect-free axial heterostructure. However, the nanoparticle-nanowire interaction can strongly affect the growth mechanism. And finding the parameter that affect axial and radial growth is important to control and tune the final morphology. So at the end, I hope to have convinced you that studying the growth mechanism is really important to develop growth protocols that allow to obtain a good control of the growth of the nanowires with the desired properties. I want to thank all the people I work with, and thank you very much for your kind attention.
Yeah, thank you very much for this nice talk. Talk is open for questions.
May I ask a question?
Yes, please.
Thank you, Valentina, for the nice talk. I'm curious about how large is the density of the nanowires, as well as which is the maximum length that you can achieve for the nanowire.
Okay, well, the density can be controlled, for example, by changing the density of the gold colloids when you use gold colloids to nucleate the nanowire. So this offers a good control of changing density. And the maximum length depends on the growth time. So, for example, for indium arsenide nanowires, that is probably the material that we are you can grow also with high fluxes. We can achieve a few microns, even 10 micron long nanowires. For other nanowires, for example, the flags, as I show, there are some problems because we need to keep the sample well oriented to have these flags. But since they are very big, if the stems bend, we lose the orientation, and so we cannot achieve big flags. But we can improve by, for example, using more robust stems, and so we can achieve also in this case a micrometer long flags with the width around half a micron, something like this.
Thank you.
Other questions? Well, I have a curiosity. So you said when you go from, you grow the indium arsenide, indium phosphide heterostructures, no? That when you go from INAS to IM, that the indium content in the droplet increases. And in the sketches, it seemed that the droplet gets larger in this process. Then shouldn't the indium phosphide part be larger? So shouldn't you have a larger diameter of the indium phosphide part as compared to the indium arsenide part?
Well, it depends on the exactly if the nanoparticles can remain stable. So if the particle inflates in any case because the amount of indium is higher. However, if the particle can remain stable, so the contact angle does not exceed a certain critical value, we don't have the widening of the base radius. But exactly if the particle becomes bigger, so its volumes increases, to remain stable, we have this widening, and so the indium phosphide segment show a larger radius.
Okay. Well, thank you very much for this very interesting talk, and
Thank you.
we move on. So the next is a keynote lecture presentation given by Gianluca Fiori from the University of Pisa, and he will talk about two-dimensional materials-based printable electronics. So please, we're looking forward to your talk.
Do you see my screen?
Yes, it's a bit small actually, but
now
it's better. Yes,
okay.
Perfect.
Okay. So first of all, let me thank the organizer for giving me the opportunity to present part of my results, and plus this is really I mean, let's thank also the organizer for organizing this conference that in these really hard days, so where it's difficult to spread opinion and to meet by person. I believe that I don't have to introduce you to dimensional materials. That is the focus of the talk. That is in particular what I try to show you today is to how to use two-dimensional materials for electronic applications. So two-dimensional materials can be obtained following different procedures, following different growing techniques, for example, CVD and so on. There are other techniques where you start from bulk materials, and then what you do is that you are exfoliating the layered materials. And one, probably the most famous, is the one related to the Scotch tape. But there are other ones that are more concerned with what is called liquid phase exfoliation, that has been mastered and first pioneered by Johnny Colemans a few years ago, where you start from bulk materials that you put, I mean, just making the long story short, then instead of applying a mechanical force, what you're doing is that you are giving energy to the like, for example, with ultrasonication, of the liquid, and then you give energy to the different layers to be thrown apart from the bulk. And then the good thing is that almost with the very same procedure, just starting from different materials with different electronic properties, you can obtain in the end liquids that have conducting, semiconducting, or insulating properties. Just starting, the only difference is that you start from different materials that are either conducting, semiconducting, or insulating. So the idea would be, why don't we use these inks, these liquids as inks, to obtain and to fabricate devices using, for example, printing technology like inkjet printing technology. So the motivation from exploiting two-dimensional materials is that current teams have limited bendability and most of all electrical properties like the mobility that is not pretty much large, that is always most of the time smaller than 10 centimeters square per second, or even way smaller. And there are also problems with stability. While two-dimensional material, in principle, could be an added plus to this technology, because they have both shown along the years extraordinary mechanical, electrical properties, and then there are plethora of materials that you can pick up with either semiconducting, conducting, and insulating properties. And the other thing is that being layer material, they stay well on top of the other. So in principle, one may think of obtaining complex structures. So a device engineer may have an additional degree of freedom while trying to build up heterostructures. So the work that I'm doing here is done in side collaboration with the University of Manchester, and in particular Professor Cinzia Casiraghi, who is developing these two-dimensional links, and the Manchester group is providing us the inks, and we are exploiting from an engineering point of view in order to obtain in the end a kind of printed electronic device toolbox, where we want to define all the electronic components that are needed in order to obtain complex circuits. So here we have to start from scratch, because this is a completely new technology. So we need to define, we need to start even from the really conducting lines. Then we have to define passive components, like, for example, resistors, capacitors, inductors. Then the other thing that is missing are nonlinear devices like diodes, up to the king of device, that is the transistors. So we need to start from scratch and try to define all these main electronic components. And while once you have achieved this goal, then you may think of going for more complex circuits, like, for example, memories, or even really complex devices, like, for example, CMOS operational amplifier. So, and in the end, you would like to go to really at the higher level of abstraction, to the highest level, of integration, and obtaining really complex devices and circuits where you integrate both, for example, the sensors, as well as all the electronics that need to be exploited in order to drive the sensors, as well as the electronics to deliver the information to an external reader. That could be whatever, even a cell phone. This is, for example, what we are trying to do in this European project, WASP, where indeed the goal is to try to print and obtain a complex circuits as the one that I've just told you, where you have sensors and electronics all integrated on flexible substrates, like, for example, a bandage, and then delivering the information regarding, for example, humidity, pH, temperature, to an external reader that could be a cell phone. So, but this technology it cannot there are really a wide range of applications where you could definitely use this technology. So not only portable healthcare application, but also, for example, anti-counterfeiting applications, like, for example, even luxury goods, or smart labels that are able to detect, for example, the freshness of the product, or for example, there's been a break of the cold chain of the product itself. So where are we now in terms of technology? So what I generally like to show is this picture that is a picture of the very first together with the other, with the brother, that is Intel 4004. That is the first ever microprocessor which has been put in production by Intel at the beginning of the 1970s. And if you zoom, you see that you have those are the metals layers and the different parts of the, I mean, the layout of the processors. And if you see the feature size of the distance, for example, between the different lines are of the order of tens of micrometers. And this is done obviously on a rigid substrate that is silicon. But actually, with the current technology, printing technology, you can obtain almost the very same feature size on flexible substrates like this one, and this is paper. So not silicon, but paper. So here you see that the distance, the gap, is the orders of tens of micrometers, but you can even push the technology farther. For example, here we can reach distances of the orders of a few micrometers, and this is being obtained, for example, with an inkjet printer that we are developing here in Pisa in order to push the resolution of the inkjet printing on flexible substrates. So, as I was saying, we have tried hard to obtain passive components, static passive components, like, for example, capacitors. Here is an example of a capacitors that we have printed in collaboration with Manchester's, where the electrode, the bottom and top electrodes are made of graphene, and the dielectrics is made of hexagon-boron nitride. We have fabricated a simple RC filter. It's a low-pass filter with incredibly we got frequency response in accordance with what was expected. These devices have been printed on rigid substrates like glass, and the larger the electrode as expected, the larger the capacitance. The capacitance that you obtain as we compare to what has been previously obtained in the literature with really good performance, and with large, both in terms of breakdown voltage that is way large. I mean, larger than I was ever expecting, because it's something like 7 megavolts over centimeter, which is close to the silicon dioxide breakdown voltage, and with the electric constant around 6, which is good as well. So, but we are not only interested in the electric per se, just to make capacitors, but we are interested in the electric in order to obtain a working printed field effect transistors. And this is the first device that we have ever been obtained on paper, on a graphene printed device, where everything is printed. This is printed on paper, and you see the structure is this one. This is a silver contacts. Graphene channel is printed. The electric as well as the top contacts are printed. Again, I mean, I want to stress that this has been printed on top of paper. The characteristic of this one, where we see a kind of flavor of modulation of the current, but this is not because these devices are not good. This is because graphene channel is not good in general, even if instead of printing the graphene as a channel material, but as has been demonstrated, for example, in the past by a group of Max Lemmer or Fedor Vuris, even if you go for microelectronic fabrication techniques and you go for a single flakes graphene, then you try to get a transistor out of it, you'll never get pretty much more current modulation as the one that is shown here, because graphene is gapless. So rather than going for graphene as a channel materials, that is a semi-metal rather than a semiconductors, you would rather go for a semiconductor here in the channel. But the problem is that so far, and this is indeed an issue that still have to be solved, printing of good semiconductors made of, for example, MOS2. MOS2 is a semiconductor, but inkjet printing of semiconductors it is for the moment really hard to do, because I mean, even from the very first example, it was clear that the modulation of the current in a device made of transistors with the printed MOS2 as a channel lead to really poor conductivity, probably because of lots of interface states and defects in the flakes that are in the network of flakes that are realizing the channel. So given that, what we decided to go for a different approach. So we decided to use CVD MOS2 transfer on top of flexible substrates, and then define all the other fabrication steps through inkjet printed technology. I mean, the definition of the contacts, as well as the electrics, the top contact, as well as the interconnection between the different devices. This is a work done in collaboration with Vienna University, Thomas Müller, Manchester, Cinzia Casiraghi, and IIT Camilla Coletti. So the idea is to start from CVD MOS2 on sapphires, then pattern, then go go for a transfer of the MOS2 on top of paper, so to obtain a paper that are pre-functionalized, let's say, with stripes of MOS2 that will be eventually used as a channel in the device. So these are this is a picture from the microscope, optical microscope, and this is those are again the pictures of the field effect transistors with the different steps. So the definition of the source and drain, then of the dielectric, and then of the top contact. And incredibly, we got really nice characteristics. So these are the transfer characteristics, negligible leakage current. And the thing that I want to stress is that we obtain really large modulations, 4 orders of magnitude, with considering really small supply voltages, smaller than 2 volts. So good saturation in the output characteristics, and the performance in terms of field effect mobility as compared to Janoff ratio normalized with the VDD, it's already good as compared to other technology, more mature technology, like, for example, organic semiconductors. And we have also made some Do you hear me?
You were gone for a moment, yeah.
You hear me now?
But now, yes. Now
okay, good. So okay. I was saying that we were doing some bending tests on top of paper, like here, and we got really, so it seems that the IV characteristics are not dependent on the bending. In principle, this can be used for flexible applications. We have also tried to use, instead of silver, graphene, and just to make everything two-dimensional. But the problem is that graphene on top of MOS2 is leading to shocky contacts, as can be seen here by the Burrs net the output characteristics as here. So probably rather than going for graphene as a contact, it would be better to stick on silver. That indeed is a good option. And we have also tried to implement these the simple circuits like inverters and NOR ports that has been used. And this is another work that we have done, but on rigid substrates. This is a work led by Thomas Müller, where indeed the MOS2 technology, but not printed, this is microelectronic technology, has been used, exploited to obtain analog operational amplifiers. And the next step, hopefully, will be to try to implement these on flexible substrates with solution process technique. I'm moving on. Probably one thing that we, let's say, the winning strategy, rather than going fully printed, is trying to use an hybrid approach. This is a work which has been done in collaboration with Tor Vergata, Professor Francesca Brunetti, Manchester, and ICN2 with Professor José Garrido, where we have tried to implement sensors where on top of substrates that is as large as a credit card, this is paper, where the antenna is printed, the IC that is deputed to read the information of the sensors and then delivering information back to the reader is done with silicon technology but on flexible substrates. So this is a flexible PCB. And then we have the sensors made of graphene. This is a strain sensor just to make a proof of concept. But this is a resistive sensor that in principle can be substituted with other resistive sensors like temperature or pH sensors. And this is a perovskite solar cell on flexible substrates. So we have tried to demonstrate the functionality. So when the light is off, this behaves like a single strain samples read, and the information is, so the power is delivered by the cell phone, and the information is delivered back once the sensor is interrogated. While in this case, when the light is on, we have multiple strain values since the power is delivered by the solar cell, and then this data are delivered back when the cell phone interrogates. I have a video. Do you see it?
Yes.
Okay.
It starts, yeah.
Okay, good. So this is a sensors. We have the read. So in this case, this is runtime. This is a counter, and this is the value of the resistance. When you see in this case, when we switch on the light, it keep on reading the value of these sensors. Indeed, you see that the runtime, now the counter is no more 1, but it's 23. Then whenever you pass on top, this is the runtime, and this is increased. So these devices is reading and storing this information. So it's a data log of the device. That for simplicity and for commodity, this has been this has been used outside. And then there is another example of a strain sensors, strain tag sensors. Then you see the graphene is a strain sensors where is changing the resistance whenever you apply the strain. So now we have just one read. It's no more a data log. We don't have a solid cell. And you see now we are applying a compressive strain, and then the resistance should decrease. And this is the case because whenever you apply a compressive strain, you increase the conductivity. While if you apply tensile strains, the resistance is going to increase. And so now you should read a resistance larger than the one that we have seen before. So 70 kiloohms, and this is the case. So I'm at the end, so just one last thing, we are hiring. So if you know anybody who could be interested in joining the group, just spread the words, telling to send him an email, and that's all, folks. So just go to the acknowledgement. Thank you for your attention.
Yeah, thank you very much for the very nice talk. Questions? Someone in the audience? Well, let me ask one. For these graphene treat effect transistors, it seemed that the graphene was quite doped. Do you have control on the doping level of the graphene, and can you actually adjust it?
You say that it was quite dope because of what? Because of the fact that
it seemed that the minimum was shifted to
yeah, the minimum was shifted by 0.5 around electron volt, excuse me. Yes, indeed, this is something that indeed we are investigating. So this is, I would say, this is an unintentional doping, and plus, you know, what you're doing here, you are printing the channel using the inks. In the inks there are solvents, and even the solvents can behave as doping. And plus those are water-based ink, and it has been proven that indeed the water by itself, water molecules can dope the graphene or even the other semiconductors, and sometimes it can be really hard to remove water, because you know you have this network of flakes, so that they can be it can be trapped between one flake and the other, and even if you anneal, you do a post annealing, then the water can be remain trapped. This is a really tricky point that somehow we have to solve.
Okay. Any other questions?
Yes. Hi, Gianluca. Thank you for the
Alessandro. Ciao.
It's I just got you're thinking about making this kind of devices for low power application. Am I right?
This is something that we are for low power, because you want to use for wearable applications. So whenever you say wearable or portable, you need to comply with the small voltages, which in the end means low power.
But in this respect, I'm wondering, what is according to you the target mobility you want to achieve? Because probably you should actually mobility around 20 or 30 or something like that. Sorry, I'm not so precise. But I think it should be enough, or do you think that you need still more better performance just in order to have wearable sensors or whatsoever?
So this is a good point. For what concern, so mobility of around the 10 centimeters squared volt per second, from my point of view, it's already sufficient to get good conductors and good semiconductors. Regarding the low power, rather than the mobility, there's another important aspect that is more related with the dielectric. So you would like to be able to define really thin dielectric, or either really thin dielectric or dielectric with large dielectric constant. So this is the key to get low power.
Okay. Thank you so much.
Thank you.
Other questions? Well, then let's thank Gianluca once more and move on to the next talk.
Thank you.
Yes, which is the last talk of this morning's session. It's an invited talk given by Lorenzo Caputi from the University of Calabria. And he will talk about graphitic layers with massless Dirac fermions wrapping iron microspheres. So, Lorenzo, please, stage is yours.
Good morning. I want to thank the organizers for inviting me to give a talk on the evidence of massless Dirac fermions we found in graphitic shells encapsulating hollow iron microparticles. I also want to thank my co-authors. The collaboration of colleagues from countries in the Caribbean region was made in the framework of the Unicaribe Research Center, which is based in the University of Calabria and is financed by Regione Calabria. Finally, I want to thank Fondo SIT of the Dominican Republic for the partial support. Graphene is at the center of a huge scientific interest worldwide. Perhaps the most relevant property and also the most exotic of graphene is the linearity of electronic bands close to the Fermi level, which makes charge carriers to behave as massless Dirac fermions with a Fermi velocity of about 10⁶ meters per second. This property makes graphene very interesting for the nanoelectronics industry. Unfortunately, to obtain graphene with high purity in large quantities and with sufficient lateral size is not a simple job. Various methods are used, but often they are not scalable, and often they give strongly interacting or contaminated graphene. But to take advantage of the electronic properties of single-layer graphene is not strictly necessary. In turbostratic graphite, in which graphene layers are rotated with respect to the AB Bernal staking, the reduction of the electronic coupling between adjacent layers causes the recovery of the band linearity. As an example, turbostratic multilayer graphene grown by CVD has been tested in field effect transistors, giving results identical to those obtained by using single-layer graphene. Therefore, turbostratic systems are an interesting alternative to single-layer graphene for nanoelectronics applications. We used a simple method to synthesize turbostratic graphene layers with high purity and high structural order in the basal planes. The method is based on an electric discharge between two commercial graphite electrodes submerged in deionized water. The cathode and the anode have diameters of 10 and 6 millimeters respectively. The cathode is fixed, and the anode can approach the cathode by translating and rotating around its axis. During the discharge, the plasma typically reaches temperatures of the order of 6,000 Kelvin. In these conditions, iron and carbon are vaporized, and they crystallize when ejected in surrounding water due to the strong temperature gradient. After the discharge, various types of particles are found in the vessel. In a previous work, we have demonstrated that in the absence of iron in the anode, carbon nanoonions with turbostratic character are preferentially formed on the surface of the cathode. Here, we found iron-containing microparticles dispersed in water that we selected by a magnet and studied by scanning electron microscopy, energy dispersive spectroscopy, and Raman spectroscopy. Here, you can see the morphology of the microparticles selected by the magnet. We observed spheroidal particles of two types. Particles in A, B, and C appear as covered by a continuous layer with wrinkles, different from particles in D, C, and F. The origin of such difference is clarified by EDS spectra, which show that the surface of particles with wrinkles is made of carbon, while the surface of the other particles is mainly made of iron, about 80%, with some carbon and oxygen. In F, a broken particle allows to observe the structure of the shell, made of nanocrystallites and with a thickness of about 10 micrometers. To gain information about the internal structure of the particles covered by carbon, we treated them in a cavitation field, which causes surface damage, as shown in this figure. In the damaged area, a nanostructure very similar to that of the naked particles emerges, showing the underlying iron microparticle. We also micromanipulated such particles to measure the thickness of the carbon layer. In this figure, you can see that the thickness is of the order of a few micrometers. We analyzed the size distribution of the types of particles. The black and gray histograms represents the distributions of the diameters of the carbon covered and of the naked particles, respectively. On the basis of these findings, we can hypothesize the mechanism of formation of these microparticles. When the bubbles of iron vapor are expelled from the plasma zone in surrounding water, the strong temperature gradient drives a rapid crystallization close to the iron-water interface, with the formation of hollow iron microparticles. After their formation, these microparticles can be wrapped by carbon layers due to the crystallization of surrounding carbon vapor. Such layers show high robustness also in the presence of strong discontinuities of the underlying iron surface. Just a few words about Raman spectra of graphenic system, which are characterized by the G band associated to the vibration of carbon atoms against each other, the D band due to the breathing mode of aromatic rings, and the 2D band, which is an overtone of the D band. The D band needs defects to be activated, and the D over G intensity ratio is a measure of the density of defects. In fact, in this figure, the D peak is absent due to the high crystalline quality of the sample. In freestanding graphene, the 2D band is more intense than the G band, and its full width at half maximum is reduced with respect to graphite to about 20 Wave numbers. In turbostatic graphite, as for example, in this spectrum, that is the spectrum of our carbon nanoanions, the 2D peak is monomodal, but its full width at half maximum is larger with respect to single layer graphene. Twisted bilayer graphene deserves particular attention. It is the simplest turbostatic system, and it has been shown that for misorientation angles higher than a critical value, Raman spectra are very similar to single-layer graphene. Here, AIN and VF are the lattice parameter and Fermi velocity of single-layer graphene. And the identity corresponds to the resonant condition in which the laser energy equals the energy difference between valence and conduction van 't Hoff singularities. In the frequency range compressed between the D and G bands, double resonance modes are activated by the static potential associated to the superlattice induced by the misorientation angle. The frequency of these R modes depend only on the rotation mismatch, and so they allow to determine the misorientation angle. It has also been shown that in twisted bilayer graphene, the combination modes are enhanced, and the M band, which is a fingerprint of Bernal staking, is absent. We studied the surface of carbon-covered microspheres by Raman spectroscopy. This figure shows 4 typical spectra. All the spectra indicate the presence of graphitic layers with different degrees of turbostatic character. Spectrum A is similar to the spectra measured on turbostatic carbon nanoanions. In spectra B and C, the situation is completely different, with a 2D over G intensity ratio much higher and the full width at half maximum of the 2D band of around 20 Wave numbers as in single-layer graphene. This seems to indicate the presence of single-layer graphene, but here the thickness of the carbon layer is of the order of a few micrometers. In spectrum D, the G and R bands are overexpressed with respect to the 2D band. We will see that this is caused by the resonant condition. A portion of the spectrum B is reported here. And we can see that more bands appear. The image in the inset was taken with the optical microscope of the Raman spectrometer and shows the points in which spectra B and C were measured. Inset B shows an enlargement of the D band range. The bands we observed indicated the presence of twisted bilayer graphene. In fact, we observe rotation modes in the range between the D and G bands. And also, we observe well-developed combination modes and the absence of the M band. Therefore, we can interpret the spectrum as due to twisted bilayer graphene. In our case, the critical value of the angle is 12.1 degrees. For higher misorientation angles, the Raman spectra should be similar to single-layer graphene. In fact, the frequencies of the R bands we observe give 15 and 26 degrees, well above the critical value. This justifies the fact that spectrum B is very similar to single-layer graphene. The R band frequency in spectrum D gives a misorientation angle equal to the critical value, and the resonance condition holds with an enhancement of the G and R bands. The similarity of spectra for single-layer graphene and twisted bilayer graphene for misorientation angles higher than the critical value has its counterpart in the low-energy electronic properties. In fact, it has been experimentally demonstrated that in these conditions, Dirac cones are recovered in twisted bilayer graphene with the appearance of massless Dirac fermions. We have to note that the depth probing is about 100 nanometers. Thus, Raman spectra are due to about 300 graphene layers arranged as a stacking of twisted bilayer graphene. Summarizing, we synthesized hollow iron microparticles wrapped by high-purity graphitic shells in underwater discharge experiments. Raman spectra show that the shells have graphitic turbostatic character in some domains, while in others they are made of a superposition of twisted bilayer graphene. In twisted bilayer graphene domains, the electronic structure is indistinguishable from single-layer graphene with the presence of massless Dirac fermions. This work opens a new road for the simple synthesis of thick graphitic layers with charge carrier properties of freestanding graphene for graphene-based electronic devices. Thank you.
Yeah, thank you, Lorenzo, for this interesting talk. Questions? Well, there is one thing I did not understand. You showed that these iron spheres, they are hollow, so empty inside. And I didn't understand why they form empty inside. I think when you form them in the plasma source, this is probably a liquid droplet of iron. And when it cools down, where does the iron in the center go?
This is what I said in my talk. I mean, if you have the droplet of iron vapor, when iron condenses on happens on the surface at the interface between the bubble and the surrounding water. So this is probably the reason for the condensation of iron contained in the bubble at the surface, near the surface, which is the interface with water. Of course, this is a very complicated process, but we can suppose something like that.
But the bubble, would this be, so you have an idea that you have some kind of an iron bubble in the liquid phase that is already empty inside, or is there water involved in this process?
No, to my opinion, if I have a bubble of iron vapor, you, in some way, of course, you condense this iron on the surface of the bubble, and so this is the reason why you have an empty space inside.
Okay. Well, thank you. Other questions? That seems not to be the case. Also, the chat is empty. Well, I think then we are done for this morning. So I would like to thank all speakers for their excellent talks and also for being on time. So then now we have our lunch break, and the afternoon session will resume at 2 p.m. Okay, thank you to everybody, and have a good lunch.
Thank you. Bye.
Bye-bye.
Bye-bye.
Okay, good afternoon. I think that I can take the chair now, because it's 2 o'clock. I don't know if there is someone connected of the organization, but I can see that Giovanni, our next speaker, is already connected. So I'm going to present. Okay, I'm going to present Giovanni. Giovanni is associate professor at the University of Rome La Sapienza, and he will give a presentation which is entitled Nanocomposite Ablative Materials for Thermal Protection Systems for Re-entry Vehicles. So if you're ready, Giovanni, the stage is yours. You can share the screen and start the presentation.
Yes, I think that, okay, perfect.
Good afternoon, and thanks for this invitation. It's a pleasure for me to talk about this research activity regarding the development of nanocomposite ablative materials for heat shielding of re-entry vehicles. Let's start with a look at some notable events in the field of space exploration. For example, in the last month, on the 2nd of May, the spacecraft Dragon, called Resilience, returned to Earth from the International Space Station with a crew of 4 astronauts. And this was a very important mission because it was the first operational mission to the International Space Station of a crewed private spacecraft. And in general, the SpaceX Dragon was the first spacecraft of a private company able to operate with the International Space Station, both as a cargo and since last year also as a manned spacecraft. Anyway, SpaceX is not the only company working to transport astronauts to the International Space Station. For example, the Boeing spacecraft Starliner is also designed to carry both crew and cargo to the International Space Station. Starliner has not performed manned missions yet, and NASA and Boeing are preparing the second uncrewed test flight planned on the 30th of July. At the same time, NASA is developing its crewed exploration vehicle called Orion. Orion is designed for long-duration deep space missions, for example, to the Moon or to Mars. Also in this case, Orion has not performed manned missions yet, but for example, a full-scale uncrewed test flight entering a lunar orbit is scheduled for the November 2021. Another recent notable space mission is Mars 2020. To transport the rover Perseverance on the Martian surface, Perseverance entry capsule descended through the Mars atmosphere exactly 4 months ago, the 18th of February. And so, the spacecrafts Dragon, Orion, Starliner, Mars 2020, but also the Apollo, what do they have in common? They are all blunt spacecraft with a sphere cone-shaped section, a low aerodynamic lift-to-drag ratio, leading to short re-entry time and abrupt aerobraking. And for this reason, the heat fluxes experienced during the atmospheric re-entry are very intense and spacecraft structures have to be protected by means of ablative thermal protection system. And so, let's have a look at an ablative thermal shield. Ablative materials typically, but not always, are reinforced composite materials having a thermosetting or thermoplastic polymer matrix. During the atmospheric entry, a huge amount of spacecraft kinetic energy is dissipated by the aerodynamic friction, and the consequent incident heat flux leads to an intense surface heating and also to a surface recession induced by the ablation mechanisms. For this reason, during the re-entry, an external porous char layer forms because of the pyrolysis of the organic matrix. There is an intermediate layer in which the pyrolysis reactions are still occurring, and an inner layer of virgin material at a temperature lower than the decomposition onset temperature. Finally, the ablation phenomena usually lead also to the surface recession of the ablative heat shield. Char-forming ablative heat shields are able to dissipate a considerable amount of heat through several physicochemical phenomena, such as chemical reactions, vaporization, and sublimation. The pyrolysis and the thermic reaction of the polymeric matrix absorb part of the incoming heat, while pyrolysis gas flows through the surface and reduces the incident heat flux in the boundary layer. The state-of-the-art of ablative materials for re-entry vehicles is represented by PICA, phenolic impregnated carbon ablator. It is a lightweight ablator using a commercially available carbon fiber preform, partially impregnated by phenolic resin. For example, both the Mars 2020 and Dragon are protected by PICA-based heat shields. The European version of PICA is Asterm. Asterm is a lightweight carbon phenolic ablator developed by Airbus, and it represents the European state-of-the-art. Anyway, more or less 13 years ago, our research group participated in collaboration with Thales Alenia Space to an European Space Agency project aimed to develop an alternative ablative material for re-entry vehicles, able to withstand moon-to-Earth re-entry conditions and with a very low density. Considering the mission requirements, the family of lightweight carbon phenolic ablators was selected, and we started to develop an alternative PICA-like European ablator. The developed material was tested in the plasma wind tunnel of the German Space Agency, able to reproduce an environment consistent with the atmospheric re-entry condition. The control of the surface recession rate is a critical factor for the ablative materials, and the first test at 6 megawatt per square meter was a success with a uniform recession and a good thermal protection provided by the ablative material. Anyway, the second test performed at 13 megawatt per square meters was characterized by a very fast surface recession, leading to a catastrophic failure of the sample and also of the holder. Then we started to think about the control of the ablation rate. And we started to design nanocomposite ablative materials. In the ablators, the surface recession is related to the stability of the external charred layer. So the first idea was to increase the mechanical properties of the char layer in order to reduce the mechanical ablation contribution. For this reason, we introduced ceramic nanoparticles in the phenolic matrix, and in particular, zirconium oxide nanoparticles were selected as nanofillers because of their very high melting point, thermal stability in oxidizing environment, and low thermal conductivity. Nanoparticles are modified by surface functionalization and then dispersed in the phenolic resin by an ultrasonic probe. The carbon felt is then infiltrated by the modified resin and then cured by a slow multi-step thermal treatment. On the right, the good result in terms of nanoparticle dispersion is shown. The mechanical properties of the virgin nanocomposite ablator were evaluated and compared to the standard carbon phenolic material. The ablator, modified by 5% in weight of nanozirconia, shows an increased flexural strength and elastic modulus. But more interesting results were obtained from the mechanical characterization of the charred materials. Also in this case, the introduction of 5% of nanozirconia leads to a remarkable increase in the mechanical properties. This comparative graph shows that nanomodified charred material has a stress-strain curve similar to the standard virgin material. The second approach investigated to stabilize the surface recession was the protection of the carbon fibers by the deposition of a ceramic nanocoating in order to limit both the sublimation and the oxidation of the carbon. It is very difficult to homogeneously coat the fibers of the carbon felt, especially in the inner part of the carbon preform. And for this reason, a layer-by-layer deposition process of zirconium oxide was selected, the so-called atomic layer deposition technique. The ALD deposition process for the carbon felt was designed, optimized, and performed at the University of Brescia, and in particular by the Professor Laura Borgesi. The atomic layer deposition is a layer-by-layer chemical vapor deposition. The first reactant compound inserted in the deposition chamber covers the substrate surface with a monolayer. The second compound is then inserted in the chamber and reacts with the first compound, creating the first coating monolayer. The repetition of the deposition steps leads to the layer-by-layer coating growth on the carbon fibers. The modified preforms were then infiltrated by the phenolic resin, and the standard curing step was performed. The following micrographs show the carbon felt fibers that are coated by the zirconia nanofilm. In this picture, a detached part of coatings permits to evaluate the nanometric thickness of the film. All the developed ablators modified by both nanoparticles and nanofilms were evaluated by an oxyacetylene torch exposure test according to an ASTM standard specific for the ablative materials. The test facility was completely developed by Sapienza Research Group. And this is the sketch of the facility. The incident heat flux is measured by an heat flux sensor. The sample surface temperature is measured and recorded by a two-color pyrometer and by a thermal camera. The sample back temperature is measured by thermocouples. The samples were tested at a heat flux of 4 megawatt per square meters for an exposure time of 60 seconds. The surface and back temperature trends show that the presence of the 5% of nanoparticles leads to the maximum thermal insulation, even higher than samples modified by atomic layer deposition. And in particular, the higher content of zirconium oxide dramatically reduced the surface recession. The post-test analysis highlights the presence of a continuous zirconium oxide shell only in the samples containing the 5% of nanoparticles. Both the samples modified by 2% and by zirconium nanofilm show the presence of ceramic islands on the surface, but the amount of zirconia seems to be not sufficient to create a continuous and uniform ceramic shell. On the basis of these results, the samples modified by 5% of zirconia were selected for a plasma wind tunnel test campaign at the von Karman Institute of Brussels. The high enthalpy plasma flow exposure tests were performed at an heat flux of 4 megawatt per square meters and for a test time of 70 seconds. This accelerated clip showed the surface recession of the sample during the test in the von Karman facility. It is very interesting to compare the surface recession of the standard samples with the behavior of the modified ones by nanoparticles. The picture clearly shows the lower surface recession for the modified ablators. The surface post-test analysis of the standard samples clearly shows the presence of spike-shaped and damaged fibers on the surface, probably due to oxidation phenomena. While the sample modified by zirconium nanoparticles seems to be almost completely covered by a ceramic shell, and the carbon fibers are less damaged than the standard sample. Finally, it is interesting to compare the performance of Sapienza ablators with the Asterm performance. Asterm is the state-of-the-art European lightweight ablator, developed by Airbus. The table shows a remarkable reduction of the recession rate in the samples modified by zirconium nanoparticles. Okay, and now just a few words about the work in progress. We are evaluating also the properties of ablators modified by different nanoparticles. For example, magnesium oxide and silicon carbide. Preliminary results of oxyacetylene torch exposure tests show interesting back temperature reduction in samples modified by magnesium oxide. And moreover, a completely different behavior of the nanoparticles exposed to the heat flux can be highlighted. Anyway, these results need to be better analyzed and evaluated. To finish, Sapienza University started a partnership with Aviosonic for the development of DECAS thermal shield. What is DECAS? DECAS is a debris collision alert system, a sort of flight data recorder that can be mounted on any space vehicles, including satellites, launchers, and planes. In case of fragmentation in atmosphere, DECAS will survive and communicate the position and the evolution of the debris using an emergency message. It is clear that for DECAS, the thermal shield is a very critical component. And thanks for your attention.
Okay, many thanks to Giovanni for his very clear presentation. I'm looking at the Q&A in the chat, but it seems there is no question. I've got just one, if it's possible. And what about the cost of your system? Are they comparable with the commercial system, or do you think that there is something more that needs to be done to make something competitive?
Yes, it's not so easy to compare the costs of this type of material because obviously the other materials, for example, Asterm, that is the European state of the art, is not a commercial material that I can buy in the Airbus shop. Anyway, this type of materials, the carbon phenolic materials, are quite interesting, Asterm, but also because the raw materials are very common materials, because the standard carbon preform is essentially thermal protection for furnaces, and the matrix that is used is quite standard phenolic resin. So the value is the process, okay? The infiltration process, the addition and the management of the nanoparticles, but the raw materials are not so expensive. So I think that probably the costs in this case not a big issue.
Okay, perfect. Very, very good. So if there is no other question, I don't see any in the Q&A. I would like to thank you once again, and I think that we can move to the next speaker. He is Marco Sebastiani, that is Associate Professor at the University of Rome 3, and the title of his presentation, seeing that Marco is here, I cannot see him, but should be connected.
Can you hear me?
Okay, now I can see you.
Hello?
Okay, the title, yes, I can see you now. So the title of the presentation is Recent Advances of Nanoscale Mechanical Testing Methods in Nano-Architected 3D Printed Materials. Okay, the stage is yours.
Hello, thank you for the invitation. This is Marco Sebastiani from University of Rome 3, and today I'm speaking about recent advances of nanoscale mechanical testing methods for nano-architected 3D printed materials. This is mostly the work of my PhD student, Edoardo Rossi, in collaboration with Jens Bauer from the University of California, Irvine. Let's start with some motivations for this work. You probably all know the relevance of the development of lightweight yet strong materials for a wide range of industrial applications. The most easy to understand is how much we could save in terms of fuel consumption and pollution if we could develop novel lightweight material, strong materials for aeronautical application. And this is becoming even more relevant given the recent guidelines of the European Commission in terms of the European Green Deal. This challenge becomes very clear if we look at the strength versus density plot. If you look at the all natural materials or human-made materials, you see that we can either have very strong but heavy materials or lightweight but weak materials. And if we also consider the theoretical limit for strength, which is given by the atomic bonding, you can see that there is actually a region which is very large, since this is a log-log plot, that can be filled by the development of new ideas for novel, lightweight, yet strong materials. One of the possible solutions is given by the combination among material science with additive manufacturing technologies and architectural design to form 3D printed nano-architected metamaterials, in which you can explore different architectures at the micron and nanoscale to obtain unprecedented increase of strength and damage tolerance of the materials. You can see an example here of a very latest article where you develop the so-called tensegrity nano-architected metamaterials to have a strain delocalization during the mechanical loading, in which you can achieve a full recovery after unloading and a very high level of specific strength and stiffness. You can also apply post-printing processes to obtain coated structure or even hollow structures. So how to make such nice architectures, microarchitectures? One possibility is to use the two-photon lithography direct laser writing technology, which is a microscale or sub-microscale 3D printing technique that uses a UV-sensitive photoresist which comes into interaction with a femtosecond pulsed laser, which is focused in a specific location of the photoresist. And thanks to this two-photon absorption principle, you can achieve resolutions in the printing process below 100 nanometers. And finally, the material that you get is an acrylic polymer similar to PMMA. Then you can also use post-printing processes to obtain ceramics, metals, or even hollow structures, in order to further increase the strength and stiffness versus density ratio. In this presentation, we will focus on one specific process, which is given by the combination between this two-photon lithography printing, followed by a pyrolysis process to get and to obtain a glassy carbon nanoceramic, and then atomic layer deposition coating on top of this ceramic in order to obtain a composite structure with improved properties. The combination of printing and post-printing processes finally leads to a hierarchically structured nano-architected material, in which you have microstructural features ranging from nanometer scale of the atomic layer deposition coatings to the micron scale dimension of the individual elements of the architecture, finally going to the unitary cell of the architecture, in this case a stretching dominated octet truss, and the final structure. So how to optimize, how to face this multi-scale material problem? One possible approach is architecture and mechanical design, in which you select the best architecture in order to obtain optimization of the stress, strain, and damage distribution. But the most interesting for us aspect is using the material size effects to increase the strength of the material by reducing the individual dimension of the dimension of the individual features, or to increase the fracture strength by reducing the size and reducing the probability of having a flow in the material. Or finally, you can work on the surface engineering, so optimizing the adhesion between layers, optimizing the residual stress in the surface coating in order to improve the crack propagation resistance. These are just a couple of examples of the potential applications. So starting from the initial developments in micro-optics, photonic crystals, now there is a huge research in the fields of tissue engineering, pharmaceutics, but also new battery electrodes and microfluidics. So there is a very large variety of potential applications, but the main gap is still represented by the scaling up of this technology. And one of the main obstacles is that the behavior of this structure and these materials under different environmental conditions is not known at all. As an example, how is the behavior in the humid or water environment, and so on. On this basis, there is already a very large and wide literature in which people have tried to solve the gap that I showed you at the beginning of the talk. And you can see they were very successful. So there are different possible solutions, different geometries, different materials, different combination between materials and surface coating. And you can see that if you plot the compressive strength versus density, there are solutions that arrive to touch the theoretical limit of strength for the materials. This is one example. This is the example of a plate octet truss structure, and you can see that the material is very, very strong, and there is also a very good deformability before failure. Anyway, the material still remains quite brittle. This is a pyrolyzed glassy carbon ceramic. So from the literature, it seems that the strength is well optimized, but there is still something missing for the scale-up of these materials. What is missing? It's missing that toughness and structural reliability are still far from meeting the industrial requirement. It is now clear that the major obstacle against the scale-up of these new class of materials is represented by the increase of functional longevity, robustness, and resilience, mostly because the strength is not the only parameter. What about the toughness, the crack propagation resistance, the reliability? And also, in addition, the effects of the coatings that are put on top of these structures on crack propagation mechanisms are not understood. Also, the effect of the residual stress of these coatings is not known at all. And the environmental effects on mechanical behavior are not well understood. So the objective of this work on this basis is to investigate in detail the material science problems related to the fracture toughness of these 3D printed nano ceramics by using novel nano indentation testing methods, to investigate the effect of surface defects and testing humidity on the toughness, and then also to investigate the effects of conformal coatings on crack propagation mechanisms. So what we did, we decided to study the fracture toughness of these materials by printing a large series of micro pillars. The pillars were printed by 2-photon lithography followed by a pyrolysis in order to obtain this glassy carbon fully amorphous material. You can see it from the FIBSEM cross-section. And then on half of the produced pillars, we deposited alumina coating by standard process parameters atomic layer deposition. And in this way, we could study the mechanical properties of the pillars with and without the alumina coating. But more importantly, we found that some of the pillars were apparently free of any surface flows. Some others presented some imperfections coming from the printing process on the pillars. So what we did practically is to make a standard nano indentation and a novel method called micropillar splitting to measure the fracture toughness in different environmental conditions. We did it in vacuum, using our in situ nano indenter, and we did it in different humidity levels by using a customized nano indentation system. So how to perform fracture toughness measurement on micro elements like the one under investigation in this study? In ROMA3, in our team, we developed a method called pillar splitting, which is based on nano indentation testing. So you start by producing pillars. You can make it by focused ion beam milling, or you can make them by 3D printing, by additive manufacturing, as in this case. And you do a sharp nano indentation at the center of these milled or 3D printed micro pillars. And then you measure the low displacement curve until you reach the failure of the pillar. You can see here one of the pillar that was split. And this is the example of the test we made by our in situ nano indenter inside the scanning electron microscope. And then you record the critical load, and we proposed an equation to correlate the critical load for splitting to the fracture toughness of the material and the radius of the pillar through a coefficient gamma, which is calculated by cohesive zone finite element calculations. So all the details on this method are reported in our previous articles. And these are the measurements that we made on our 3D printed glassy carbon micropillars. So you see here, this is a cube corner indenter, and then we used this in situ nano indenter to make measurements inside the SEM. And this is a video of the failure of this pillar. So you see now we are pushing the indenter in the pillar until you reach the critical load and you have the failure of the pillar. And then we use this equation to calculate the fracture toughness. As I told you, these measurements were made in vacuum inside the SEM, and then we made additional measurements at different levels of humidity using the same nano indenter, but in an environmental chamber with different testing humidities. So let's start with the results on the pillars without the ALD coating. This one is our nano indenter that we put inside the glove box in order to control the humidity. And if we look at the standard nano indentation testing, you can see here a series of nano indentation imprints on the top of one of the pillars. You see that mostly there is no effect of the humidity on the hardness and elastic modulus. So it seems that the mechanical properties are not really affected by the testing humidity, especially when you do measurement of the static properties like modulus and hardness. On the contrary, we observed a relevant effect of testing humidity on the crack propagation resistance. And in particular, we observed up to 35% reduction in the fracture toughness for high humidity conditions. And there is also a secondary effect if you look at the data. So not only the average value of the splitting load and then the fracture toughness is much higher at low humidity, but also the scattering of the data is much lower. So you can see there is a large data scattering for a high humidity condition. And we think this is the effect of the surface flows that interact with the growing crack during the indentation in order to reduce the fracture toughness. To check these, we have separated the data on the pillars without surface flow, which are the data in red and green, and the data with the presence of surface flows, which are the ones on yellow and blue. And you can see that when you have surface flow, you have always a reduction in the fracture toughness, but this reduction is probably not very significant for low humidity and becomes very important when you go to high humidity levels. So this really suggests that the flows and the water diffusion through the flows in high humidity conditions can have an effect on the fracture toughness of these glassy carbon amorphous nanoceramics. And here is a sketch with a possible interpretation of the data that we are observing. So when you have a pillar and when you are doing the indentation, you have a crack which is nucleating and growing inside the pillar. And then you have some surface porosity or nanoporosity or some surface cracks through which you can have liquid diffusion in the situation of high humidity conditions. This liquid diffusion and the associated diffusion zone can generate growth of cracks and an additional stress field in proximity of the diffusion zone that interact with the crack growing in the material during the indentation and promote early failure of the pillar. How we know that the crack geometry is like this? We made some FIB cross-section in one of the pillars before the splitting, and you can see this is a three-dimensional reconstruction of the crack. You can see that really you have a median crack in between and you have ring cracks on top. So it seems that that controlling of the surface flows distribution can be the key aspect for upscaling of these materials in terms of upgraded and improved reliability. And finally, let's go to the effects of surface coating, alumina ALD coating on the fracture toughness. The results actually are very interesting. So here for comparison, I just give you the numbers we get without the coating for the defective pillars. And as we observed before, there is a decrease of toughness for higher humidity. This is not happening in case of alumina coated samples. So the fracture toughness becomes independent on testing humidity. However, there is also no beneficial effect on the toughness. The toughness is not increasing after the addition of the alumina coating. We simply cancel the effect of humidity, which already is a good result. So the question is why the alumina coating is not so beneficial for the crack propagation mechanisms. Probably the explanation is the residual stress. Looking at the literature, the alumina ALD usually is in tensile residual stress. So we were searching for a method to measure the residual stress in these materials, and actually we have it. In Roma3, we developed a method called the FIB DIC, Focused Ion Beam Digital Image Correlation method, in which you can locally measure the residual stress by milling out some volume by FIB and then measuring the relaxation strains after that. I have no time to explain this method, but there is a paper to look for it. And by doing so, we found actually that the alumina coating is in tensile stress. So that's why we see a beneficial effect against the humidity effect, but we don't see an effect on the increase of change of fracture toughness after coating. Finally, the conclusion. So we found that fracture toughness in additively manufactured nanoceramics is a surface-dominated characteristic. where the imperfections coming from processing, from printing, can have a paramount effect on the mechanical reliability. And so we can conclude that toughening of such materials, such nano-architected metamaterials, will need to have a strong focus, stronger than on bulk materials, on surface effects like the found capillarity embrittlement. So to this aim, the design and production of conformal nanocoatings with designed and tailored residual stress seems to be a key factor for increasing the functional longevity of such materials. And with this, I thank you all for your time and attention, and I will be happy to answer your questions.
Okay, Marco, thanks. Very nice presentation. I'm looking at the Q&A section, but there is no message there. I don't know if there is someone that wants to do any question. Otherwise, I've got one. Is about very interesting, but do you think that this technique can be applied to any material, or there is any constraint when you change material that is printed?
Yeah, this is thank you. This is a very relevant question, because the printing process actually is related to a restricted range of photoresists, and so you can print only some types of polymers. But there are some post-printing processes that, as the one we applied in this work, that allows you to obtain ceramics. There are other processes that allows to obtain metals or hollow structures. So this is one of the main routes of research in this field, because I can say that the range of materials is quite limited so far. So there is a huge research needed. Now there is people working trying to print biological materials or soft materials, even softer than the polymers that we are now printed. So the range is still quite limited, but there is a lot of activities ongoing to expand this possible range.
Okay, very good. I think there is no question from the audience, because I cannot see any in the chat. So I really thank our speaker, and I leave the stage for the next session chair with Marco Ornellese and for the other speaker. Okay, thanks to all. Bye.
Okay, thank you, Gianluca, and good afternoon, everyone. So we move to the third presentation of this afternoon, given by Jacopo Tirillo, University di Roma. And the title of this presentation is Hierarchical Fibers to Tailor the Fiber Matrix Interface in Composite Materials. So please share the screen. Perfect.
First of all,
it's perfect.
Thank the organizing committee for giving me this opportunity to share with you the latest results of my research group. My talk will address one strategy to improve the interfacial adhesion in polymer matrix composites, which is based on the hierarchical fibers. The results will be presented for battle fibers, but it is a strategy that can be used with other reinforcement as well. We use battle fibers because it is considered a natural fiber of mineral origin with mechanical properties similar to glass fibers. From a global market estimation, today 90% of composite materials are made using glass fibers. These fibers present a problem in the recycling process, which is why several studies are focused on replacing synthetic fibers with natural fibers, such as basalt ones. However, basalt fibers exhibit poor interfacial adhesion when used as reinforcing material in polymeric matrices. For this reason, this research work is focused on studying the surface modification of unsized basalt fibers for the optimization of interfacial adhesion with polymer matrices. This work is divided into 4 parts. The first 3 describe the different surface modification strategies of basalt fibers, while the 4th and last part is their comparison. The first part is referred to the zinc oxide nanorods. Here you can see the hydrothermal process performed on 2 different substrates, basalt fabric and single basalt fibers, consisting of 3 steps. A first step of cleaning the material through ethanol. In the second step, a solution was used to place the zinc particles on the surface of the fibers. On the right side of the slide, you can see the solution used. The last step in the growth of nanostructure through a growth solution, 3 different times were used for each substrate at constant temperature. The scanning electron microscopy analysis proved that the best results were obtained for the longest times, that is, 5 hours for basalt fabrics and 2 hours for single fibers. Let's start with analysis carried out on basalt fabrics. From an X-ray diffraction analysis and transmission electron microscopy, it was verified that all diffraction peaks can be indexed to hexagonal Hursited zinc oxide and no diffraction peaks of any other compounds are detected. All the nanostructure present on the fiber were associated with the zinc oxide nanorods. Other properties of the modified fibers have been studied, such as wettability, showing that the presence of zinc oxide increased the hydrophobicity of basalt fabrics up to 116 degrees. And also the photocatalytic activity, showing that the modified fabric eliminated 37% of the pollutants in solution after 8 hours of testing. Considering the single fibers, first tensile analysis was carried out. This showed a slight decrease in tensile strength after the hydrothermal process, likely due to handling the fibers. Then the viable distribution confirmed the validity of a unimodal viable function. A single fiber pull-out test was performed to evaluate interfacial strength. In the graph, you can see the comparison between the bare fibers and modified fibers with zinc oxide nanostructures. As you can see from the table, the apparent interfacial shear strength is increased by about 16%, having however the total work of extracting the fiber from the matrix. This means that thanks to a mechanical interlocking between the nanostructures and the matrix, a higher strength was reached, but once the bond between them was broken, it was very easy to extract the fiber. Unlike bare fibers, where the presence of surface roughness allowed higher friction during extraction and therefore a higher total work. So, there was a poor chemical bond between the zinc oxide nanostructure and the fiber surface. This was also confirmed by the scanning electron micrographs after pull-out test. The limited amount of zinc oxide nanorods present on the fiber after the pull-out test demonstrates that once the maximum forms was reached, all the nanostructure remained stuck inside the epoxy matrix and were easily detached from the surface of the basalt fibers. Subsequently, dynamic contact angle tests have shown an increase of 30% of the dispersive component of the total surface energy, and this makes the material more compatible with polymeric matrices compared to bare fibers. The second part is referred to the plasma polymerization via plasma-enhanced chemical vapor deposition. In the first table, you can see the setup used for the plasma process as a function of power, time, and pressure, while the second table shows the 6 different sizing mixture used to deposit a thin polymeric film on the surface of the fibers. The SPS analysis clearly show an increase in the intensity of carbon and oxygen related peaks. As already demonstrated in the literature, the increase of these elements is proportional to the increase in the percentage of oxygen in the deposited tetravinylsilane oxygen mixture. During the polymerization process, the oxygen atoms were incorporated, forming a silicon-oxygen-carbon network. The presence of a polymeric film was also verified through a scanning electron microscopy analysis, making small cuts on the surface of the fibers. Also in this case, single fiber tensile tests were carried out. The result showed a slight increase in mechanical properties, confirmed the theory that the presence of polymer films on the surface of natural and synthetic fibers can heal the main surface defects. The pull-out test on the different families have shown that the best results was obtained for the mixture with 52% oxygen with an increase in the interfacial strength of approximately 80%. The fact that fibers treated with the tetramethylsilane with 52% oxygen mixture perform better than fiber treated with 71% oxygen can be explained by the significant increase in the concentration of carbonyl groups due to the large amounts of oxygen on the fiber surface. Recent studies have shown how carbonyl groups can be responsible for the decrease in shear strength, preventing the formation of surface covalent bonds. For better understanding, an interlaminar shear strength test was performed to evaluate the interfacial strength between the nanocoated basalt fibers and the polyester matrix. In this case, an increase of 144% was obtained. This is the result in the formation of numerous silicon oxygen-carbon functional groups on the fiber surface which are essential for improving interfacial adhesion. The dynamic contact angle test showed that for all the different formulation of treated basalt fibers, there is an increase in the dispersive component of the surface energy, ranging from 73% to 92% for the fibers treated, with a mixture of pure tetramethylsilane with 52% of oxygen, and tetramethylsilane with 71% of oxygen, leading to a better compatibility of these materials with apolar lipids, as in the case of apolar polymeric matrices. The third part is referred to the carbon nanostructures. We first performed a dipping step using 3 different catalysts based on iron, sodium, and copper. The table shows the molarities of the solution and the immersion times. Then the fibers covered with the metal catalyst were subjected to the reduction and growth phase inside the tubular chamber. In this case, the process time and temperatures have been changed. Therefore, not considering the nanotubes obtained with the iron-based process, we can see the sodium hydroxide and copper. We obtained the best configuration with a process with a copper-based catalyst at 300 Celsius degree for homogeneity of the surface coverage and size of the nanostructures. To study the morphology of the obtained nanostructure, Raman and transmission electron microscopy analysis were performed. As can be seen, the iron-based catalyst is the only one that has made it possible to obtain carbon nanotubes with well-ordered graphitic planes. In the case of the process with sodium at 480 Celsius degree, we can see shorter and amorphous structures, while with the copper catalyst, longer or helical-shaped structure have been obtained, with a bamboo structure in the case of 480 Celsius degree and amorphous at 300 Celsius degree. Knowing the bad influence of high temperature on the mechanical properties of a basalt fiber, tensile tests were conducted in parallel. In fact, a strong decrease was found for the process at 650 Celsius degree with an iron-based catalyst, while the decrease with the sodium-based catalyst is due to the chemical interaction between a strong base, sodium, and a predominantly acid structure like basalt. The process with a copper-based catalyst at 300 Celsius degrees was able to almost completely preserve the original mechanical properties of the fibers. This process also showed the best results in interfacial adhesion properties, with a 30% increase in apparent shear strength and a 60% increase in total pull-out work. This behavior can have 2 explanations. The first is the increase in the surface area thanks to the presence of helical structure, and the second is the presence of catalyst particles incorporated in the nanostructure. As also explained in the literature, if the catalyst particles are not found on the surface of the fiber and the nanostructure, a stronger bond is obtained between the fiber and the nanostructure. In the end, and I will show you a comparison of 3 different approaches. All 3 surface modification processes proved to be effective in modifying the basalt fiber surface. zinc oxide nanorods, plasma coating, and carbon nanostructures. Then, comparing the tensile test on single fiber. The process with zinc oxide or carbon nanostructures led to slight losses of the mechanical properties of the fibers, while the plasma process showed an increase of up to 20% in the case of the mixture with 52% of oxygen. The study of the interface between the modified fibers and an epoxy matrix showed increases for all three processes: zinc oxide, copper growth, and tetravinylsilane. It should be noted an important increase in the total pull-out work in the case of carbon nanostructures, as well as an increase in the case of the plasma process for the upright interfacial striate strength. These results are a demonstration of a good chemical bond between the basalt fibers with the applied nanostructural sizing, as is also demonstrated by the residues on the fibers after pull-out test. In conclusion, all the treatments described in this research work have shown to be effective in the surface modification of basalt fibers, grafting homogeneous thin layers of polymer sizing or homogeneous layers of nanostructures. The optimization of the techniques was obtained with the growth process at the highest times for zinc oxide nanorods, with the deposition of the mixture tetravinylsilane with 52% of oxygen for the plasma polymerization process, and finally for the growth process of the carbon nanostructures using a copper-based catalyst at 300 Celsius degree. The plasma-enhanced chemical vapor deposition techniques was the most interesting in terms of results, proving to be a highly effective technique for surface modification of fibrous substrates, with 20% increase in tensile properties and 80% increase in interfacial adhesion with polymeric matrices. With regard to future perspectives, we should try to optimize the chemical bond between the surface of the fibers and the nanostructure, which is the main critical point. As for the plasma strategy, it is necessary to address the influence of the power of the plasma used as a function of deposition times and percentages of oxygen, considering the use of different silane precursors. It is also important to consider all the additional functionalities that will allow these materials to be used in other fields than the structural ones, while moving to an industrial scale-up of these treatments. I would like to thank all the partners and all of you for your attention.
Well, good presentation, Jacopo, and no questions coming from the chat and Q&A. So if someone in the audience want to ask a clarification. Also, nothing is coming on the chat. I have just a curiosity. Maybe I lost the details in the initial part. What about the dimension of your fibers, length and diameter? I lose this point. Maybe you have the microphone off, Jacopo. Can you hear me? Can you hear me, Jacopo? I cannot hear you. I don't know if it is only my problem. No. Is your microphone on or not? Well, I hope that the other one are listening to your answers.
No.
Okay. Okay. Now yes. Okay, perfect. Jacopo, you understand my question, my curiosity? Yes? Sorry, but maybe it's a problem of my connection. I do not hear from you. Okay, 13 microns. Thank you very much, Jacopo. Thank you. Okay, no other questions are coming, both in the chat and in the Q&A section. So I thank again Jacopo for your presentation, and I introduce the next talk by Francesco Fagnani from the Università Statale di Milano. The title of the presentation is Two Appealing Families of Cyclomethanolate Platinum 2 Complexes for Solution Processable OLEDs with a Tunable Emission. It is a pre-registered presentation, so We will meet in 15 minutes.
Good afternoon. My presentation deals with the two appealing families of cyclometallated platinum-2 complexes for solution processable OLEDs with a tunable emission. At first, a brief introduction of luminescence. When a photon with the proper energy hits a molecule, this molecule can go from the fundamental state to an excited state. This excited state has a higher energy. Then the molecule will lose its excess energy through many photophysical pathways, which can be both radiative or non-radiative. The Jablonski diagram shows these possibilities. We have a fundamental state called S with 0, which is a singlet state. Upon excitation, the molecules can reach another singlet state, which is at higher energy. The emission of radiation from this S with N state is called fluorescence. Another possible process is the intersystem crossing from the singlet excited state to a triplet excited state. When emission of radiation occurs from this triplet state, we have phosphorescence. Then we move to OLEDs. OLEDs are the result of the research in the field of electroluminescent materials. These devices are based on the direct excitation of organic semiconductors by means of electricity. OLEDs present different advantages. For example, the displays are thinner and lighter, no back illumination is required, the light is emitted only by the needed pixels, and these consequences also bring about an energy saving going from 20 to 80%. OLEDs have the following components. The anode, which is formed by a transparent conductive material, for example, indium tin oxide, a cathode made of a metal, and between the electrodes, an organic layer which emits light. How an OLED works? The electrodes pump electrons and positive holes on the opposite surfaces of the organic layer. Then these electrons and holes migrate through the organic layer and arrive at the interface. At the interface, they recombine, forming excitons. Finally, these excitons can decay in a radiative way, emitting light. On the right, we have a general structure of an OLED device. Transition metal complexes can be particularly important for OLEDs, since the presence of the metal atom provides interesting luminescence properties. We have the so-called heavy atom effect, which is at the basis of an efficient intersystem crossing which populates the triplet state from the corresponding singlet excited state. From this triplet state, the radiative emission can occur. As a consequence, the absolute emission quantum yield can reach very high values, up to 100%. And so these molecules can have useful applications for the production of OLEDs. An example of this class of compounds is the NCN-based complexes of platinum-2. On the right, we have the general structure of these complexes. We can observe the third dentate ligand, which is a dipyridyl benzene, which can also bear a substituent called R on the central benzene ring. Then we have the platinum, and finally an ancillary anionic ligand, which is white. These molecules present a rigid structure around the platinum complex, and this rigidity of the coordination environment allows for the efficient radiative decay from the excited state. In particular, the other important characteristic of this family of compounds is the possibility of use them in solutions of dichloromethane or similar solvents, since they have a very high solubility in these solvents, and moreover, they can be sublimed to produce pure layers of compounds. So by sublimation or by using dichloromethane solution, we can obtain OLEDs. Starting from three well-known complexes of this family, which present a chloride as ancillary ligand and a mesethylethionine or a methyl group on the benzene ring, we obtain the substitution of the chloride with two different thiolates. In red, we have the phenyltetrazole thiol, and in blue, the phenylthiazole thiol. From the three starting complexes with the two new thiolates, we obtain 6 new complexes. The synthesis of the ligands involved cross-coupling reactions. In the first case, for ligand 1, we started from tribromobenzene and performed at first a Suzuki-Miyaura coupling, and then a Stille coupling to give the NCN third dentate ligand. In the second case, we also started from tribromobenzene, and we employed the Stanil derivative of thiophene and pyridine to obtain ligand 2. In the third case, we started from the bromotoluene, and with the tributylstanil pyridine, we obtained ligand 3. Then the complexation involves the use of potassium tetrachloroplatinate as a source of platinum to give the three corresponding complexes PTCl1, 2, and 3. Once these complexes have been obtained, the substitution occurs through the sodium salts of the 2 different thiolates, and we have the labels for the 6 complexes. These complexes have been characterized starting from their chloromethane solution. We have performed both absorption and luminescence measurements. In particular, PT1, PT2, and PT5 are very interesting because they have a very high quantum yield after the freeze pump thaw procedure, reaching values up to 90%. The freeze pump thaw procedure was required since the emission of these compounds occurs from the triplet excited state, and the oxygen present in the air and also in solution has a fundamental state which is a triplet, so it is able to efficiently quench the emission from these complexes. So the procedure is able to remove the oxygen from the air and from the solution to give a real value of the quantum yield. Then the complex PT1 is particularly interesting for the luminescence properties, so we studied it deeply. The quantum yield is 4.7% before the freeze pump thaw procedure and 89.9% after it. We have the structure of the molecule and then the absorption and emission spectra in solution of dichloromethane. We can observe that the emission occurs in a range of wavelengths from 475 to 750 nanometers. In particular, it has peaks in the yellow and green region of the spectra. This complex has been used by Dr. Massimo Cocchi from CNR of Bologna for the production of OLEDs. He produced 3 different OLEDs with different amounts of the platinum complex in the emitting layer. We have the emission spectra of the 3 OLEDs. In the first case, we have an 80% amount of platinum complex in the emitting layer, and the emission is the green plot, so in the green region of the electromagnetic spectrum. Then we can observe that the higher the amount of platinum, the higher the presence of aggregates. The presence of these aggregates shifts the emission towards the red region and the near infrared region of wavelength. In particular, these complexes have a square planar coordination geometry and so can efficiently form dimers or in general aggregates. This interaction between the molecules shifts the emission. In blue, we have the plot corresponding to a 25% amount of platinum in the emitting layer, and we can observe an intermediate situation where both monomer and aggregate is present. In particular, the total emission of this emitting layer is in the yellow region. Finally, when we have 100% of platinum in the emitting layer, we have an emission in the red region with a peak at about 750 nanometers. We also obtained the CIE coordinates of these OLEDs. So we have a scheme with the X and the Y coordinates of the precise color of the emission. We also have the photos of the OLEDs going from the 8 to the 25 to 100% of platinum in the emitting layer. The color goes from green to yellow to red, and we observe the exact emission on this scheme. Finally, to conclude, we started from the 3 already known cyclometalated platinum-2 complexes and obtained 6 new compounds by substitution of the ancillary chloride ligand with 2 different thiolates. These complexes have a very high quantum yield, up to 90%, and are very soluble in solvents such as the chloromethane. So these characteristics allow for the efficient use of them in solution processable OLEDs. Because of the luminescent properties of these compounds, the emission color of the device can be tuned on the basis of the amount of complex in the emitting layer. In the future, by varying both the ancillary ligand and the substituent on the central benzene ring, we could expand the range of colors achievable through the luminescence emission. Thanks for your attention.
Okay, thank you, Francesco, for this presentation. Okay, good afternoon, Francesco. So no questions are coming in the Q&A section and no question in the chat. So if someone in the audience have a curiosity or a request of clarification. No, I just try to make a very small, simple question, since it's not exactly my topic of research. So which are the further application of your research, the practical application, if there are some examples? Thank you.
Good afternoon. Do you hear me? Yes. since these complexes are very luminescent and the emission is towards the red part of the visible spectrum, the possible applications are, for example, in bioimaging, in cellular bioimaging, since the emission in that region is very good, since it does not interfere with other emission of the substrate, so of the different parts of the cell. Other possible applications are for OLED and for luminescent devices in general. So it depends on the emission.
Okay, thank you very much. There is a question in the chat. Is there some special reason to choose those species as Y residues?
Yes, some thiolates had already been tested for these complexes, but it was observed that the quantum yields are quite low. So it was sufficiently strange when we observed that the use of one of these two thiolates leads to a very high quantum yield. So the first thiolate was used simply because we already had it in our lab among the many other reagents. Since it was very appealing and successful, we also tried the second thiolate, and the results are also very promising. So at the beginning, we did not understood why it was so successful, but we still do not know. So we simply tried them.
Research in progress, obviously.
Yes.
Okay, thank you a lot. Okay, if no other questions are coming from the audience, I thank you for these two talks, and I leave the chair to Carlo Rezza from the Università dell'Aquila. So if Carlo is there, okay.
Good afternoon. Do you hear me?
Yeah, exactly. Yes.
Okay. I will introduce the next three talks. The first speaker is Alessio Gabbani from University of Pisa. And the title of his talk is Active Magnetoplasmonic with Transparent Conductive Oxide Nanoparticles.
Okay.
The floor is yours. Okay.
Can you hear me?
Yes.
Okay, so I'm gonna share the screen. Yes. Okay. I'm Alessio Gabbani. I'm actually in Florence at CNR and University of Florence, but this research I'm presenting you has been carried out during my previous postdoc at University of Pisa. So it's about active magnetoplasmonics with transparent conductive oxide nanoparticles. So plasmonics is fascinating properties of zero-dimensional particles, which can be applied in several applications. I mean, in surface-enhanced spectroscopies, exploiting the field enhancement around the surface of the plasmonic nanostructure, or it can be exploited for sensing, and in particular for refractometric sensing. So this approach follow the basically the tracking of the plasmonic resonance variation with the refractive index around the surface of the particles. It can be a promising alternative to some commercial refractometric sensors, which are based on metal films, noble metal films, and propagating plasmon. The advantages is there are several. For example, the local sensitivity is enhanced. There's no need to stabilize the temperature, and a simple setup is required at the end. But to improve the performance and reach the values needed for practical applications, it would be desired to achieve an active modulation of the plasmonic response with an external tool. So to explain with a simple sketch this need for modulation, basically you can think that if you are looking for your friend in a crowd, and everyone is shouting and moving, it would be difficult almost impossible. But if only your friend is moving his arms, in this case, it would be more easy to detect him and isolate him from the rest of the crowd. So the basic idea is that you can selectively modulate the plasmonic resonance with a stimulus in order to improve the sensitivity and the detection strategy. And in particular, in magnetoplasmonics, we use a magnetic field as an external tool. It's quite convenient stimulus because it's fast, it is reversible, it is easy to generate and propagate, and you do not need to have a direct contact with the plasmonic material. How does this magnetic modulation work? So to explain this, I need to explain the magneto-optical technique that we use to detect this signal, which is magnetic circular dichroism. In this technique, we detect the differential absorption between right and left circularly polarized light. If you illuminate your nanoparticles with of course, you need a magnetic field, so this differential absorption is measured in the presence of a static magnetic field. If you illuminate your nanosphere with a circularly polarized wave, you can excite circular motion of free electrons in the sphere. This circular motion excited with opposite helicity are degenerate unless you apply a magnetic field. If you apply the magnetic field, you remove this degeneracy and you have an opposite shift of the plasmonic resonance condition in the case of the two helicity. And this can be rationalized as a different Lorentz force, which is experienced by conduction electrons due to the different helicity of light, or the same is if you reverse the magnetic field. So as a consequence, the differential absorption that you measure has this derivative-like line shape. It's important to notice that the magnitude of this peak-to-peak signal is directly proportional to the energy shift between the two plasmonic modes, which can be expressed according to this simple equation. So it's linear with the magnetic field and inversely proportional to the effective mass of the charge carrier, M. So in a previous work by our group, we analyzed a simple dispersion of spherical gold nanoparticles of around 10 nanometers. And we see that we have this line shape in MCD, which has this derivative line shape I already explained, which is centered at the maximum of the extinction peak. If you want to do sensing experiment, you can disperse the particle to just a proof of concept experiment. We can disperse the particle in two different solvents, as this has been performed here on the right. If you look at the extinction peak, you see that the extinction peak moves with the refractive index, but it is much easier to detect these movements, so these changes with refractive index, if you look at the magneto-optical spectrum. So you can follow the shift of the zero crossing line of the MCD curve, or you can fix the wavelength and simply monitor changes in intensity of the magneto-optical signal following the vertical arrow, the red arrow. Unfortunately, for these simple systems, the modulation is weak for application in practical devices. So there is a need for an improvement of this magnetoplasmonic response. We can act on two parameters. Okay, we can improve the magnetic modulation, so the energy shift between the two modes, as is sketched here on the left. So the more shifted are the peaks, and the bigger is the peak-to-peak signal in MCD. But we have to keep in mind that the resonance must be kept sharp, the optical resonance, because in this way, because if it's broadened, we also decrease the peak-to-peak signal in MCD, as is shown here on the right. So what material is desired? So we need to fulfill these three requirements. So the plasmonic response should be maintained sharp, and for this, noble metals are the best. because they have sharp resonance, but they have weak magnetic modulation. So if you go to ferromagnets, for example, a nice work by the group of Professor Vavassori in Spain on nickel nanodiscs has demonstrated the higher magnetic modulation and higher magnetoplasmonic response on nickel nanodiscs. And these materials are able to support a plasmonic resonance and are ferromagnetic. But the resonance is broadened with respect to noble metals, as can be seen here on the left graph. And the same is if you go to hybrid materials. So you can add use a heterostructure with a noble metal part and a magnetic part. The two materials must interact, but also in this case you broaden the plasmonic resonance with the addition of a magnetic metal in the nanostructure. So the great challenge is to increase the magnetic modulation without degrading the plasmonic properties. So to do this, we choose to look beyond noble metals, and in particular to plasmonic heavily doped semiconductors. This is another class of plasmonic material where you can tune, if properly doped, if intensively doped, this material can support a plasmonic resonance. For example, transparent conductive oxide support a plasmonic resonance in the infrared, which is quite sharp. And interestingly, the effective mass of the charge carrier in some transparent conductive oxide can be lower than in noble metals, which, according to this formula, of the energy shift, can increase the magnetic modulation. So we decided to focus our attention on this material, and in particular on indium oxide doped with tin, and cadmium oxide doped with fluoride and indium. In this case, the doping introduced free electrons, and we synthesized through colloidal chemistry approaches two classes of semiconductor nanocrystal, doped semiconductors of transparent conductive oxide, indium tin oxide and FICO, fluorine and indium co-doped cadmium oxide. We obtained quite good monodispersity of the nanoparticles with good crystallinity. And if we look at the optical spectrum, we confirm that we have a resonance, a plasmonic resonance in the infrared. And here there is a comparison with gold nanodiscs. So the comparison of the magneto-optical spectrum immediately tells us that we have a 40-fold enhancement of the magneto-optical response in these two transparent conductive oxide nanoparticles. So this is quite promising. The measurements are done at room temperature and on colloidal dispersion of particles. Why this increase? Of course, because of two reasons. The first is the lower effective mass, which we also extract from the fitting of the optical and magneto-optical response, as is sketched here in this table. So they have lower effective mass with respect to gold, and it's almost comparable between the two semiconductors. But with FICO nanoparticles, we have an increased magnetoplasmonic response, and this can be explained with the reduced line width of the plasmonic peak, which is shown here on the right graph. Okay, so this is very promising material, and we decided to exploit further these materials in a proof of concept refractometric sensing experiment. So we dispersed the nanoparticles in three different solvents with different refractive index. And we look at the optical spectrum first, so we can see that the pitch shifts with the refractive index, and we can estimate the optical sensitivity defined as a wavelength shift divided for the refractive index variation. Okay, so we have also here we have improved performance, slightly improved for FICO nanoparticles, but we also perform a magneto-optical sensing experiment. And in this case, we decide to follow this approach. So if you look at the green vertical line, changing the refractive index, you have a variation, a measurable variation of the MCD signal. And monitoring this variation as a function of the refractive index, we obtain the graph on the right, where we compare this curve with the state-of-the-art material for magnetoplasmonics. So the red curve of FICO nanoparticles is the one with the highest slope. So we have an incredible enhancement with respect to our previous work on gold nanoparticles, and we are also better than the previous works in the literature performed on nickel nanodiscs and even complex architecture with nickel and gold. Basically, we obtain with a non-magnetic material a very promising approach, an enhanced performance. An advantage of this approach that employ magnetic modulation is that you don't need to fit the curve as in extinction spectroscopy, but you just need to monitor a change in intensity of the signal as a function at a fixed wavelength. And it's robust against matrix interference because we only detect the modulated signal, and also if we compare with standard approaches of plasmonic sensing with nanostructure, we can detect diffractive index changes as small as 3.3% to the -5, which is not so far from the performance of standard plasmon-based sensors. So this is a very good starting point for magnetoplasmonics. A further perspective will be to try to dope a transparent conductive oxide with a magnetic cathode. The idea is that if we have an interaction, a magnetic interaction between free electrons and the magnetic cation, we can further increase the magnetic modulation. Of course, also here there is a challenging goal which needs to be overcome, that if you insert the magnetic cation, you also dump the plasmon and decrease the quality factor of the plasmon. So further research will be carried out in this topic. Okay, so that's the end. Thank you for your attention and all the funding institution, and I'm here to answer your question.
Okay, thanks for your contribution, Alessio. It's a time for a couple of questions. I don't see question from chat. Okay. I have a question. Do you observe also high order localized surface plasmons, or only the first mode?
Okay, so in this sphere, no, because we are in the quasi-static regime. They are quite small, 15 nanometers, more or less. So it's just a dipolar resonance.
Okay. Another technical question. The presence of magnetic field breaks the reciprocal symmetry, and so you have the effect. Okay. No, we have also that magnetic field can provide anisotropy response. Do you observe something about anisotropic response, or do you think that anisotropic induced by magnetic field change the response or shift the frequency of surface plasma?
In which, what we are measuring is actually a shift in the a very weak shift in the plasma resonance that can give rise to the signal. So at the end,
okay.
So basically, what do you mean by anisotropy?
I think the direction of magnetic field.
In the permittivity.
Yes, in the permittivity.
The fact just that here is explained with a diagonal tensor, maybe. So you just insert the shift inside the cross section. So it's like you have a peak with it slightly shifted for one helicity in one direction and in another direction for the other helicity, and then you measure the difference.
Okay.
I don't know if I explained or not.
Okay. Okay, and thanks again. Thank you, Alessio, for your talk. Now we have a coffee break, and we will see soon. We have 15 minutes for this break.
Four high-tech companies, each an expert in the field of materials characterization, have come together to create something special. Our merger into one company creates immediate and clear benefits, leveraging our strong brands, highly skilled employees, and trusted technologies. Our mission is to create superior customer-focused solutions and services, and to deliver tangible economic impact through chemical, physical, and structural analysis of materials. Our name, Malvern Panalytical. www.malvernpanalytical.com.
A very warm digital welcome to you all. At Malvern Panalytical, we are big on small in many ways. Today we are presenting live from inside the Malvern Panalytical Application Lab, where we bring you our latest innovation. So sit back and prepare to be inspired as we are powering the next generation of XRD research. Fabio, this is your second time.
Yes.
Last time you were a bit nervous. How are you doing now?
Better. I think last time taught me that I don't have to be scared of you. So it's actually great to see you, because whenever we see you, it means we're bringing something exciting to the market. So I'm really excited to be here today again.
And what we had with the Aris was one very good knife. So what changed in that?
We have now added, and that's what we are now announcing, new scan modes to the Aris platform. From now on, we will also be able to do racing incidents and transmission diffraction. And that makes it a really, I would say, unique tool. Now they can have this instrument where they can continue to do the powder diffraction research, but also add thin film analysis, for example, or transmission scan on pharmaceuticals, for example.
I guess you're not the only one jumping up and down in your seats. People at home will be wondering, what does this look like? How does it work? So let's switch over to Nicholas for the demonstration. That brings us to the very last minute of this event. Anything we urgently need to express before we go out?
I'm really excited that today we have been able to announce these novelties, and also based on the number of questions, really looking forward now starting to work with our customers with these novelties.
Malvern Panalytical proudly introduces the third generation of Empyrean, the most advanced X-ray platform for high-quality structural analysis available on the market. The new Empyrean is the first fully automated multi-purpose X-ray diffractometer. Users can perform a large variety of measurements without any manual intervention. This is possible thanks to the newly designed X-ray optics, the I-core and the D-core. When combined, the multi-core optics bring a new level of automation in X-ray data collection that has never been seen before. With the new Empyrean with multi-core optics, you can prepare batches of different measurements to run overnight or in the weekend, therefore maximizing the usage of your X-ray platform and increasing its efficiency. Training new students to become proficient with more advanced X-ray applications is now much simpler because there is no need to exchange expensive X-ray optics. The I-core and D-core are completely motorized prefix modules, which are now automatically detected. The result is a fully recognized optical beam path. This helps to completely trust the data measured in regulated environments or by inexperienced users. Empyrean with multi-core optics is the only platform on the market that can seamlessly perform 0D, 1D and 2D measurements in a fully automated way, extending once more the dimensionality of your dataset to unravel hidden features of your samples. A large set of template measurement programs for the various applications has been defined to decrease the complexity for the user. These templates can either be used without changes or they can be modified to satisfy different requirements. The new measurement programs, combined with the automated data collection and the possibility to generate automated analysis scripts, provide you with a fully automated solution for your X-ray diffraction measurements. Empyrean, the intelligent diffractometer.
A very warm and digital welcome to you all. Today, we'll be presenting live from inside the Malvern Panalytical Application Laboratory, and we'll share with you our latest exciting innovation.
What do you think? Should
Why
have a
don't
look?
we? Yes.
Great. Then here it is. And voila! This is our new wonder detector. One of the characteristics of this detector, it's a one-dimensional detector or a strip detector. So here it is in all its beauty. I think also by design, our team did really a good job, and you will see it also in the machine, how well it fits, even from an aesthetic point of view.
I would like to invite you to feel free to join the conversation, because this is all about you and your questions.
Let me show you the detector over here. The first thing you see is a color display, and it's touchable. So first what we see here is the previously collected X-ray diffraction signal. Not only that, by touching the screen, I would swipe to different functionality of the interface. For example, I could see the status of the detector currently.
Here, seeing the invisible. Look at this little peak here. It was completely hidden by the noise, by the background here. It starts to be visible, but still doubtful. And there it is in all its beauty. Same here and same in other places. So really you start getting this very weak feature, or what Martijn was mentioning before, these minor phases, they really pop out. And these are very, very important for our customers.
So that's a huge innovation then,
That's a
seeing
huge,
the invisible.
That's correct, that's a huge innovation.
Something.
We really help our customer to get better battery. Actually, we help our people getting better sample, and therefore improving everyone's life.
Thank you all at home so much for joining this session. And for now, thank you. Stay safe and have a great day.
The growing need to characterize and analyze structures in the nanometer range and the complexity of such measurements with various instruments create a demand for automated solutions and advanced correlative analysis. That is why we have developed LightScope, a unique compact atomic force microscope designed for plug-and-play integration into scanning electron microscopes. With LightScope, you are able to merge the forces of the two of the most used techniques for sample analysis on the nanoscale. Measuring with LightScope is intuitive and simple, yet precise and time-efficient. Its integration into the SEM prevents sensitive samples from contamination or oxidation, as the measuring is done in the same place and under the same conditions. LightScope enables precise localization of the region of interest and AFM tip navigation. It extends the capabilities of SEM by measuring a sub-nanometer topography, together with mechanical, electrical, and magnetic properties of the sample. LightScope incorporates a unique imaging technique called correlative probe and electron microscopy, shortly CPEM, enabling simultaneous acquisition of AFM and SEM data. LightScope and the CPEM technology allow sample analysis in a way that was difficult or impossible by the two imaging technologies separately. Together, they bring new possibilities for advanced correlative imaging in a variety of scientific and industrial fields such as material sciences, nanostructures, semiconductors or solar cells industry, life sciences, and many more, defining their own category of the correlative microscopy.
Rigaku, the world's leading analytical X-ray instruments company, offers a highly versatile, state-of-the-art multi-purpose X-ray diffraction system with built-in intelligence guidance. SmartLab SE offers continued refinement of the original ease-of-use SmartLab features that resulted in the prestigious R&D 100 award. SmartLab SE is a highly versatile
Okay, good afternoon again. Now we have the third talk. The speaker is Grazia Politano from University of Calabria. Do you hear me? Okay. Oh, okay. The title of the talk is variable angle spectroscopy and ipsometry of graphene-based fields. Okay.
Hi, I'm Grazia Giuseppina Politano from Università della Calabria. Graphene-based materials are advantageous materials that can be produced in ultra-thin sheet form and may be used in several applications. Graphene-based materials show notable optical properties such as highly transparency in visible spectrum, photoresponse up to terahertz frequency range, and tunable infrared optical absorbance. Variable angle spectroscopic ellipsometry is a highly precise optical method designed for studying the optical properties of materials. Herein, we present a review of the author's research works on variable angle spectroscopy ellipsometry of graphene-based films. The optical study of graphene oxide films electrophoretically deposited on titanium was carried out using VACE, before and after the annealing. The optical models of graphene oxide and reduced graphene oxide films are represented respectively by a combination of 2 and 3 Lorentz oscillators. The figures show the optical constant dispersion curves. These figures show scanning electron microscope images of graphene oxide and reduced graphene oxide on titanium. In comparison with other research works, using this technique, we have obtained higher optical constants. VACE was performed also on graphene oxide deposited by deep coating on magnetron spattered silver. In this figure, the optical constant dispersion curves are reported. The optical model of graphene oxide deep-coated on silver is described using a combination of 3 Lorentz oscillators and a diode-like oscillator. In particular, the oscillator at 3.8 electron volt is attributable to the silver volume plasmon. Remarkably, these films may be useful for hyperbolic metamaterials, as reported in the effective medium theory simulations. Moreover, we report that Raman signals of graphene oxide in such graphene oxide magnetron spattered silver thin films continue to display surface-enhanced Raman scattering activity. Additionally, Raman peaks have been observed, which are dependent on the intensity of the laser and the thickness of silver and graphene oxide films. Deep coating was employed for the deposition of graphene oxide films on magnetron spattered gold thin films. This figure shows the dispersion laws of the samples. In this figure, a same image of the graphene oxide in films deep-coated on magnetron spattered gold is shown. The dispersion model of the samples was described using a combination of 3 Lorentz oscillators. Graphene oxide absorbs mostly in the ultraviolet region. By means of gold magnetron spattered thin films as substrates, graphene oxide absorbs also in the visible region, and the peak of the extinction coefficient is at 3.1 electron volt, which may be described in terms of strong metal graphene oxide interactions. Moreover, we report on the Raman spectroscopic and morphological investigation of silver, graphene oxide, gold structure, where the graphene oxide in film is embedded sandwich between magnetron spattered silver and gold thin films. Enhancement effects occur in the so-called dot spots. In fact, additional sharp Raman modes, sometimes stronger than the graphene oxide typical band, are observed at low laser intensity. They can be related to localized vibrations of molecular groups attached to graphene oxide network. Moreover, same characterization reveals the presence of silver nanoparticles of diameters 40-50 nanometer dispersed in the silver thin film. The optical properties of graphene oxide, thermally reduced graphene oxide, and PSS functionalized reduced graphene oxide films were obtained using a Lorentz oscillator model in accordance with Kramer's Kronig relations. These figures show the dispersion laws of graphene oxide and reduced graphene oxide films on silicon substrates, while this figure shows the dispersion laws of PSS fractionalized reduced graphene oxide films on silicon substrates. The optical study of graphene nanoplates films was carried out using BASE, and the optical model is described using 3 Gaussian oscillators. The oscillator at 3.7 electron volt agrees quite well with the bulk and surface interlayer state of graphite, whereas the oscillator at 2.7 electron volt is attributable to defects, and the oscillator at 1.5 electron volt is in accordance with pi star band of graphite. This figure shows a same image of the sample. The optical properties of chemical vapor deposition grown graphene on silicon were described using 4 Lorentz oscillators. The absorption peak at 4.5 electron volt is attributable to the effects of resonant excitons on the interband transition peak. The oscillator at 2.36 electron volt is linked to the resonant excitonic effects attributable to the electron-hole interaction in the pi and pi star at the M point, whereas the oscillator at 2.8 electron volt is due to the hopping amplitude that gives rise to the direct nature of low-lying excitations. At 0.5 electron volt, a conductive layer with Drude-like electrons is observed. This figure shows the same image of the samples. The optical models of bilayer and trilayer graphene with random stacking orientation obtained by chemical vapor deposition synthesis on silicon are composed of 2 Lorentz oscillators. The oscillator energy at 4.4 electron volt for chemical vapor deposition grown bilayer graphene is due to the peak due to the Fanov singularity in the density of states, with a redshift from 4.6 electron volt in single layer graphene to 4.4 electron volt for bilayer graphene. Hence, such peak shift happens also in non-AB stacked graphene samples. The extinction coefficient peaks in the optical spectra of bilayer and trilayer graphene on silicon at around 3 electron volt are due to the nearest neighbor term, which gives a reasonable description of the Dirac cones at low energies. The optical models of monolayer, bilayer, and trilayer graphene samples on PET were represented using 2 Lorentz oscillators. The oscillators at 4.6 electron volt are due to the Fanov singularity in the graphene's density of states. Remarkably, the redshift of this peak is not reported, while it was visible on bilayer graphene on silicon. Consequently, the redshift of the absorption peak is dependent on the substrate. Herein, the optical properties of graphene oxide deep-coated on magnetro-sputtering titanium, gold, and silver thin films were discussed. Moreover, the optical properties of graphene oxide, thermally reduced graphene oxide stabilized with PSS, and graphene nanoplates films were summarized. Finally, the optical properties of chemical vapor deposition grown monolayer graphene samples and of chemical vapor deposition grown bilayer and trilayer graphene samples on silicon and PET substrates were reported. Future investigation of ways of graphene oxide films should mainly focus on a much deeper understanding of the reduction mechanism. In fact, further studies on the controllable oxidation and reduction of graphene oxide could improve its utilization as a semiconductor for transistor and photoelectronic devices, Moreover, WAIS could be used to study the optical properties of compounds made by combining graphene-based materials with other 2D materials and matrix polymers. Finally, as topic board member of Crystals, I take this opportunity to recommend you this journal. Thanks for your attention.
Okay, thanks, Grazia, for your nice talk. Now it's time for questions. I don't see question from chat. Okay. I have a question. I understand that you check your data using Kramer's relation, no? Do you compare your data with theoretical model based on density function theory or somewhere else?
For example,
For example, for monolayer, graphene monolayer, that is very considered in literature.
the theoretic TST, for example, we have used Kramer's Kronig, we have used Lorentz oscillator models, Gaussian models, Cauchy-Lorentz. We haven't done, for example, a DST model. No, we have used only the models provided by the ellipsometers software.
Okay. Another question: did you quantify the effect of substrate on this on graphene or?
Yes, in fact, we have seen that the substrate affects the optical properties of the samples. In fact, we have found different values for graphene oxide discoated on silver or gold. And moreover, we have found in the work variable angle spectroscopic ellipsometry of chemical vapor deposition ground graphene that in the substrates there were doping effects that we have calculated in this work.
Okay, thanks for your reply and for your nice talk. Now there is the next talk. The speaker is Emanuele Longo. Are you ready, Emanuele? Okay, and
yes, I'm ready. But I think it's a pre-recorded.
It's a pre-recorder, and the title of this talk is Large Spin to Charge Conversion at a Room Temperature in a Standard Epitaxial SP2T3 Topological Insulator Chemically Grown on Silicon. The floor is yours.
Thank you. I think that the presentation should start. Welcome everybody, and thank you for being here today. I am Emanuele Longo, and I'm a research fellow at the CNR IMM unit of Arete Brianza in Italy. And today I would like to talk with you about my work, which is entitled Large Spin to Charge Conversion at Room Temperature in Extended Epitaxial Antimonotone Topological Insulator Chemically Grown on Silicon. This presentation is divided mainly in three parts. I will start with a brief introduction about the spin to charge conversion mechanism at the interface between ferromagnetic thin films and topological insulators, and then I will discuss the results obtained on the growth of the epitaxial antimonotone topological insulator and on the ferromagnetic resonance and spin pumping measurement performed on gold, cobalt antimonotone and gold, cobalt, gold antimonotone heterostructure. And then I will conclude by explaining the origin of the enhanced damping constant observed in gold, cobalt antimonotone heterostructure and demonstrating the large and effective spin pumping in the large area antimonotone topological insulator. Let's start explaining what is spintronics. Spintronics is a branch of electronics in which the people use the spin of the electrons in order to engineer new device functionalities. In principle, spin-based devices are supposed to be ultra-low power with a higher density on a chip and ultra-fast as compared to the conventional electronic devices. If we think to a magnetic memory storage process, and if we think to have a ferromagnet and an heavy metal, and to a charge current which is flowing inside the heavy metal, what happens is that the electrons experience a spin splitting with a consequent spin accumulation at the boundaries of the heavy metal. And through this spin splitting, we are able to control the magnetization in the ferromagnet through the so-called spin orbit torque effect, and so by controlling the magnetic state of the ferromagnet. The use of the topological insulators in place of heavy metals, it is supposed to boost the efficiency of the spin-to-charge conversion. And due to the Dirac-like surface states, the topological protection of those states, and the spin momentum locking that electrons experience flowing across the surface states of a topological insulator. The second generation of three-dimensional topological insulator is composed by bismuth and antimony chalcogenide, and here we will discuss on antimony telluride because it is poorly investigated as compared to the other two compounds. What we did to grow antimony telluride with an epitaxial fashion was to use a metal organic chemical vapor deposition on a large area on a 4 inches silicon 111 wafer, and we performed some thermal treatments in order to improve the crystalline quality of the film, starting from a granular fashion towards an epitaxial quality. Here, the topological nature of the film was checked by magnetic transport and ARPS measurements. The magnetic analysis on these materials is performed by broadband ferromagnetic resonance at room temperature, which is a very powerful technique which gives us the possibility to measure a lot of different magnetic properties of a material. In order to integrate the ferromagnet on top of the epitaxial antimony telluride, we use the ABM evaporation, and in particular, we choose cobalt to deposit on top of the epitaxial antimony telluride. And here we also cap the cobalt thin films with a 5 nanometers thick gold layer in order to avoid the oxidation of the ferromagnetic film. We perform broadband ferromagnetic resonance in the in-plane configuration, so by putting the external magnetic field parallel to the surface of the sample, and we analyze the response of the signal as a function of an external frequency. And here, the relationship between the resonance frequency and the resonance field was given by the Kittel equation, which gives us information about the effective magnetization of the film. Here we can see the evolution of the Kittel equation as a function of the cobalt thickness, which is in accordance with the shrinking of the cobalt layer. And then here, by plotting the effective magnetization as a function of the inverse of the cobalt thickness, we were able to extract the saturation magnetization of the cobalt layers, which is in accordance, which is very close to the bulk cobalt saturation magnetization, which means that we have a high quality cobalt layer. Here, by studying the line width of the FMR absorption line as a function of the resonance frequency, we were able to extract information about the inhomogeneous broadening and the damping constant, which is important to determine the spin mixing conductance. What we observed is that if by extracting the alpha values from the slope of these lines and plotting this value as a function of the inverse of the cobalt thickness, we observe that we have a bad linear correlation, because according to the spin pumping theory, the evolution of the alpha as a function of the inverse of the ferromagnetic thickness should be linear. But here we have not a linear correlation. It seems to be more parabolic. And so this could lead to an overestimation of the spin mixing conductance, and thus to an overestimation of the spin current generated. By searching evidences of overestimation of spin mixing conductance in literature, we found that in a very recent paper in ferromagnet heavy metals bilayer, the authors observed these similar trends in their material, and they treated this behavior by adding a parabolic term which was attributed to the 2 magnum scattering coefficient, which is an energy transfer process from the uniform ferromagnetic resonance precession to degenerate spin waves. And here, so by using this model to fit our data, we found that we have a more reliable fit, and we were able to decouple the TMS signal from the pure spin pumping. Here, the presence of TMS hides the effective spin pumping efficiency, and to our knowledge, a TMS analysis on ferromagnet topological insulator bilayer have never been reported so far. So in order to study the origins of this effect, we decided to produce a new set of samples by putting an interlayer of 5 nanometer thick gold in order to decouple the interface between cobalt and antimoney telluride. And here, with the idea to prevent the damage of the topological surface states of the topological insulators from the magnetic impurities. And what we found by carrying out the same ferromagnetic resonance analysis on the new set of samples, we found that the introduction of the interlayer suppressed the TMS signal, and so we observed a pure spin pumping effect. But for a direct confirmation of the spin pumping, we can also perform analytical detection of this phenomenon. What we did was to perform a spin pumping ferromagnetic resonance at room temperature, and so we produced a new set of samples where we fixed the cobalt thickness to 5 nanometers, and we produced 2 reference samples in order to identify the role of the gold layers in the overall signals. What we did was to put the sample on top of a coplanar waveguide, and we connected the edges of the sample with an AG paint, and we measure a drop of potential across the junction during the resonance. Here, the black dots indicate the DC signal, which is called mixing voltage, and the signal was fitted with a Lorentzian function, which is divided in 2 parts, in asymmetric parts, which is attributed to the spin pumping signal, and an anti-symmetric part, which is attributed to the rectification effects, here represented respectively with the green and the blue lines. Here we reported the 3 samples and all the parameters correlated to the samples, and what we found is that the detected DC voltage signals are in accordance with the spin pumping theory, because here we can see that the DC voltage signal is superimposed to the FMR signal, and we can see that by reversing the external magnetic field, also the spin pumping signal was reversed, here the green line. By plotting the spin pumping signals of the 3 samples normalized over the resistance and the width of the samples, we extract information about we extract the values of the 2-dimensional charge current, and as we can see here, we have that by the introduction of the antimoney telluride layer produce a huge announcement of the produced charge current density of the 250%. In order to calculate the spin-to-charge conversion efficiency, we have also we must calculate the spin mixing conductance. So we performed the broadband ferromagnetic resonance analysis on the samples with antimoney telluride and without antimoney telluride, with just a tri-layer, and we subtracted the contribution of the damping, which only coming from the tri-layer of gold, cobalt, gold. And so what we did was to calculate the spin mixing conductance and then to calculate the 3-dimensional current density with this equation. In order to extract the spin-to-charge conversion efficiency in this structure, we use the inverse SNA effect principle. So we, on the hypothesis that we have a purely 2-dimensional electronic transport in antimoney telluride topological surface states, and here the figure of merit of this effect is given by the inverse SNA effect length, and basically by the ratio between the 2-dimensional charge current and the 3-dimensional spin current. And what we obtain here using 2 methodologies are 2 values, which are 0.28 and 0.75 nanometers. And which which are an indication of the possible range according to the fitting procedure. The novelty here of this research was that we have here a first demonstration of the spin-to-charge conversion in antimeteorite, and we have a first demonstration of the spin-to-charge conversion in a topological insulator, which was chemically grown on a large area. And then here, the 0.75 is a record value for spin-to-charge conversion efficiency for chalcogenide-based topological insulators. And we also pointed out that there's a need of a universal methodological approach for spin-to-charge conversion estimation. And all these results are summarized in a paper, in our paper, which is under revision. So to conclude, we achieved an epitaxial antimeteorite quality, an epitaxial quality of the antimeteorite thin film on a large area on silicon 111 using metal-organic chemical vapor deposition, and we managed to suppress the TMS effect in gold-cobalt antimeteorite through heterostructure through the introduction of a gold interlayer at the cobalt antimeteorite interface. Moreover, we performed simultaneous magnetic and electrical detection of spin pumping in the optimized gold-cobalt-gold antimeteorite heterostructure, reaching a record value of 0.5 nanometers for the inversely distant effect length, which was second only to stannine. And this is of potential interest for innovative spintronic application. I would like to acknowledge Professor Marco Fanciulli of Department of Material Science at the University of Milano Bicocca for the access to the FMR facilities. And I want to underline that all this work was conducted in the framework of the SkyTop European project. And thank you all for your kind attention.
Okay, thanks a lot, Emanuele, for your nice talk.
Thank you.
It's time for questions from chat. I don't see any question. I am not an expert of this subject. I am only curiosity. Do you think that other topological insulator could be more efficient with respect to your configuration, or?
Yes, for sure. In the future, I think that something more will be done. So this is a very huge question. So yes, in the future, for sure,
okay.
something better will happen. So.
Okay. Another question, more technical. What do you expect by varying the thickness of topological insulator?
Yes.
There is a.
Sorry.
Okay. No. What do you expect by considering different thickness of your topological insulator?
Yes, the idea is that varying the thickness of a topological insulator and performing spin pumping experiment, we can have access to the spin diffusion length in our material, which is a lack in our study up to now. Because if you study a signal with a single thickness, indeed, as I told at the end of my talk, the interpretation as a purely two-dimensional transport was just an hypothesis, because we cannot. We have a strong indication that it is a two-dimensional transport, but we cannot be sure because we don't know how how the signal behaves as a function of the topological insulator thickness, which could will disentangle the bulk contribution from the
bulk contribution. Okay. Thanks a lot for your reply and for your nice talk. Thanks. I want to thank again the last three speakers, and I leave the floor to the next session. I leave the floor to Alessandra. Okay.
Thank you, Carlo. Thank you so much.
You're welcome. Okay.
To chair this last session of this interesting meeting. And so I think we are perfectly on time. So we can, let's just introduce myself. I'm Alessandra Continenza from University of l'Aquila. So I'm going to chair this next session. And the first talk scheduled on this session is by Carlo Rizza, once again, from Università degli Studi dell'Aquila. And he will be talking about artificial magnetism through mimicking magnetic localized surface plasmons. So please, Carlo.
Good afternoon, everybody. In this talk, I will discuss a new strategy to achieve artificial magnetism by using a peculiar phenomenon, the mimicking of magnetic localized surface plasmon. This work is in collaboration with the MRI group at the University of l'Aquila, Professor Marcello Alecci, Angelo Galante, and in collaboration with Elia Palangi. First of all, I will discuss the state of art about artificial magnetism in metamaterial science. After, I will talk about magnetic localized surface plasmon, and finally, I will discuss the new strategy for achieving artificial magnetism through magnetic localized surface plasmon mimicking. Metamaterial are arrangement artificial structures elements designed to obtain advantages and unusual electromagnetic properties. A metamaterial structure is generally described in the homogenized regime, where the parameter d, the period of the structure, is smaller than wavelength. In this regime, the electromagnetic response of the metamaterial can be described by few electromagnetic parameters: the effective permittivity, the effective permeability, and by tailoring the geometry of the structure and by choosing a suitable material for inclusions, in principle, one can obtain the desired electromagnetic response and the desired effective permittivity and effective permeability. It is very interesting to note that by considering a metamaterial approach, one can obtain magnetism property, significant magnetism response at the optical frequency. And this is an important ingredient in several applications, photonics phenomenon such as invisibility clocking, negative refraction, and artificial magnetism is useful in at the radio frequency range for enhanced performance in magnetic resonance imaging. And it is very intriguing to note that the magnetic materials support exotic waves such as magnetic surface plasmon polariton and magnetic localized surface plasmon that are the magnetic counterpart of the standard surface plasmon waves. Artificial magnetism is generally realized by considering metal inclusions inside metamaterial structures. Here, the effect is due to the giant induced current in these meta atoms, and another strategy to obtain artificial magnetism is to consider high-index electric material as inclusions inside the metamaterial structures. In this situation, the phenomenon is due to the high displacement current that are very high, since the epsilon is very high. Here, I focus my attention on magnetic localized surface plasmon supported by magnetic sphere. Magnetic localized surface plasmon are the magnetic counterpart of localized surface plasmon, and in this situation, we have that a magnetic, negative magnetic permeability support several confinement waves known as magnetic localized surface plasmon. In summary, by using the metamaterial approach, we can obtain a magnetic property. On the other hand, metamaterial science shows some disadvantages. So metamaterials can require complex fabrication, and they are not suitable for nanophotonic applications, since the effective response is altered by subtle feature to the inclusion, and these are very detrimental in a nanophotonic regime. Here we propose an alternative approach to overcome this disadvantage, and we propose the electromagnetic mimicking to obtain artificial magnetism. We have considered a homogeneous structure in the electric sphere. In this situation, the electric sphere supports wave modes that share some features in common with magnetic localized surface plasmon. For more precisely, by using the Mie theory, we have investigated the wave modes supported by the electric permittivity and the wave modes supported by magnetic permeability. In some condition, one can show that the profile of the modes supported by the negative magnetic permeability sphere reported here as a dashed line, share the same profile of the the wave supported by the electrical configuration outside the sphere, whereas inside the sphere the profile are very different, as reported in the figure. This is the electromagnetic mimicking. Here I report the result concerning on the first the fundamental modes, and the magnetic localized surface plasmon exists in the situation where mu is about -2, as reported in the first panel, the panel A, and the equivalent, the electric permittivity, is reported in panel B and C. Note that epsilon is very high in this situation. In addition, we have considered the discrepancy between the two electromagnetic configurations. C is related to the difference between the two electromagnetic field, and we have that this parameter is very low in the considered situation, and depend on the geometrical parameter, and depend on the electromagnetic losses that are detrimental for this mimicking effect. In order to confirm our theoretical analysis, we consider also full-wave simulation. In this numerical simulation, we consider that the electromagnetic field is generated by a near-field source, their yellow ring around the electric or magnetic sphere, and we have compared the result. We have compared the electromagnetic field supported by the magnetic sphere and the electromagnetic field supported by the electric one. The solid line is the field supported by magnetic sphere, and the green surface is the field supported by the electric sphere. The mimicking is good, the agreement is good. We have only a small deviation near the source, the yellow ring figure. In conclusion, we showed the possibility to mimicking magnetic localized surface plasmon supported by magnetic sphere. It's very interesting to note that we obtain a negative permeability behavior in the far and near field. Note that metamaterial approach does not work in the near field. About future developments, we will consider the fact that at the radio frequency, since ferroelectric ceramics are rolled and show at index the electric constant at this range of frequencies. And next theoretical step will be to use all wave modes, high order surface plasma modes, and we will investigate the other geometries. We try to generalize our approach to other geometries. Thanks for your attention.
Okay, thank you, Carlo. Let's see if there are questions and remarks. It's very interesting indeed that you can sort of heat a material, you know, just of properties, just using different materials with completely different properties, and you know, get electromagnetic fields which really look like the same. So did you really try indeed with the values for, I saw in your last slide that possible candidates for this?
Yes, we have purchased in the last slide. There is a figure of a ball, the electric sphere, and this is ferroelectric ceramics showing a very high dielectric permittivity, 1000. But this is possible because it is ferroelectric, and this is a possible candidate for this phenomena. And at the radio frequency range, okay. And we will investigate the response, the mimicking of this surface plasmon at the radio frequency in collaboration with the magnetic resonance imaging group of University of L'Aquila.
Oh, okay, so I mean, you had already some tests for feasibility to realize such a system. So, well, that's interesting indeed. Nice.
The sensitivity, sorry?
No, I mean, you really had the way to test the feasibility of
the accessibility. Okay. Yes. The idea is to consider a reflection transmission experiment to obtain the response of this sphere at a radio frequency source and now we will investigate this effect. Okay.
Okay, I see. Well, thanks. I don't see other questions coming or remarks. So, if this is all. I see Carlo already, probably ready to.
Sì, Alessandra, grazie.
Grazie a te.
Grazie per la Woman Chair e un saluto allora da parte mia come Chair della conferenza a tutti voi partecipanti, un ringraziamento molto sentito non solo a voi ma anche alle prestigiose organizzazioni di ricerca come il CNR e anche organizzazioni che hanno partecipato. È chiaro che la cerimonia conclusiva parte da dei ringraziamenti. Innanzitutto non posso mancare di ringraziare il mio collega Antonio Politano del DSFC, del Dipartimento Scienze Fisiche e Chimiche dell'Università dell'Aquila, che ha messo a disposizione la sua rete vasta e capillare di contatti e di conoscenze. Non posso mancare di ringraziare naturalmente le mie due collaboratrici, le ingegneresse, come si dice adesso, Valentina Paolucci e Jessica De Santis, e soprattutto di questi tempi la regia di tutto questo evento, che è il carissimo dottor Maurizio Cironi. Detto questo, ho un po' di numeri della conferenza. Abbiamo avuto circa 170 iscritti, 14 keynotes, 44 invited e più la partecipazione di 10 espositori di organizzazioni che hanno a che fare con servizi e apparecchiature e sistemi per quanto riguarda la scienza dei materiali. Naturalmente un ringraziamento molto sentito va al Consorzio Interuniversitario Nazionale della Scienza e Tecnologia dei Materiali, ovvero INSTM, che ha patrocinato questo evento. E a tale proposito darei la parola per un saluto e per proclamare sostanzialmente i due premi sponsorizzati da INSTM al collega Andrea Caneschi, presidente del INSTM. Prego Andrea.
Buongiorno a tutti, è sempre un piacere vedere delle organizzazioni di successo, di workshop di questo tipo e quindi insomma a noi ha fatto piacere sponsorizzarlo a prescindere prima. Dopo siamo stati ancora più contenti perché abbiamo visto che ha avuto veramente un ottimo successo, quindi è stata una buona attività in comune. Tra le varie attività che facciamo c'è anche quello di cercare di supportare un pochino i giovani migliori che sono nel campo della chimica, della fisica, dell'ingegneria, per dargli un po' di aggiunte al loro curriculum, no? E questo il consorzio lo fa essendo molto dinamico nella creazione di borse e altre forme contrattuali nei periodi in cui c'è bisogno di coprire qualche persona che non sia strutturata, ma cerca di farlo anche dando piccoli premi che gratifichino le persone e che ne riconoscano un po' la qualità, perché questo a livello internazionale è un po' un punto debole dell'Italia, cioè in Italia si danno pochi premi. Se uno guarda i CV degli inglesi sembrano siano tutti premi Nobel, però sono un po' troppi, ecco. E invece noi siamo molto poco premiali in questo senso, quindi anche dei piccoli premi servono alla fine a dire che qualcuno ha riconosciuto che le attività di certi ragazzi erano da premiare, da riconoscere e così via. Detto questo, dare premi è piacevole perché è una cosa gradevole, non è gradevole nonostante tutto scegliere, non è gradevole scegliere perché spesso ci si trova in imbarazzo e anche questo è stato un caso, nel senso che i piccoli premi che vengono assegnati oggi sono con diciamo, il curriculum, cercando di normalizzarlo più o meno per l'età accademica delle persone, quindi qualità del curriculum un po' normalizzato, un po' anche sulle presentazioni che hanno fatto presso di voi, e l'insieme di tutto questo però, come dire, ha portato molte persone a essere diciamo, di area premiabile, e quindi c'è stato un po' di imbarazzo. L'imbarazzo però è anche una riconferma della qualità della ricerca e dell'entusiasmo che hanno i ragazzi che entrano adesso nel campo in cui noi siamo da molto tempo. Quindi ho fatto questa breve premessa semplicemente per dare un pochino un quadro che è questa attività premiale, e adesso quindi dovrò dire chi sono i vincitori, secondo noi ovviamente, e secondo noi e secondo gli organizzatori. Quindi come premio INSTM ne abbiamo due, vado in ordine alfabetico. Il primo è al dottor Antonio Agresti. Allora, Antonio Agresti è della Università di Roma Tor Vergata, e viene premiato per, come dire, la sua produzione scientifica elevata come quantità e qualità, e che è essenzialmente incentrata sul campo delle celle solari. Lui ha lavorato anche a un centro, al centro solare di Tor Vergata, no? Per qualche anno, è andato un'occhiatina, e anche per il suo contributo che era MXNS and Emerging 2D Materials for Perovskite-Based Photovoltaics. Ecco qua. Allora, questo è, diciamo, come dire, quello da mettere nella cornice, e poi il premio associato ti contatteremo per ovviamente fartelo avere. Quindi complimenti ad Antonio Agresti.
Aspetta.
Grazie mille, grazie
Bene.
a tutti quanti, grazie. Grazie al comitato organizzatore, grazie per la bella esperienza e grazie per l'interessantissima conferenza.
Grazie a te, Antonio. E il secondo invece va a Emilia Paone, e Emilia ha presentato un contributo che è Spent Lithium Cobalt Batteries, Efficient Heterogeneous Catalyst for Reductive Upgrade of Biomass Derived Furan. Ecco, quindi questo è stato il titolo del contributo che ha presentato. Poi anche lei nelle motivazioni ha la operosità, che mi piace molto come termine, operosità scientifica, nel campo principalmente della chimica verde, ma l'approccio che ha fatto Emilia è un approccio, direi, piuttosto multidisciplinare, quindi decisamente interessante. Quindi, come dire, complimenti anche a Emilia Paone, che viene dall'Università di Reggio Calabria. C'è anche
Grazie mille, vorrei ringraziare il professore Caneschi e tutta l'organizzazione del congresso. Grazie per questo premio che naturalmente mi onora molto. Per tutta la riuscita dell'evento in generale, che ho seguito, è stato molto piacevole, molto formativo, e quindi ringrazio tutti.
Bene, grazie Emilia. Io quindi a questo punto, come
Sì,
dire,
riprendo la parola io, Andrea.
Perfetto, benissimo.
Quindi ringraziamo anche INSTM per il patrocinio e per i due premi. Prima di proseguire una nota tecnica, diciamo subito che il comitato organizzatore di New Times si è permesso di identificare attraverso una menzione d'onore altri partecipanti al convegno, e questa comunicazione vi sarà data al termine di questi miei saluti, vi sarà data dal collega Antonio Politano. Per quanto riguarda
Ottima
Sì,
iniziativa, perché veramente è stato
grazie.
imbarazzante scegliere
Grazie.
dove scegliere, grazie davvero.
E poi lasciatemi concludere con una nota un po' più locale, ma non per questo meno importante. Io avevo un grande affetto con il professor Giovanni Schippa, che è stato il pioniere di ingegneria dei materiali qui all'Università dell'Aquila, e ha dato un contributo eccezionale e ha lanciato tutti i gruppi che lavorano nel settore qui presso l'Università dell'Aquila. Per cui il comitato si è sentito di sponsorizzare 2 premi a memoria del professor Giovanni Schippa, e questi 2 premi è aperta la call, quindi per i ricercatori under 35, tutte le modalità di erogazione del premio sono riportate sul sito di New Times, quindi chi è eleggibile può andare a verificare i requisiti, e vi informo che la premiazione sarà effettuata in occasione del convegno nazionale AIMAT, Associazione Italiana dei Materiali per l'Ingegneria, che si terrà a Cagliari a settembre. Quindi avevamo questo tributo da dare a un nostro fondatore qui
Ed ex
locale.
rettore pure.
Certo, assolutamente. E ultimo, ma per questo non meno importante, diciamo che siamo stati contenti, siamo molto contenti della riuscita di questo convegno, e in fondo questo successo ci porta anche a pensare a poterlo replicare, e pensiamo sicuramente di metterci in between, come si dice. Probabilmente sfrutteremo queste opportunità che ci sono state scoperte in questa contingenza Covid, e lo faremo online con una frequenza da verificare e da stabilire nel futuro, e apro una call anche a tutte le organizzazioni, a tutti coloro che sono interessati a una partnership in questo diciamo evento che è New Times, per poter contribuire, darci idee, partecipare con noi in questa, diciamo, che è una occasione molto grande e anche eccezionale di proporre qualcosa in maniera alternativa, non di nuovo. Il nostro obiettivo è dare grande spazio ai giovani ricercatori italiani. Quindi mi sento di concludere a questo punto con una speranza proprio di avere questi giovani con noi nella prossima edizione. Per cui vi ringrazio di nuovo, è stata un'esperienza per noi eccezionale, molto bella, e sicuramente speriamo di rivederci, come si dice, su questi schermi. Grazie a tutti, grazie per la partecipazione e buona serata a tutti quanti. Grazie, arrivederci.
E adesso passiamo ad un evento satellite in collaborazione con Gambetti Chenologia. Chiedo al dottor Paolo Carrozzo di collegarsi, di accendere la webcam. Paolo, ci sei? Allora, Gambetti Chenologia ha sponsorizzato 2 premi per i migliori e-poster nel campo della scienza delle superfici e nel campo della nanoscienza, quindi per le sessioni 5 e per la sessione 6. Ieri abbiamo fatto un evento, che è un vero e proprio salotto Gambetti a fine giornata. E adesso, molto più brevemente rispetto a ieri, facciamo un evento simile per premiare il miglior e-poster della sessione 6 di nanoscienza, nanostrutture e nanomateriali. Allora, la commissione del comitato organizzatore di New Times, New Trends in Material Science and Engineering, ha valutato tutti gli e-poster della sessione 6 e ha stabilito che il vincitore del premio Gambetti Chenologia per la nanoscienza è il dottor Stefano Scurti dell'Università di Bologna. Stefano, ci sei?
Ci sono. Colgo l'occasione per ringraziare il comitato organizzatore e anche la Gambetti Tecnologia per il premio che mi è stato assegnato, e anche il mio gruppo di ricerca del Dipartimento di Chimica Industriale dell'Università di Bologna. Sono molto orgoglioso di aver ricevuto questo premio al mio primo congresso, perché faccio il primo anno di dottorato di ricerca in chimica. Mi sono molto colpito dall'organizzazione e dalla struttura dell'evento, soprattutto, nonostante sia stato svolto completamente online, quindi un ulteriore applauso agli organizzatori e a tutte le persone che sono state dietro nell'organizzazione di questo incontro. Grazie.
Adesso mandiamo in onda il tuo e-poster, perché gli e-poster sono dei poster in PDF con un supporting video di qualche minuto.
Good morning, everyone. I'm Stefano Scurti. I'm a PhD student in chemistry at the University of Bologna. Today, I'm going to talk about the influence of hydrosoluble polymeric stabilizer in...
Che è successo? È rimandato in onda il video.
Good morning, everyone. I'm Stefano Scurti. I'm a PhD student in chemistry at the University of Bologna. Today, I'm going to talk about the influence of hydrosoluble polymeric stabilizer in nanocatalyst, and in particular, we are focused on the molecular weight effect of the polymeric stabilizer used. In the wet chemical preparation of nanoparticles involves the utilization of specific ligands that can be in the surface of nanocatalysts to tune the nanostructure and prevent the aggregation phenomena by lowering the free energy of the metal surface. Polymeric coating of colloidal particles is a robust and effective technique for imparting colloidal stability, and the conformation of surface ligands on confined nanoparticle surface is largely determined by the chain-length, charge, density of the ligands at the nanoparticle surface. In addition, novel studies have focused on the effective role of the polymers in the catalytic mechanism in terms of active phase, coverage, selectivity tuning, and promotion effect mediated by defined functional groups. In this work, we have chosen 3 different hydrosoluble polymeric stabilizers such as polyethylene glycol, polyvinyl alcohol, and polyvinyl amine. And we have studied the impact of the molecular weight of the polymeric stabilizer chosen on the sites and the catalytic activity of the gold nanoparticles supported on active carbon. The different molecular weights were obtained by chain transfer reaction to solvent. In this optic, 3 solvents able to chain transfer with different intensity was chosen in order to tune the molecular weight of the polymer. The polyethylene glycol used with different molecular weight were commercially available. Instead, the polyvinyl alcohol and the polyvinyl amine were synthesized by solution radical polymerization of the related monomer in the first step, and in the second step, by direct saponification, we have obtained the final polymer. The gold nanoparticles supported on active carbon were synthesized by solely mobilization method using a tetrachloroauric acid like a precursor and sodium borehydride like the reducing agents. The XRD diameters calculated by the Scherrer equation showed a direct correlation with the molecular weight. When they use a polymer with high molecular weight, the size of nanoparticle increased. On the right, we can observe the transmission electron microscopy image performed in order to confirm the nanometer dimension of our system. The 4-microphenol catalytic reduction with sodium borehydride as the chosen reduction agent has been used to investigate the catalytic activity of synthesized gold active carbon catalyst. The influence of molecular weight on the apparent pseudo first-order kinetic constant are here reported, and a peculiar trend we can observe. The catalytic performance are better when the molecular weight decreased. For the samples synthesized with PBA and polyvinylamine, we can observe a second effect due to the high amount of functional group on the side chain, which can block the diffusion step on the reagents on the catalytic metal surface. And in order to explain and confirm this behavior, we have synthesized gold nanoparticles with different gold polymers weight ratio. When the ratio decrease, the catalytic performance increase, and from these results, it seemed that the amount of polymer could influence the diffusion of the reactants to the particle surface. The reagent, in this case for nitrophenol, to diffuse from the reaction medium to the gold surface and to cross the polymer layer around the gold nanoparticles. And a low amount could promote this migration and therefore influence the catalytic activity. To complete the investigation of the gold active carbon catalyst, a reusability study was also carried out, and here we've reported the reusability for the best gold active carbon catalyst of the polyethylene glycol series. As displayed in the figure, the conversion remained constant at around 18% when the a defined reaction time was defined. At the end, the catalytic activity observed has been explained based on a structural activity correlation, and the molecular weight of the stabilizer using nanostructured material synthesis can be considered a significant parameter for controlling activity and catalyst stability. It can be offered a toolbox for design highly effective and stable catalyst. Thanks for the attention.
Allora c'è Paolo Carrozzo di Gambetti Tecnologia che vuole fare i complimenti.
Mi congratulo col dottor Scurti per aver vinto il premio. Mi spiace per questi problemi di connessione, ma sono i side effect di queste nuove metodologie di conferenza. Speriamo quanto prima di poter tornare a una pseudo normalità, anche se questo modo di fare conferenze, di fare incontri non deve essere sicuramente abbandonato. In qualità di rappresentante di Gambetti Tecnologia sono veramente orgoglioso di poter dire che appunto questo premio sia stato assegnato alla macro area della nanoscienza. Anche perché da vecchio dottorato al Politecnico di Milano, e quindi che ha avuto a che fare tantissimo con la ricerca, col mondo della ricerca, sa quanto è importante ricevere le giuste gratificazioni e i giusti premi per il lavoro svolto, che non è mai abbastanza. Quindi mi congratulo, spero che questo sia soltanto l'inizio per il dottor Scurti e che sia il minore dei traguardi raggiunti.
Grazie Paolo. Stefano, un brevissimo commento su quali sono le prospettive future di questo lavoro.
Allora, ringrazio il signor Paolo, che non riesco a vedere il cognome, quindi
Carrozzo,
per l'in-bocca al lupo e per le belle parole rivolte verso il premio che mi è stato assegnato. Beh, questo lavoro è un lavoro molto interessante perché si basa sul concetto che è possibile sfruttare la versatilità dei polimeri in termini sintetici per poter influenzare quello che sono poi le attività catalitiche dei materiali nanostrutturati. Quindi fondamentalmente, anziché andare a ricercare e ad applicare a livello industriale complesse metodologie per ottenere catalizzatori altamente performanti, si possono sfruttare, o perlomeno l'idea è quella di sfruttare le proprietà intrinseche anche nella composizione delle macromolecole per poter avere un miglioramento delle performance catalitiche. Quindi sicuramente sono soltanto all'inizio, come dicevo prima, è solo il primo anno di dottorato di ricerca in chimica, quindi spero che negli anni a venire posso sicuramente implementare e migliorare quella che è questa attività di ricerca, che però ha già mostrato degli ottimi risultati per il futuro.
Sì, la nanocatalysi è estremamente affascinante. E allora ringraziamo ancora il dottor Carrozzo e il Gambetti Tecnologia per il supporto a questa conferenza. Facciamo ancora gli auguri a Stefano, così come a Antonio ed Emilia per i premi NSTM. E adesso concludiamo con le menzioni d'onore per le sessioni 1 3 e 5, anzi 2, 3 e 5, perché per la sessione 1 e la sessione 4 già avevamo premiato le migliori comunicazioni con un premio supportato da Assing. Ora chiedo alla regia di mettere in onda le menzioni d'onore che sulla base di una valutazione con il coinvolgimento dei vari chair abbiamo valutato che sulla sessione di Advanced Materials for Energy Conversion e Storage c'è un ex equo come menzione d'onore alla dottoressa Maila Danielis dell'Università di Udine e il dottor Andrea Marchionni del CNR ICICOM. Considerando l'elevatissimo numero di partecipazioni a questa sessione, abbiamo valutato anche il caso di dare un'ulteriore menzione d'onore per il campo dell'energy storage. Posso fare già uno spoiler sulla seconda edizione di New Times. Questa sessione sarà suddivisa in Energy Conversion e Energy Storage. Quindi facciamo anche i complimenti alla dottoressa Erika Michela De Matteis dell'Università di Torino. Per quanto riguarda la sessione 3, Advanced Materials for Nanobiotechnology, quella di biomateriali e biotecnologie, e la dottoressa Laura Matino dell'IIT di Napoli ha la menzione d'onore da parte del comitato di New Times. E infine, per la sessione 5, New Trends in Surface Science and Coatings, c'è un ex equo tra il dottor Tummala e del CNR IMM di Agrate e Brianza e il dottor Gaetano Caloggio del CNR IMM di Catania. Per questa sessione, di cui sono stato io il session chair, si è pensato di dare una menzione ad un teorico e ad uno sperimentale. E manca la sessione 6 perché è terminata da poco ed è venerdì pomeriggio, quindi ci sarà una menzione d'onore, però non abbiamo avuto il tempo di organizzare la valutazione. In ogni caso facciamo i complimenti a tutti i partecipanti perché questa conferenza ha avuto un'elevata qualità scientifica e una grande partecipazione da parte della comunità di chimica in primis, poi di scienze dei materiali e anche di fisica. E quindi davvero grazie a tutti e speriamo di ritrovarci su questi schermi prossimamente. Ringraziamo di nuovo tutti coloro che hanno supportato questa organizzazione, con gli sponsor, gli esibitori e le organizzazioni, INSTM e l'Università dell'Aquila. Allora, grazie a tutti e arrivederci.